Okay, there we go. Okay, Sue, pick somebody.
Doug? Has Doug gone?
Don't think so.
I'm sorry, my printer's going, so I hit it on mute. I apologize. I guess the simplest way to put it is I'm getting closer to retirement age, and I'd go nuts if I got nothing to do. So I'm just trying to build some skills to be able to be of service to other people as we go down the road.
Where do you live?
Southeast Michigan. So I echo a lot of the sentiments of the other people. I just don't know where it's going to take me just yet.
Okay, pick the next person.
Stephanie's Autopilot. The name intrigues me.
Stephanie's Autopilot. Okay, she might not be available. Let's go with Victor.
How about?
Now let's go with Victor.
Hello, my name is Victor. I'm a Portland University student, and I'm just currently learning. I want to learn ham radio because I'm interested, and yeah, I live in the Portland area. So,
And okay, cool. Are you at Portland State?
Yeah.
Oh,
yeah.
cool. Say hi to Andrew for me.
I'll pick Luke Maxwell.
Hi guys, my name is Luke Maxwell. I'm a student at Montana State University, originally from Kalispell. I'm now living in Bozeman.
Go Grizz.
Yeah, and so yeah, I just found out there was a ham radio club on campus, and that was something I've always been interested in. So I looked into it, and they sent me here. So I hope to get my ham radio license and kind of get more involved with that kind of thing. But yeah. Who else hasn't gone? Sorry, my laptop
Ellie
died for a minute. So
Ellie's new.
I'll call on Ellie.
Karen, Ellie. Take it, Ellie.
Hi, my name's Ellie Urbancic. I've got my camera off because I'm having my breakfast right now. I'm a sophomore at the University of Oregon in Eugene, and I've always liked Morse code a lot. I got really interested in Morse code in middle school and thought it was really cool. So ham radio is cool to me as an extension of that also. And I've been wanting to get my license for a while, and my mom told me about this class, and I'm excited to be here. A fun fact about me is I'm named after a fictional radio scientist. I'm actually named after Dr. Ellie Arroway from Carl Sagan's Contact, so I think that's fun.
And Ellie, so you met Hannah.
Uh-huh.
So I actually am a Morse code aficionado. Did you know that?
No.
No, I copy it 40, 45 words a minute.
Wow.
So I can teach you as much Morse code as you like.
Fantastic.
My favorite mode.
Okay, who hasn't gone yet?
Karen, I think.
All right, Karen.
Hi, can you hear me?
Yep.
My name is Karen. I live in Eugene, Oregon. I have absolutely no relevant experience, but I'm on my neighborhood association board, and I'm trying to establish an emergency communications team. I encouraged my neighbor to take a ham class and get her license, so it's kind of now my turn. So
who is that?
My neighbor?
Yeah.
N7JI.
Oh, yeah. Okay. We live about a mile apart.
Oh, nice. Yeah, she's right across the street from me. So yeah, so I'm excited to be here. It's great to see folks from all over the country. I had no idea. So
I was in her attic helping her put an antenna out.
Oh, yes, she told me about that. That's awesome.
That was me.
Ah, great. Well, nice to meet you.
Who else hasn't gone?
How about Deborah?
Oh,
is Deborah gone?
How about Gina? Is it Jenna? I guess we'll find out.
Hi, it's Jenna.
Jenna. Okay.
Nice to meet you guys. I'm a freshman at the University of Alabama in Huntsville, where I'm studying industrial and systems engineering. But I've always really loved ham radios. I want to have some sort of job with it in the future. And I got introduced to this class specifically through the Space Hardware Club, where I heard a lot of people have their license. Yeah, I know, I'm super excited. I'm doing CanSat this year, so that's why I'm here. But I'm excited, so it's great. I will pass it on to Mr. Aaron Rowe.
Hello, I'm Aaron. If you guys can hear me.
Yep.
Whoops. Okay. I'm in Jefferson, Oregon, and I've had a long interest in emergency management stuff, and a long interest in amateur radio, but I waited till I'm 52 to actually do something with it. So I'm a little overwhelmed with all the math and stuff that, like some of you, but yeah, I think it's gonna be a fun hobby and be useful in some emergency management type stuff.
So that's Jefferson, just north of Albany, right? That area?
It is, yeah.
As opposed to the
Yep.
state of Jefferson.
Yes.
Is there anyone here
This-
who, is anyone here not from Oregon or California? You know what the state of Jefferson is? That was going to be the 51st state, and it was derailed by World War II. Southern Oregon and Northern California were trying to form into a state called Jefferson. So there's still something called like Jefferson Public Radio, and there are signs along the side of the road that say, "Welcome to Jefferson."
Oh, I didn't know that.
So those people are all wishful thinking, right?
Yep. Yeah, I don't think it's going to happen anymore, but there was a big push before World War II for that to happen. So, let's see, who haven't we talked to yet? Carolina. You're muted. There we go.
Okay. I'm Carolina, and I'm on the central coast of Oregon, and I'm a micro farmer. I'm part of a 100-year-old homesteaders group, and our CERT program, community emergency response team. And that's where I got Scott's information to do the ham radio. Our club, we'd like to create a network because we're very rural here out the Smith River. And so we have several ham radio people. I've never done ham radio, so this is brand new to me. And I've always wondered about electricity, so I'm learning that, which is cool. So I'm looking forward to having that rolling. It looks to me like it's going to take me a little while to figure this all out and memorize it. But repetition's already doing it, so keep reading my notes over.
And what's the nearest town to where you are?
I'm right on the edge of Reedsport, Oregon.
Oh, you know Melvina?
Malvina, yeah.
Melvina Adolf?
You gave me your contact.
Oh, good. Yeah. I've known her. She took my very first class 7 years ago.
Oh, cool.
Yeah.
Yeah. We'll be doing a CERT training coming up on the 9th of September.
Cool. Very cool.
With some more of the ham radio people there.
Okay, let's see who else.
Okay.
If you haven't gotten called yet, go ahead and just speak up if you want to. Otherwise, okay, let's start studying. All right, so thank you, everybody. Now, everybody hopefully knows everybody a little bit, at least anyone who wants to be known, so that's good. Now basically this is your cohort, this is the group of people who you're going to have gone through class with, and they're a resource if you choose to work together, and 5 years from now, say, oh yeah, I remember taking a class with you. So all right, so the first thing we're going to do is we're going to kind of not look at the book yet. And what we're going to do is we're going to draw this thing. And any idea what this poorly drawn thing is called?
That looks like the circle for the Ohm's law.
It does. Well, it's a circle for a lot of things, right? It's a very poorly drawn circle, but we're going to basically go with it being a circle. And I like this to be a very interactive class. So please feel free, unmute those mics and, blurt stuff out. So, okay, so this is a circle. And what we're going to do is we're going to give this circle a radius of 1 unit. This is known as the unit circle, right? Because it has a radius of 1 unit, whatever that happens to be. So there's a couple important things about this circle. Number one, the circle is the collection of all points that are 1 unit away from the center of the circle. Right. So that's basically every point that's exactly 1 unit away from the center. That includes this one over here. That includes this one over here. And that includes this one over here. And every other one you can think of from the center. Now, to differentiate all these points from each other, what we also have is an angle. And so this is our coordinate. This is our coordinate axis, where this is the x-axis and this is the y-axis. By definition, it's our Cartesian coordinate plane. And what by definition, how many degrees are in a circle, everybody?
360.
360. Okay, so that's 360 degrees. So because a circle is the collection of all points that are 1 unit away from the origin of the circle, we have to have some way of differentiating this point from this point, from this point, from this point, and all those other different points. The way we do that is we say that we are a distance 1 away from the center, and we've now moved through this particular angle, which is a portion of 360 degrees. By definition, this is our 0 degree mark, and our angle increases as we go this way. So it's counterclockwise around the circle. Carolina, are you watching on a phone or something bigger?
No, I'm on my computer.
You should be able to grab it,
There,
and
Just a little.
you should be able to pin it and make it full size.
Pin it. Just click on it.
Well, it depends on how big your window is. If you make your window, if you double click on that, on the top bar of the window, it'll make the whole window full size. And then you can select the,
Oh,
there's
there
like
it
a
is.
slider bar. You can make it super big.
Thank you.
Okay. All right. Want to be
I have
able
a
to,
question. I have
Yes.
a question much farther because I'm trying to relate it to, I was in real estate forever and ever.
Uh-huh.
So is this kind of like meets and bounds? Everything is north, south, east, or west from a specific meridian?
pretty much. Yeah.
Okay.
I mean,
That'll help.
different
Yep.
names, but yeah.
It
So,
gives me a reference point.
okay, so this is our 0 line. That's our 0 degree line. Right. Whereas, if you're talking about north, south, northeast, west, and south, you start at north being 0 degrees and work east. So, and then to south, but it's the same, it's a similar thing, except that by definition, 0 degrees is on the x-axis. And then you work up. So when you get to this point right here at the top, which I'll put in yellow, that's our 90 degree angle. When we get over here to the left, that's our 180 degree angle. And when we get down to the bottom, that's our 270 degree angle. Now, interestingly, as we go around the circle, what happens when we get back to 0? What's our angle?
0.
Well, it has multiple names.
359.
300, well, it's 360. 360 and 0 are the exact same thing. So what if I was to go the other way and my angle was counting up negative? That would also be negative 360. It could also be, if I went around twice, it could be 720. It could be negative 720. So there's
Correct? You mean?
Yeah.
Okay. Okay.
depending on
Okay.
which way I go around.
So
But
clockwise would
basically,
be
yeah, but basically all of those different angles have the, there's an infinite number of names for every one of those points. But to simplify things, what we usually do is we just go with the positive between 0 and 360 to give it a name. So now what we're going to say is, okay, well, how far away from the origin are we at this random point right here, up on the upper left? How far away from the origin are we?
Maybe 100 degrees.
Yeah, but I mean, from the origin, from the center of the circle.
One
We're
unit.
we're 1 unit away. That never changes. How about down here in the lower left? How far away from the origin are we?
1 unit.
1 unit. Yeah. Okay. That doesn't change. So the only thing that we really have to describe where we are is how much angle we've gone through, how much our angle has progressed. So what I'm going to do right now is I'm going to erase this screen and redraw this in a nice clean format, nice fresh circle. Here's our 0 degrees. Here's our radius of 1 unit. And we're going to go around this way. So as we pick a random point, like let's just pick this point, there's a couple of different things that we can do to this point. Again, what is the distance from the center?
1.
1. Okay. But now, how far are we in the X direction?
80?
Well, I mean, it's about 80 degrees, let's say. But how far, if we were to measure a distance from the origin, are we in the X direction? Well, it's less than 1, right? Because 1 would be all the way over here on the right.
Yep.
So it's less than 1. The other thing we could do is how far up are we? Well, we're not all the way up to 1, are we? But we're pretty close to 1. So these have different names. This function is known as the sine. That's the x-axis. And the other function in the y-axis, this is done, sorry, cosine for the x-axis and sine for the y-axis. So cosine and sine basically tell you what the projection is in the x direction and the y direction based on the angle. So x, our distance in the x direction, is whatever the radius is, which in this case is 1, times cosine of the angle. This is known as the angle. We use the Greek letter theta for that. Y is equal to the radius times the sine of the angle. And these are very commonly known, very commonly known values. They're lookup tables, they're in your phone, they're in every calculator, cosine and sine. Somebody had a question.
I can't really read that much. So are you just like not just using like regular algebraic math to explain all that?
Yep.
And
So-
you're not putting any like dot in between or anything like that for multiplication?
Well,
or
I can
anything
do
else?
I can do r dot cosine theta.
Right, because
Yeah.
the way you got it written there, it's like hard for me to see that.
Oh, okay. Yeah.
And you did say, in your defense, you did say like you didn't write real good on there.
Well, I mean, I can do that.
There you go. All right, now that's more better.
Okay. All right. So x is our cosine theta, y is our sine theta. So what this allows us to do is it allows us to essentially swing this angle around, starting at 0, all the way around to 360, and plot out what our values will be. And what we're going to find is that this makes a pretty common and familiar looking thing. So we're going to say this is our X. And this is our theta, which is our angle. And so what's the highest value of X that we're ever going to see?
1.
We're going to see 1. And what's the lowest value?
-1.
-1. Okay, and now we're going to do the same thing with our Y. We're going to draw the same looking thing. The highest we're going to possibly get is 1. The lowest we're going to get is -1. And now it is time to start moving our stuff around. So we're going to have really 4 important points when we're talking about angle. We're going to talk about 0 and 360. Actually, I guess it's 5 important points. 180, 90, and 270. And on the Y one, we're going to have 0 and 90 and 180 and 270 and 360. Now, important to note, what's the difference between 0 and 360?
Difference.
Yeah. What's
Nothing.
there's nothing. They're exactly the same. It refers to the exact same point. So that's why there's really 4 important points. But, you know, we're going to, for the sake of this graph, we're going to make 5. Okay, so now we're going to swing up to plus 90. So the question is, at plus 90 degrees, how high above the x-axis are we? In other words, what's our vertical displacement? How far up are we?
1 unit again.
1 unit, okay. And how far left or right of the origin are we? We are 0.
Mhm.
Okay, so now let's go over to the 180 degree mark. And let's evaluate where we are. How high up are we?
0.
We're at 0. And what's our left or right displacement? How far left or right?
Plus or minus 1.
That'd be -1. Yep, because we're all the way to the left.
Minus 1. Yeah, yeah.
All the way to the
Sorry.
left. Okay, and at 270, which is down at the bottom, we're going to be underground now, which is -1 on the Y. Oops. Down here. And we're going to be right on the vertical axis. So left and right, we're at 0. And now we're going to have at 360 degrees, which is the same as 0, our x-axis or our x displacement, which is left or right, we're going to be at +1. And our y, we're going to be right on the ground level. So time to connect the dots. Here we go.
Creating sine waves.
We just made sine waves. Okay, so what is a sine wave? How is a sine wave made? Does everybody recognize this picture?
Scott, you just kicked out the. Uh-huh.
Does everybody recognize this picture?
The part I can see of it.
Oh,
That's only because everybody else's pictures are over part of it. So
you
I
should.
guess that's, how do I turn that off?
I think you might be able to move that or minimize it.
Yeah, there's a little dash where the pictures are that you can minimize it.
Oh, found it. Yeah, it
Yay.
like disappears unless you move your mouse. There we go.
So this is a sine wave. The one on top is actually called a cosine wave.
Mhm.
Now, very important. What happens to the left if we keep going?
Repeats.
It repeats. Yeah.
Over and over.
Over and
again.
over. What happens to the right?
Repeats.
It repeats. So this is basically, we're just looking at a snapshot of this whole of something that goes on forever. If that circle keeps spinning over and over and over, the map goes on forever. Now, what's really kind of cool about this is, what do you notice about those pictures overall? They kind of look the same, right?
Mhm.
And
One's out of phase from the other one.
that's right. One of them is just shifted. So in order to make a sine wave, we can start with a cosine wave, and we can basically shift it 90 degrees to get the exact same picture. For the sake of argument, we really don't use cosine wave. We use sine waves just because somebody had to pick. So they're really just a shifted version of the exact same thing. So the one that
Do
we
we use-
use,
Sorry.
go
Do
ahead.
we use radians at all? Or just
Typically,
degrees?
no. I
Oh,
mean,
I hope not.
yeah. Well, there's two pi radians in 360 degrees. So a radian is about 57 degrees. But okay, so now that you brought it up,
Gee, thanks.
well, it's actually good to know because people are afraid of this kind of stuff. So what is a radian? All right, how many degrees are in a circle?
360.
Okay, and we have a radius. And what is the circumference of a circle? Does everybody remember this?
Mhm.
2 pi r.
Mhm.
So what a radian is merely the length of a radius if it were a curvy shape on the circle. That is 1 radian. And that is why there are 2 pi radians in a circle, which is 360 degrees. So we don't use radians here, but it's important to note that your calculator can do radians. In engineering, we sometimes do radians because.
Notice how your calculator gets like hotter when it does this.
It does, yeah. Okay, so now what we've done is we've created a sine wave. So now we're going to take this sine wave and we're going to draw this. There's our sine wave.
Yeah.
And it has a peak, whatever that happens to be, and a negative peak. And it goes from 0 degrees up to 90 degrees to 180 to 270 to 360. It's going to go through that whole cycle. All right, so now one thing I can do with this is I can take that sine wave and I can do something like this with it. What have I done? I've taken the sine wave and I've delayed it in angle by 90 degrees. Right? It's the exact same sine wave, but now it has a phase shift. The phase shift is measured in degrees or radians, depending on how you want to do it. I could also take it and I could do this with it. Everyone agree with that?
Makes it completely opposite.
Yep, I just multiplied the entire thing by -1. Now, interestingly, because if it's the same amplitude, that is actually the same thing as shifting at 180 degrees.
Correct.
Yep. So there's all kinds of cool stuff you can do with sine waves. Sine waves are great because they repeat over and over and over and over. Now, there's a couple of fundamental things about sine waves. What is one thing that I can say about this wave? I can ask for its phase, right? If it starts at 0 degrees, I'd say that it starts at 0 degrees. What is another fundamental thing I can say about this wave?
It's a function.
It is a function, yeah. How about something else?
It's repetitive.
It's repetitive. How about something else?
It's 2 times the distance for each side.
I can also say that it has an amplitude,
Right.
right? I can give it a size. I can make it an identical one, except smaller.
Frequency.
That's basically a sine wave, but with a different amplitude,
Mhm.
right? Which is its size. What can I also do?
It has a period.
It has a period. That's right. And what is a period?
Frequency.
Time.
Well, it's not frequency, but period.
One cycle. One
Yep.
complete cycle.
Period is known as T, which is time. The time needed to make one cycle. So that's its period. Now, interestingly, if we were to draw a circle, and let's say that this was a wheel, and I were lucky enough to be sitting on this merry-go-round, sitting right here, what would the period be? The time needed to do what?
Rotate all the way around once.
Go all the way around one time. That's a period. Okay, so now.
Oh, I see. It's 360.
Okay, so now another thing that I could say here is that if, let's say I had a period 1 second, how long would it take me to go all the way around?
1 second.
1 second. How about if I went and created a period of a half of a second? How long would it take me to go around?
1 second.
Well, half of
Yeah,
a
that's
second,
right.
right? Okay. In 1 second, how many times would I go around?
Twice.
Twice. That is the frequency of something happening. And frequency is measured in things per unit time. So that could be a trip to the zoo. That could be a trip to the bathroom. That could be a time going around this circle. It's just a thing that happens in a given unit time. And for the most part, we use seconds. However, it could also be, I have a birthday once per year. That's a frequency, right? It's a different time base. For the most part, however, we use per second. This per second thing has a name, known as a Hertz, named after Heinrich Hertz. So if I were to be on this merry-go-round, and the merry-go-round had a period of 1/2 of a second, my frequency would be 1 divided by the period. And if I do my units, that would be rotation per second. So 1 per second, I could replace that 1 per second with a Hertz, or in this case, sorry, it would be actually 2. My frequency would be 2 Hertz.
So
If
the
I were to-
frequency always anticipates a 360-degree travel time.
That's what it's based on, because it's based on circular motion of something. Now, it does not necessarily have to be that. I mean, I can draw a different shape wave. I can draw a wave that looks like this. Right? Anyone know what that's called?
Square wave.
That's a square wave. Okay. If I take that square wave and I have 1 square wave per second, what is my frequency?
It's 1.
It'd be 1 Hertz. That's right. It's 1 wave per second.
Mhm.
If I were to take this and instead say that my square wave had a period of 0.001 seconds, what would my frequency be? It'd be 1 divided by 0.001 seconds is 1,000 Hertz. I would have, if this continued on, I would have 1,000 of these every second. If I were unlucky enough to be sitting on this merry-go-round, and let's say that I was at NASA training headquarters down in Houston, and they put me on one of those big centrifuges, and it spun me around with a period of 0.001 seconds, just to see if my body could take it. What would the frequency be?
1,000.
Yeah.
1,000 Hertz, right? And the G forces would probably kill me, but it's, fortunately I can do this and erase the whole thing and the problem goes away. So, okay. So basically now what we've done is we've established that frequency and we haven't done wavelength yet, but frequency and period are related to sine waves, and sine waves are related to circles. So now what we're going to do is we're going to take our sine wave and we're going to add something else to it. We're going to say that well, let's say that we were to take this sine wave. And instead, now we're going to take this sine wave and we're going to basically add another dimension. So we're going to take this sine wave, and unfortunately, I can't do it on, I can't do it here, but you're going to have to picture it. We're going to have to take your screen and turn it so that you're looking at it end on. So you're looking at this sine wave as it's approaching you and going away from you. And you can't really see it approaching you or going away. But what do you see? You see
Single
something,
line.
a single line that goes up. And then what does it do? It goes down.
Mhm.
And it goes up and it goes down. It makes a straight line. Okay, so what we're going to say is now we've taken this sine wave and turned it sideways. And this represents the motion of something as it's traveling through space, right? We just know that it's following this basic periodic pattern. And we're going to add another dimension to it. We're going to add the dimension of velocity of this dot. So we're going to take this dot, which is moving in a circular motion that we're looking at edge on, but now we're going to take this dot and we're going to move it in this direction.
Just like it's traveling down the highway.
Just like it's traveling down a highway. Exactly. So what we're going to now see is that this is going to make because this actually is still moving up and down with a sinusoidal motion, except now what we're doing is we're taking that sinusoidal motion and we're stretching it out in the right direction, as it's moving toward the right. What we're going to see is now a new sine wave, which is still going to go like this, but as it goes up and down, how does that sine wave get stretched or compressed?
The speed?
The speed. Right? Because that thing, that little dot that's moving up and down now, has a velocity associated with it. Well, okay, so now we're going to go back to this and say that this thing going up and down right here has a frequency. What is frequency measured in?
Hertz.
Hertz, or a unit of 1 per second. That's per second, okay? But now we're going to look at this thing called a velocity. Well, we're going to move the particle over to the side, to the right. How do we measure velocity?
How much time?
Well, what per time?
Time and distance.
Distance per
Both.
time.
Yeah.
Distance per time. The most common MKS system, meters, kilograms, and seconds, thing to use is meters per second. That's how we measure a velocity. Well, what do you guys notice about hertz? What does hertz have a unit of in it?
It has second on the bottom.
It has seconds on the bottom. Yeah. Okay. And the velocity has seconds on the bottom. So this is something called dimensional analysis. Dimensional analysis allows us to make sure that we don't screw up our units. So if we were now to take our velocity, which is in distance, or we'll go with meters per second, and divide this by our frequency, which is actually in cycles per second, or one complete thing that it does, one complete cycle of the wave, well, we have this division. Now, I'm allowed to do this because math says I'm allowed to do this. So what I've just basically done is taken one unit and divided it by another one to see if I get something else that's useful. Well, what do I get? I now get this per second on the top and the bottom, so that cancels out. So now I get meters per cycle. And what is a cycle? That is a cycle. That is one full cycle.
Period. Yeah.
That is one full cycle of the thing. Well, if I now have a certain number of meters per cycle, what is that? That's a physical distance, right? That has a name.
Yep.
That is called our wavelength. This is a wave. It has a length, therefore it has a wavelength. So by merely dividing our velocity by our frequency, we get a wavelength. And this is kind of magic, because what we've done is just taken two units, which really aren't all that connected, and we've combined them together, and we've created this Greek letter lambda, that is our wavelength, is equal to a physical wavelength. So now if we have a sine wave with a particular frequency and a thing with a particular velocity, we have how much physical distance that wave covers. So what we're going to do now is we're going to say that we have sound waves. We're going to start with sound wave. And we have a wavelength, and we have a speed, and we have a frequency. Well, as it turns out, all these things cancel out. And so now let's say that we are talking about sound waves, 350 meters per second, roughly. And we have a frequency of 350 hertz. And no, I don't know what note that is. I know that an A is 660, a C is, I believe, or no, an A is 440, a C, I think, is 660, if I remember right. So what does this mean? This means that for a note of 350 hertz at 350 meters per second with sound waves, that means that our wave, which is traveling through the air, will have a distance of 1 meter. So where does this come into play? Anyone play a musical instrument?
Mhm.
Yep.
Anyone play a wind instrument? Anyone play a wind instrument? Clarinet, oboe, saxophone, flute? I play the flute. How do you tune a musical instrument to make the pitch lower? Not a guitar, because guitar strings are different. How do you make a musical instrument have a lower pitch?
Make
You
it bigger.
Yeah, extend it out.
Yep, you make the wavelength of the column of air that's vibrating a little bit longer. And to make it a higher pitch, you shrink the tube a little bit.
Mhm.
Believe it or not, we're getting to this. Antennas work the same way. So now we're going to move on to the next part, which is to say that we're no longer talking about sound waves. Sound waves are pressure waves. The velocity of sound waves varies a lot depending on the medium that it's in. So we're going to pick something that is a little less variable, a little more constant throughout the universe. And we're going to look at electromagnetic waves. Electromagnetics. Okay. So for this, we're going to have to draw 3 dimensions. We have everybody hold up your right hand. It can't be your left hand. It has to be your right hand. Okay, so electromagnetics. Well, we have electrical. Wiggle your thumb. And we have magnetic. That's your index finger. And now if you stretch them all out so they're all perpendicular to each other, this is called the right hand rule. you can make it so all three of those fingers are perpendicular to each other. This thumb, that's the electric field. Index finger is the magnetic field. And this, your middle finger, is the
We can't-
direction.
We can't see your hand. We
Okay,
see-
I'm going to shrink it down. There we go.
There
You
you
can
go.
make me huge. Okay. Your thumb is the electric field. Index finger is the magnetic field.
Mhm.
Your middle finger is the direction of movement of the wave. So if you have two things, really three things, an electric field and a magnetic field, the wave that's making them or carrying the energy is going to be moving in that direction. If you rotate them around, electric field, magnetic field, you know which way you're going to be going. So I can now draw this by saying that if I have an electric field, magnetic field, so we're going to draw I'm sorry, I'm using my fingers here. Electric field going up and down, magnetic field going this way, then I will have my energy moving that way. That's actually known as the pointing vector. So this is my electric field. This is my magnetic field. And notice these are all perpendicular to each other. And my electric field is going to be going in the shape of a sine wave like that. My magnetic field is going to actually look like this. They're going to be at right angles to each other. When the electric field is going up, the magnetic field is going to be going that way. When the electric field is going down, the magnetic field is going to change direction. These are always perpendicular to each other. And the direction of movement of the energy is to the right. If I were to reverse one of these, the energy movement would be to the left.
So the energy doesn't go out in a 360 direction, it goes in one direction.
Well, no, because the electric field and magnetic field are much more complex than that. If you could limit it to just these directions, then yes, the energy would basically be going in just one direction, but it never works that simply in real life.
Nothing does.
Nothing does. Okay, so now looking at this from this point, well, what are some fundamental things about these waves? They have amplitude, right? And they have period. And they have frequency. And as the thing is moving to the right, it also has velocity. The thing that's basically moving to the right has velocity. The energy is actually progressing in the direction to the right. So again, this is called an electromagnetic wave. It contains an electric component and a magnetic component, and they're actually related by the material that they're traveling through.
So they're also at the same time and speed.
Yep. They have no choice. If you want to go a little deeper into this, you can look up this guy, James Clerk Maxwell. He was the one, along with, I believe, Michael Faraday. They came up independently with the fact that this was actually how electromagnetic energy traveled through space. And for those of you like myself who have spent time in the electrical engineering world, you probably have heard of Maxwell's equations. Maxwell's equations basically there are four equations that essentially define everything about electromagnetics as we know it. It's very, very elegant solution to all this stuff, the movement of energy by electromagnetic radiation. Okay, so now that we have this, the most important one that we have is this thing called a velocity. And electromagnetic waves in free space travel at this mysterious speed called c. Anyone want to guess?
Speed of light.
Speed of light. And the reason that electromagnetic waves travel at the speed of light is a result of Maxwell's equations, or it was solved by Maxwell's equations. The other thing is to note that, well, what does any of this have to do with radio? What this has to do with radio is the fact that this right here, remember that thing that I mentioned, the electromagnetic spectrum? They're all the same. They're all exactly the same. Radio waves, microwaves, all infrared light, all the colors of the spectrum, ultraviolet, X-rays, cosmic rays, gamma rays. What is the only thing on this chart, and the hint is all the way to the left-hand side, that makes any of them different from any other ones?
It's the frequency.
Different wavelengths.
Frequency and wavelength. That is the only thing that differentiates a radio wave from ultraviolet, or an X-ray from a microwave.
Mhm.
The only thing that makes these different is the frequency and the wavelength. Now, it also turns out that the higher the frequency, the higher the energy, which will also come into play as we talk about this. Radio waves are actually very low energy and low frequency waves. X-rays, obviously very high energy waves, very, very high frequency. They penetrate your bones to the point where they can actually take photos of the inside of your body and stuff like that. And because they have such high energy, the way they interact with people, the way they interact with the atmosphere, the way they interact in space, they're very, very different. They behave very differently. But they're all fundamentally exactly the same. So now let us go back and take a look at our wave again, and let's figure something out. So we have our wave. It is now traveling at the speed c, approximately 3 × 10⁸ meters per second, or from the sun to the earth in about 8 minutes, or from earth to the moon in about 1.5 seconds, or one full trip around the earth 7 times per second. So it's about 140 milliseconds to have a signal go all the way around the earth and back to where it started. So now we can say that we have this wave and it's traveling at 3 × 10⁸ meters per second. And let's say we have a frequency of 1 megahertz. And we're going to get into units. 1 mega is 10 to the 6th power, is 10 times 10 times 10 times 10 times 10 times 10, also known as a million. 3 × 10⁸, we can do 300 million. That's a lot of zeros to keep track of, which is why we usually use scientific notation to get rid of all those extra zeros. So we could say, we remember that formula, wavelength is equal to velocity divided by frequency. We can now replace this. We can say that for radio waves, for electromagnetic waves, that speed is c, which is the speed of light, divided by the frequency. Well, we could say that in this case, it's 300 million divided by 1 million. And what's 300 million divided by a million? 300 meters. So from here to here, one wave would be 300 meters long. So to simplify this, we know that for the most part, we're not going to be dealing in hertz because those numbers are crazy. You know, we're dealing with much bigger numbers. So we basically take an implicit factor of 10 to the 6th, which is a million in there. So we have wavelength in meters is equal to 300 divided by the frequency in megahertz, because most of the time we're dealing in megahertz. And we can also rewrite this by multiplying both sides by frequency, and we get 300 is equal to lambda in meters times frequency in megahertz. The easy way to remember this is by drawing this circle. If you can't remember this because you don't like, you don't like writing down equations, you can always draw this circle. And you basically will say, okay, well, let's say I have measured a wavelength of 1 meter. So here's our sample question. We have a wavelength of 1 meter. Well, we know that that's right there. So our unknown is the frequency. So the question will be, what is the frequency of a wave that has a wavelength of 1 meter? Well, okay, we don't know this one, so we'll cross it out. We're left with 300, and look, there's a division line. So our frequency is equal to 300 divided by 1 is equal to 300 megahertz. Problem solved just by drawing that circle. So if you can't remember it, you're not particularly great with algebra, this is a really easy way to do it. All right, everybody ready for a 5-minute break?
Yep.
Mhm.
Any questions?
Yeah, I'm going
You
all the way
just-
back to high school math.
Yep.
I was just gonna say, you covered 3 years of engineering school there in about an hour and a half. Or 2
Well,
hours. Yeah,
no,
about an hour and a half.
I covered 3 years of EMAG
Okay, yeah.
and a little bit of complex variables and a little bit of trig.
Yeah, but most of us haven't even used that kind of math since high school.
That's right.
Right.
But it's important to know that it still governs most of the things that you actually use. So the whole point of this is to just get you used to the fact that this stuff is everywhere. And it can be boiled down to something that makes a lot of sense and is easy to use. But I believe that it's very important to understand the basis of something, because understanding where something comes from. I mean, I remember being in engineering school and they would give us a formula to use. The ARRL handbook is full of formulas for things. But what it doesn't really do, it doesn't go through derivation. And to me, the derivation is actually the most important thing rather than just knowing the formulas. There are sometimes if I'm at work or something and somebody says, figure out what the pressure drop is in this pipe. I'm not a mechanical engineer. I never took fluid dynamics. I don't know all the steps for calculating Reynolds number and figuring out what the pressure drop is. For that, I'll just plug stuff in. But for something that's important to me that I'm going to be using, it really helps for me to understand where the derivation came from.
I have a question.
Me too. And actually, your examples are great. I appreciate just even the illustrations like the merry-go-round and things like that. Is there any chance, and I don't know if you already addressed this, that we can get a replay of just the first hour and a half?
Well, I mean, I'm recording the whole thing. You can just.
How do we get a copy of that recording?
I'm going to put it on YouTube. I don't publish it, but I do put it out there. So in other words, it's out there. If I give you the link, you'll be able to see it.
Thank you.
I'm hoping that, because there's so much information here, I'm hoping that it is going to be kind of like learning a quadratic equation, that once you become familiar with the formula, it'll all fall into place. Because right now it's just a jumble.
Yeah, but you'll just know what to use. Like really what it comes down to with figuring out wavelength and how it relates to frequency is that one equation. All that was really for one equation. But what we've also done is, you know, where a sine wave actually comes from. And you understand what it means when, if somebody says that, you know, I'm 60, let's say that we're both sitting on that same merry-go-round and it's spinning at a certain rate and we're 60 degrees apart on the circle. Could you figure out how far behind you are? How, at what point in time, given a certain rotational speed?
Yeah. So if
how
the train
far-
to the station at blah, blah, when is it going to arrive at, you know, point A to point B, that kind of
right.
thing?
Or let's say that somebody, you know, your friend is on the merry-go-round and they pass over a frog that's sitting on the ground. When will you pass over that same frog?
Okay, so I
If
have
you're
to
60
solve
degrees
the
apart. Well,
Yeah.
you don't have to, but that's really where it comes from. And as you progress, you don't need to know that for the technician exam. You
Right.
don't really need to know that for most of anything. But what you'll find is that all of this stuff becomes applicable. If you have something that looks like this, which is let's say that this, we're going to be doing this a little bit later. So this is a dipole antenna. This is a simple antenna which has a wavelength at whatever frequency you pick of roughly 1/2 wave. Hey, guess what? What do we already know how to do? If we have a frequency, what can we figure out from the frequency, Carol?
How long to make the antenna?
We know how long the wave is. Well, if we know that the dipole has to be a 1/2 a wave long, we know how to make the wires.
So are you
We all-
saying we can determine how high we have to make the antenna go? Is that what you're saying?
No, you can determine how long you actually have to make these pieces. Because the total length of this antenna, and we're going to cover why sometime later today, we're going to cover why it has to be that way. If it's a 1/2 wavelength long, you know, because you know what the frequency was, and you know what the speed of light is, you know what the wavelength is, you know how long these pieces have to be.
You're giving me a lot of credit for knowledge I don't really have.
You'll understand it will all fall into place.
Hey,
Yeah.
Scott, is that length in meters?
Yeah, always meters.
Oh, them Germans.
3.3 feet. Just remember 3.3 feet. Okay, so now let's say that this is where we also get into interesting stuff. Let's say that we've represented an antenna by a dot. And the pattern antenna puts out energy in that pattern, right? So it's strongest in this direction and that direction. Well, if we have another one here, and we want this one to be the same way, but they're physically spaced a distance apart, how far do you make that distance? And how far ahead of one antenna does the other one have to be? And that's where one antenna might be receiving a signal like this, and the other one might have to receive a signal like this, so that they play together and they work together. And that would be known as phasing. And if you've ever seen an antenna that looks like this on a car, for instance, like this is an antenna, and then you might have this thing that looks like this, and then another piece of an antenna above it. Has anybody ever seen something that looks like that?
Yep.
Or one that looks like this?
Police
that-
vehicles.
Right? Well, that could be a loading coil. That could also be a section of a delay, which causes these two pieces of antenna to be separated by a certain distance, so that they are receiving the same energy, but delayed in phase, delayed in time with respect to each other, so that they additively work together. By understanding by understanding the concept of phase, by understanding the concept of frequency, that allows you to understand why those things work. And if you understand why those things work, you can actually use them.
Mhm.
Which is why I also say that that a lot of people that I teach here, if they've gone through the general class, for instance, the band edges and some of the nuances of the general class stuff, they basically can do the general exam also. Because, I typically don't dumb things down to the point where I just teach you what you need to know. I teach you the stuff behind it. And the stuff behind it doesn't have a license class. The stuff behind it is electronics and radio and electromagnetic theory. It doesn't matter what license class you're going for. Those don't change because that's all physics and math.
I have to take one license class before the other.
Yeah, the
So-
general first.
Yeah, I was told that you can generally sit for the general license if you pass the technician license at the same time.
Yep.
Are you giving us enough insight that we could take a stab at it without going through all the books?
What I would do, before doing that, if you look, because what ends up happening is now I'm going to bring up the band plan. Okay, so this is the band plan coming up. Okay, this is the band plan. In order to pass the general or any license class, any license exam, you basically have to know the band plan. You have to know your band edges. And that is really the rules of radio, the rules of the FCC are basically the same for any license class. The rules of electromagnetics and physics and electronics are the same. You're basically going to look at a little more in the way of electronic theory. There's more about vacuum tubes, like neutralizing an amplifier. And when you talk about the general class exam, you have access to all these frequencies, which means you need to know how you can use them and when you can use them and where you can use them. So that really is the difference, that when you get to the general exam, that forces you to have to actually study for it at least a little bit.
Okay.
What I found is that I've had people who, with no background, if they got to the point where they were killing the technician exam, they could get 50 to 60% on the general exam just like that, without even looking at it. To get over the edge, you really do need to, look at the specifics for the license class.
Okay, fair enough. Thank you.
But but the last class I did, I actually did it combined. I did an extra half day on the general, and a lot of the people who did that actually went through and passed both. And that's actually where all the fun is. The general class licenses opens up the high frequency bands, which are, a lot of fun.
Pat, are you planning to do a general test or a general class?
I do sometimes. I haven't since June. I guess the last one I did was that combined one. It's just that it just requires a little more time.
So what exactly can you do when you have a general license in addition to technician? What does that allow you to do that you can't do with just a technician?
Technician license gives you access to everything above. I might as well show the band plan again. Band plan. Okay, the technician license, any amateur radio license gives you access to 6 meters and up, which is 50 megahertz and up. You have very limited access to the high frequency bands, and this is where you get all your long distance propagation.
Oh, okay.
So all your worldwide stuff.
Okay.
When you get your, so you see this, if you look for that little hatched areas, like this one right here, come on, 28.5, that little blue hatched area, the green hatched area, same down here. Those are typically Morse code only. Up on the 10 meter band, you have a little bit of phone. When you get your general license, you have access to at least some portion of every single one of these bands. So it is a significant thing. because
Okay.
that's where you start to like, oh, yeah, I worked Antarctica today. Oh, that kind of thing.
With repeaters, can we talk internationally?
Yeah.
With a technician's license?
Yes.
Okay, that's what I thought. Okay.
If the repeater is an internet-based repeater, which many of
Oh.
them are now.
Okay.
So it'll basically be an RF system that's connected to, the internet, and somewhere on the other end, there's, another system that will pop up somewhere. And so you can have a bunch of people in England talking to a bunch of people here in Oregon. There's also digital communications, digital mobile radio and things like that, where and then you have something else called All-Star Echolink, where you basically can have a radio that connects to the internet, and then essentially the internet has a virtual repeater on it, and other people can be using that same internet-based repeater from anywhere else in the world. So it basically seems like you're using a local repeater, except that it's all tied together over the internet. So it's actually using that same voice over internet protocol that people use for telephones. There's a lot of hybridization that people have done because the technology's there. And, even if, let's say, the technology is such that your company decides they're going to modernize their phone system. Really, there's nothing wrong with the old phone system. They just want the newer and better one, right? Well, again, there's nothing wrong with the old one. And a lot of the ham bands are very, very, very close, if not overlapping with a lot of the Wi-Fi bands. So you can take your old Wi-Fi router, put new firmware in it, and it becomes a ham radio. And then instead of being limited to, part of basically the ISM protocol, which is part 15 or whatever it happens to be for Wi-Fi routers, which limits your power levels, limits your bandwidths, limits everything like that. Now it becomes a ham radio, and you're not limited to an antenna that's this long and 50 milliwatts. You want to put it through a 100-watt amplifier and hook it up to a 6-foot dish, you're allowed to do that. So, because
just a quick question.
Yeah.
So I was hearing by some people in my radio club that you could also get long distance communication with a technician license by using the ISS's repeater. Is that something that you could do as a technician?
Sure. I mean, it's a little spotty, If you're familiar with have you ever done an ISS pass?
Never, but I've seen
Okay.
videos.
Okay, I've actually contacted an astronaut and used the ISS repeater when it flies overhead. Number one, it's moving at 17,000 miles an hour with respect to the ground, right? There is no number two. It's moving at 17,000 miles an hour with respect to the ground, which means that from horizon to horizon is about 9 minutes. And on top of that, if you've ever heard of something called Doppler,
of course,
17,000 miles an hour is pretty freaking fast. And, we think of let's say a fire truck driving by, and you hear the pitch change because the fire truck is approaching and then driving away. 17,000 miles an hour approaching you, and then straight overhead where it's basically zero, and then moving away at 17,000 miles an hour actually stretches the radio frequency, and it causes you to have to retune your radio during approach, overhead, and as it's going away. So you have to alter your transmit and receive frequencies accordingly, so that by the time it gets there, they're on the right frequencies. And by the time their signal gets to you, you can understand it.
Seems to me an SDR radio would just do that.
Only if it's programmed to do so.
Right, but it could do that.
You could do that, yeah.
But only for 9 minutes. Regardless.
But only for 9 minutes. And the other thing is, when it's low on the horizon, it's 1,600 miles away. Yeah. Straight up, it's 200 miles away. And then when it's going away, it's 1,600 miles away. And because the ISS repeater is on FM, it can really handle one signal at a time. So let's say you take that ISS system and you stick it over Alaska. You don't have a whole lot of users, right? So no problem. But now you take that same ISS repeater and you put it over the central United States, and you have, you know, there are 770,000 hams in the United States, of which a small subset, but not zero, really enjoys looking for and using the ISS repeater. So now you have, let's say, 400 people trying to use one repeater for a period of 3 minutes. It works. It's challenging. You got to be really, really short. You're not going to sit and have a long chat with anybody. You're basically, your contact is going to be, in my case, like N7JI, Charlie November 84. And someone will say like N7GR, Charlie November 80, N7JI, N7GR, Charlie November 87. And I'll say, N7GR, thank you, good luck. Because everyone's trying to use it.
I think you have answered my question, but
Now,
it can be done.
It can be done. Well, now I will also say that there is a satellite called, I believe, QO, which was put up by the Qatari Amateur Radio Club. And it is actually the only geosynchronous ham radio satellite up there.
Oh, how cool.
Yeah, it's the only one. But unfortunately, the farthest west that it goes is the east coast of Brazil. It
So
covers
it's
the
basically
eastern
over
hemisphere.
Qatar.
It is, yeah. It covers the eastern hemisphere, unfortunately.
So isn't this where you get a whole bunch of people to get together and talk to Elon Musk about putting something up for us?
Yeah, there's no money in it.
Well, exactly, but he's not always about money. What did he do? Launch a Tesla towards Mars?
You know, he did. You know, part of it also is that it's really expensive. It's really cheap, relatively cheap, to put up a low Earth orbit satellite like a CubeSat. It's really expensive to put something in geosynchronous orbit. I mean, it's really expensive.
Yeah, it seems to me like everything would just bump into it. That's up
Well,
there.
no, they're all geosynchronous. So they're all at static locations, but there's just not that much room. And you got to get it 22,000 miles up as opposed to 200 miles up. It's a much bigger rocket, which means it costs a lot more. So who was working with this? Who was working with the space stuff at school?
That was me.
So have you started looking at doing CubeSats and things like that? Is that your focus?
I've heard about it. I'm actually part of the CanSat team. So right now we're trying to do everything with a payload to launch it and then have it fall and then take all those measurements. But that actually excited me because you said CubeSat and I wrote it down. I was like, I heard about that. So, but yes.
So at Portland State University, in up here in Portland, I should say. So much for my break.
Yeah, I was going to say, what happened to the 5-minute break?
This is just fun. So ORSAT. So
cool.
To give you some idea of how big a CubeSat is, it's about 4 by 4 by 4 inches. And so this is Oregon ORSAT 0. The guy who runs the group is Andrew Greenberg up in Portland. It's in the engineering building at Portland State. They also build liquid fueled rockets and cool stuff like that. But this was ORSAT 0, and they designed all the circuit boards, and they designed all the, they built all the ribbon cable to tie it all together. This right here on the, where is it? Yeah, battery card, the part that's not supposed to catch fire. That was their task. Don't catch fire. Up top, you notice those things that look like they're like held in by dental floss on the very top.
Yeah.
It's basically dental floss. That's the antenna system. And once it is deployed, basically picture this rocket carrying 50 of these little CubeSats. And they basically just open a door and let them fly. And once it's in space,
Wow.
go ahead. So once it's up in space, it just basically is released. They sort of have to orient themselves, figure out where they are. And those little wire looking things, which look a lot like dental floss, basically those are the things that hold the antenna. They fire up a small resistor. It heats those little pieces of string, and they go boing, and the antennas spring out.
So that's a one-shot thing, and if it doesn't work, the thing don't work.
That's right.
Oh.
Wow, that's impressive.
Cool stuff. All done by college students at Portland State. Okay, well, any other questions about the radio stuff before we get back to it? Okay, so the next thing we're gonna do is we're gonna cover electronics. So we're basically going back to like page, if I had to pick, I'd say page 4. Because we generated electromagnetic waves, or we were looking at electromagnetic waves, and now we have to figure out how to make them. Okay, so Ohm's law. Here we go. E equals I times R. E, I, R, like that. E is known as electromotive force. We measure it in volts. And that's measured in volts. We use a symbol V. I is current, and we measure that in amps or amperes. We use the letter A. R is resistance. We measure that in ohms, and we use the Greek letter omega. So that's it. That's all you have to remember. That is Ohm's law. Well, at least that's the first half of it. So if we have an equation that looks like this, E equals I times R, we're going to draw our first schematic. That's a battery. That's a resistor. And okay, so electromotive force is the ability of something to push electrons. And current is the flow of electrons. So if we were to look at then a resistance is something's ability to resist the flow of electrons. So if you think of it as water, if you have a reservoir up here, and then you have a stream bed draining into another pond, what happens is that depending on the size of the stream bed, that's your resistance. If it's a really, really narrow stream, maybe it doesn't have a whole lot of area to flow, so it has a high resistance to flow. The current is literally how much water is flowing through that creek, and the potential or electromotive force, how much push there is behind it, is the height differential. So if this were a very, very tall mountain, you'd have a lot of water, you'd have a lot of potential energy stored up in that reservoir, and you'd have a big push. That would, the analog to that is voltage. But that's basically what this is doing here. So what we have here is a battery. A battery is a way of storing chemical energy and being able to put it out as electrical energy. We have this wire that connects everything. The wire is made of a conductive material like copper. that connects all the components. And the resistor is usually carbon or something similar that has the ability to resist the flow of electrons. So what we're going to do is, just to make sure everybody's on the same page, we're going to draw an atom. Okay, what's at the center of an atom?
Electrons.
No, everything.
Nucleus,
Nucleus, which contains
protons and neutrons.
right. Protons
Yeah,
are a
them
positive.
bug.
Protons are a positive charge. Neutrons are a zero charge. To balance this out, flying around the nucleus in different orbitals, we have our electrons, and the number of electrons in a neutral atom has to match the number of protons so that it's electrically neutral. If we were to have oxygen, that would be 8 protons. Flying around the outside, that would be 8 electrons to match it. Now, it also turns out that if we were to have some other atom, let's say copper would have a nucleus that has 29 protons and 29 electrons flying around the outside.
Okay, I have it there.
So, okay, so importantly, what this means is that if you were to draw the electrons, they are not all at the same distance, and they are not all held as tightly by the nucleus. And in fact, for some of these atoms, there may be a stray electron or two that are in the very outer shell furthest away, right? Which receive the smallest pull by a long shot from the nucleus. Well, that means that that electron, because it's really not being held very tightly, it can kind of drift away if there's another one that comes in to replace it. You know, they let's say you have 2 of these atoms right next to each other. Well, one of them might just sort of like say, okay, I got a new electron. Well, that one can go. I don't really care. You know, it can also drift away very easily. This is actually known as a conductor. An atom that does not hold its electrons very tightly is usually a really good conductor. Most metals are really good conductors. That's kind of the definition of what a conductor is. But now let's take another one, and we will look at, let's say fluorine. Ooh, that's a good one. So it has 9 protons. It has 2 electrons right here and 7 electrons right here. This shell can contain up to 8, which means that all of those electrons are pretty close to the nucleus. It can have up to 8. And in fact, it likes to grab electrons from other places and hold them in place. So those electrons are very tightly held. That's a good example of something that would be an insulator. An insulator is a material that does not transfer electrons easily. So things that are good conductors: copper, gold, silver. Things that are good insulators: dry air, actually a really good insulator. Mica, rubber, paper, water, if it doesn't have any salt in it, is actually a pretty good insulator. Any questions before we go on?
I am trying to think in terms of pictures.
Mm-hmm.
So my brain is telling me, and maybe wrong, that the insulator is a good insulator because of how closely packed, how densely packed those protons and neurons or whatever are.
Well, the electrons.
Electrons.
Because remember, it all relates to movement of electrons. The definition of current is movement of electrons.
Yeah. So where I was headed with this was because they're so densely packed, there's not enough room for movement. You know, So it can't conduct, create friction, create energy because it can't move. Whereas
Well,
if it's,
keep going.
am I seeing this? So if it's loosely packed, then there's more bouncing, more movement. You can generate more energy. Am I visualizing it incorrectly?
Kinda, yeah. And I can, so what I'm gonna just erase this. So we really need to go and look at the periodic table, because it really does come down to how things are built. So if we look at things from an elemental level, let me go grab the periodic table. Okay, share the periodic table. Okay, so periodic table of the element, right? Who here hasn't seen this since high school? Okay, so the periodic table, the way that this is laid out is in groups. The stuff that's in the middle in blue, those are usually metals. Stuff to the right, it starts to separate between metals and non-metals into the yellow area. The stuff that's on the left, those are all metals as well in the red. Well, one characteristic of a metal, if we were to draw this, is that if we look at an atom, it has the nucleus, and then at a pretty great distance, you start to have the electrons. You have the one shell, the first shell, that has a maximum capacity of 2 electrons. Then you have the next shell, which is the second shell. That has a maximum capacity of 8 electrons. The next shell out is the third shell. That has a maximum capacity of 8 electrons. And then you have the fourth shell. That has a maximum capacity of 18 electrons, and so on and so forth. Well, the farther you are from the center, because the nucleus is what is essentially holding everything together, that has all the protons in it, it's pulling all the electrons. The electrons in those outer shells are held looser and looser and looser the further you go out. So let's say
you're losing centrifugal force, or you're losing force.
No, it's actually electrical force. I mean, if you think about it, you have pluses and minuses, and what holds them together? That's electricity. Pluses and positives and negatives attract. But the further the distance away you are, the weaker the pull.
Okay.
So now let's say that we have a really small atom. Right? Let's say we have a really small atom. Well, everything's held in there pretty tightly, right? Even if we have an atom that it could have up to 7, it could have up to 8, but it's actually 7 that we find in there. That means there's actually an empty space. And all those electrons that are there are held pretty tightly. But now let's make that atom bigger and bigger and bigger. And so what we find is that a big atom, let's make a 5th ring way out here. That can have up to 32. Well, now we're starting to get into the areas of like gold. And gold might have just a couple of electrons floating around way on the outside. So what can you say about those electrons that are floating around way on the outside? That all these inner shells are good. They're all full. And these guys are just floating around way to the outside. They're far, far away from the center. Right? I mean, those are really far away from the middle. And not only are they far away from the middle, but this last shell out here kind of acts as a shield to them. So not only are they far away from the middle, but they're kind of shielded, which means they could, given a little bit of a push, just sort of drift out and disappear. So if there was another gold atom right next to it that had the same thing happen, or somebody somewhere were to throw an extra electron in, well, still got a balance. Let's say we threw 2 electrons in, what's going to come out the other side? If it's got to be balanced, if there's another atom there, those electrons are going to flow into the next atom, and they're going to flow into the next atom. And it didn't take a lot of work for that to happen, because they're so loosely held anyway that it really doesn't matter. I mean, they're so far out there that it really doesn't matter to the atom that it happened. That is kind of like the essence of a conductor. Typically a big, and that's why gold is a really good conductor. That's why silver is a really good conductor. And that's why copper is a really good conductor, because they're big atoms and they have electrons that are really loosely held out there. I think you're right. Well, no, the third shell I think is 18, because 288 gives you 18, which is argon. So 28, I think it goes 288, 18, 32. All right, so that's basically a little bit of the chemistry behind what makes something a good conductor or a bad conductor. So that actually brings up a really interesting and important point. Now we're going to take something that has the nucleus, which has 14 in it. And so we have our 2, and we have our 8, and the next shell out there has 4. That shell can hold between 0 and 8. So 4 is right in the middle, right? This is known as a semiconductor. Anyone ever heard of that word?
Mm-hmm.
You're using it today. You're using it today. There are billions of them in your phone, billions of them in your computer. This is silicon. Silicon is at that magic spot where it has an atomic number of 14. And if you look at silicon, it is right on the cusp of being an insulator or a conductor. And by adding a little bit, let's say we throw a couple of extra electrons in there built into the material, it becomes a better conductor or a better insulator. If we throw a couple of extra pluses in there and take some electrons away, it works the other way. So that's actually the basis for transistors, for diodes, for all kinds of cool stuff, for everything that we use today.
Isn't that what they call doping?
That is called doping. Yep. Okay. And I know I saw a lot of people, I saw a lot of people saying that it was going a little over their heads, but you know, if anybody wants anything else about that, now's a good time, because you know, I know this is a ham radio class, but again, you know, it's important to understand why things are conductors and why things are insulators, because we're about to get into exactly what a circuit looks like made of conductors and insulators, and where our schematic diagrams come into play. So let's say that our voltage here, we have our E, which is our electromotive force, that's our push, and we have a resistance, which is 10 ohms. That is just a unit, and we would measure our current going around the circle. Now, by definition, in a battery, I want everyone to notice this. What is the positive terminal of a battery? Marked with a plus, right? Right. In a car battery, this is going to be marked with a plus, and this is going to be the red terminal. In a car battery, this is going to be the black terminal. A car battery has a voltage of about 12 volts nominally. It's really 13.8, and it's defined by the chemistry inside the battery. But what's important to note about this is, what is the charge on an electron? Are they pluses or minuses? What's an electron, everybody?
Negative.
A negative charge. So where do the electrons come out of the battery? They
From
come
the
out of
black
the
side.
from the black. The electrons actually come out this way. But we measure current from positive to minus, positive to negative. Wait, isn't that confusing?
Yes.
Yes. You know why that's confusing? Because if we go all the way back to 1850, we will find that nobody had discovered the electron yet. So they just knew they had a battery and they could make a meter to measure it. And they knew that when they hooked something up, they said, oh, okay, well, the current, I guess, flows out of the positive and it flows all the way back to the negative. Well, okay, we'll call this the positive, which is the way that, the way that this battery works. Well, it was only many years later that it was discovered that the actual carrier of energy was the electron, which had a negative charge. But because everybody had already learned that current, which is the flow of electrons, flows out of the positive and into the negative, the mistake was made and it was too late to go back. So that is why today, by convention, current comes out of the plus and back to the minus. If I draw a circuit that looks like this, and I have a battery here, and I have something that goes like this, and I have a capacitor over here, and I put a ground down here and an inductor over here. This is my plus and this is my minus, and I measure all my currents like that. Just because that's how it was done, and they made a mistake, but everybody knows it that way, and we can't go back and fix it. So this is the last time that I'll talk about that, but that's why we measure current going out of the plus and into the minus.
Oh, so we're perpetrating the lie.
Yep. But the problem is that the entire world knows it. So it's not really a lie, it's just a mistake. So our formula E equals I times R, you can do it like this, EIR in the circle. So we don't know our current because we know that our resistance is 10 ohms. We know that our voltage in this case is 10 volts. We don't know this. We have a division bar. I equals E over R is equal to 10 over 10 is equal to 1 amp. And we know what our current is. Our first application of Ohm's law. Now, the next thing we can do with Ohm's law is we can the next thing we do with Ohm's law is that we can take this same circuit, have a resistor that goes like this. Ohm's law also defines this thing called power. And that's measured in watts, named after the Scottish engineer and physicist James Watt. Now, the nice thing about power is that power is just a unit of energy consumed or generated per second. This is measured in joules. Energy is measured in joules. Seconds is just in seconds. And what's cool about power is that it doesn't matter what that power is. It can be, and it doesn't matter what the energy is. Energy is energy. It can be potential energy or kinetic energy, which is movement. It can be energy. It can be something stored as chemical energy. It can be the energy in light as it's being, sent from the sun to us. Energy is energy and power is power, which means we can take electrical energy and we can convert it into rotational energy of a motor. We can take rotational energy of a waterfall going through a water wheel, and we can turn a generator and make electrical energy out of it. So it works in multiple different directions. If we have a battery, we can take that energy, which is going through a water wheel, turning a generator, use it through a power supply, which generates AC to DC, which we'll get to, and charge up our battery. So then we're storing water energy, potential energy, and movement as chemical energy in a battery. So the only thing to note about energy, energy can neither be created nor destroyed. It only changes form. Unless, of course, you're talking about, Einstein's general relativity, E equals mc squared, in which energy is converted into matter and back and forth. But we're not going to get into that. So energy can neither be created nor destroyed. It just changes form. So given the fact that we assume that this is still true, what we're going to do is we're going to draw this circuit. We're going to have a 10-volt power supply and a 10-ohm resistor. And we're going to go through and calculate what the current is. And we're going to do E equals I times R. Again, we'll always come back to this, E, I, R. And R is 10, E is 10. We don't know our I is equal to 10 divided by 10 is equal to 1 amp. Okay, so now we can actually say that we know what our current is. It's 1 amp. So now that we have established that, we're going to use the second half of Ohm's law and say P is equal to I times E, which is current times volts. Draw it the same way, PIE. And we know that we can do the same thing. So we want to say, okay, how much power is being consumed by this resistor, which has a resistance of 10 ohms and a current of 1 amp? Well, you notice what doesn't show up in this equation? There's no resistance. Right? We could always do substitutions, or we could just say that because energy is neither created nor destroyed, it just changes shape, changes form. We could actually look and see how much power is being made by the battery. Because it doesn't change shape, it doesn't change form, the power consumed by the resistor has to be the same as the power made by the battery. But we can do that. I times E is equal to 1 amp times 10 volts is equal to 10 watts. So if the battery is making 10 watts, how much power must that resistor be consuming? 10 watts. Okay. But since energy can neither be created nor destroyed, is that resistor moving anywhere? I certainly hope not.
Getting
right?
hot.
Yeah, the resistor's not moving. Hopefully it's not making any sound. We're looking at sources of energy. Power in a resistor turns into heat. That is what a resistor does. A resistor converts energy into heat, converts electrical energy into heat. So now, what do we know about this resistor? How much power is being dissipated in the resistor? How many watts?
10 watts.
10 watts. Okay, so if this resistor has a rating of 10 ohms and 5 watts, what will happen to the resistor?
Burn up.
And what will be let out of it?
Heat.
Dare, what will be let out of it?
Smoke.
And what does smoke contain?
Fire.
Magic. Okay, so smoke is the magic component. Think of it like this. The magic component inside all electronics that makes them work. When something blows up because you heated it too much, you have let the smoke out and the component doesn't work anymore. So that's what we call letting the smoke out. Once the smoke is gone, the component doesn't work anymore.
That's why when you get a new thing and you plug it in, it's your smoke test.
Yep, that's called your smoke test. Exactly right. Just a little bit of technician and engineering lore. If you let the smoke out, the thing doesn't work anymore. Ergo, it must have been the smoke that made it work in the first place. Okay, so we are now on to, well, we already did sine waves. Now we're going to do an application of sine waves. Okay. So what we're going to draw is, I did not do that well. There we go. Okay. We're going to draw a graph of volts versus time. A car battery has a nominal voltage of how many volts?
12.
12 volts. And in actuality, that
13.
is a somewhat discharged car battery. A car battery is made of 6 cells, which are a combination of lead and H2SO4. Anyone know what that's called?
Sulfuric acid.
Sulfuric acid, that's right. So your car battery has a combination of lead and sulfuric acid in it. So if a battery is overcharged or discharged, what can happen is that you can outgas H2. Anyone know what that's called?
Helium?
Nope.
Sulfuric
Smaller.
acid,
No, H2 is hydrogen gas.
Yeah.
hydrogen. Okay, right.
Has
Yeah.
anyone ever had a car battery explode? I have not, thankfully. I know people who it's happened to. So what can happen is if a battery is charged too much or discharged too much, it can outgas and be surrounded by hydrogen gas, right? So what happens if hydrogen gas meets oxygen and a spark?
Lots of fire.
You get an explosion. And what is one of the major components in a car battery?
Acid.
Sulfuric acid. That's right. Which is why when you go to jumpstart a car, what do you never ever do?
Where's the
Grounded first.
That's right. Because if you do, you will generate a spark in proximity to the battery. That's why a lot of people, when they make the connection on the dead battery, will always go somewhere else, like the frame of the car, because you don't want that spark, if it's made, to be anywhere near the dead battery. Okay, so a little bit of safety there. So let's see. So now we're going to take our car battery. We're going to put it at 12 volts. So if we're running a mobile radio, for instance, how much voltage do you think, if it's designed to run in a car, it's designed for? What kind of voltage do you think it's designed for? Probably that same 12 volts. And in fact, most equipment today is designed for 12 volt operation. Now, if I were to look at this battery voltage, I would see that over time, the battery voltage would hopefully stay about 12 volts. Does this ever go negative? Does it ever change a whole lot? Does it ever go below 0?
Yeah.
It does not. This is called DC, or direct current. The battery voltage always stays in the positive direction. Now, I could also make it so that it was a negative 12 volt system where it looked like this, and if it never changed. Anyone know where you find something like that?
And computer.
This would be called a positive ground car. Some cars are wired positive ground, not for a long time, but some cars are wired positive ground. Need to make sure you don't hook it up back. Anyway, so we have a 12 volt system. This is DC. This is a DC system that is direct current. If I were to draw this battery, it would look like this, and it would be, let's say, 12 volts DC. So that would be a plus and a minus, and it would always go in the same direction. The current would always go in the same direction. But now, let's say that I were to take this battery and I could do a really cool trick, and periodically I could take this battery and do this with it, so that my wave went like this. I could flip the battery around so that my new picture of my voltage looked like that, where sometimes it was plus 12 and sometimes it was minus 12. Whenever it went to -12, my plus and minus arrows would be different. I would have to redraw the battery, right? Like this. And my plus would be here and my minus would be there. My current would then be flowing this way. My current would change direction. Anyone know what this is called?
Alternate
AC?
current.
AC, or alternating current. Now, I have drawn this picture as a really ugly AC waveform. I've drawn it as a square wave, but it's alternating current. Alternating current changes voltage from plus to minus. What do you also notice about this voltage? It does it a certain number of times every second, right? What's that known as?
Period.
A period, and it also has a frequency. The frequency is number of cycles per second. So if I were to take this and do it once per second, so that this was 1 second, I would have a frequency of 1 hertz. Now, the other thing I might want to do is I might want to clean up this waveform. And let's say that I had a piece of rotating equipment that went around in circles, around and around and around, that was running a motor backwards so that it was generating a voltage. What do you think the wave might look like in that case? The shape that it would make, because it came from a circular motion, might look something like that. What's that called?
Sine wave.
A sine wave. That is the basis of our power system. In the United States, we're not going to draw that 12 volts anymore. In the United States, our power system has a frequency of how many hertz?
120. No, that's the voltage.
60
60
cycles.
60 cycles per second, or 60 hertz. Now, it also has a voltage of 120 VAC. But now, here's where it gets a little tricky. Let's say that I were to go and take a meter and stick it in my wall. And I said, okay, well, what's my voltage? And it says 120 volts AC. But then I were to go and take an oscilloscope, which puts out a graph that looks just like that. And I were to take measurements of the voltage. What would I get for my peak, high and low? I'd get 170 volts and negative 170. Well, that doesn't make a lot of sense, does it? The reason that I get that is because there's a mathematical construct which is known as RMS. Okay, so we just covered what was Ohm's law for power. P is equal to I times E. All right, so somebody tell me what those components are again. What's P?
Power.
Okay, what is I?
Current.
And E?
Voltage.
Voltage. Okay, and the other one is E is equal to I times R. Agreed? So if I were to take this and rearrange it, I would have I is equal to E divided by R. And so if I could take this and substitute it right here, my new equation would be P is equal to E squared divided by R. What is E again?
Voltage.
Voltage. Okay. Well, if my waveform actually looks like this, how much power am I making right there where my voltage is 0?
0.
0. How about right here where the voltage is 0?
0.
And over here?
Same.
0 again. And if I were to go like a little bit above 0 and try to compare it to how much I was making way up at the top, I would find that I make a lot more power way up at the top than I do anywhere near the bottom. Well, so over one full cycle, my power that I make actually would look like this, because it's the voltage squared. It would look like this. Does that look consistent to you? Very, very not, right? It's basically two big spikes. So what we do is we say, okay, well, if I were to take a DC voltage and average it out, what would my voltage have to be? In other words, what would the equivalent voltage have to be to make as much power as the AC voltage? This is known as RMS. It's a time average of the power, which is why if you stick your oscilloscope on your wall voltage, you will see a voltage much higher than 120 volts AC. And it's actually a square root of 2. You want to know what's on the general exam? This is on the general exam. So it's important to note that there's something called RMS. Okay, so back to a good old United States power. We have 120 volts RMS AC at 60 hertz. How about if you go to Europe?
50 cycles.
Yep, 50 cycles. And it's 230 volts. So the flavor of the voltage is different depending on where you are in the world. Some places it's 100 volts, some places it's 220, some places it's 240. So the flavor of the voltage changes. In the United States, we deal with this right here. 120 volts, RMS, AC, 60 hertz. Okay, so for the sake of calculation, because the average power is already calculated in, whenever we do calculations, we're going to assume that RMS is implied. So we're going to now look at an AC circuit. And we're going to say this is 120 volts AC. The RMS is implied. Here's our resistor. Perfect circuit. Everything's happy. We're going to make this a 10 ohm resistor. Because it's actually RMS, we can use the same Ohm's law stuff. It still applies. E equals I times R. We'll draw the circle. EIR, like that. We don't know the current yet. We want to figure out the current. We want to solve for the stuff we don't know. This is 120 volts. This is 10. I is equal to 120 divided by 10, which is 12 amps. Okay, so now how much power? P equals I times E is equal to 12 times 120 is 1,440 watts. Okay, this has a name. What is this thing called? You find one in your house.
Heater.
Yep, that's a space heater. That could also be an electric resistance heater. If this is inside a tank of water, what does that become?
Yeah, hot water heater.
We got an electric hot water heater. Right. If this is inside a small box in your kitchen, what do we have?
Microwave.
Oven.
Not a microwave. That's an oven.
I know.
Yeah. We're getting to microwaves though. Okay, so basically this is a heater. Now we're going to add something to this circuit to say, okay, well, let's say that something weird happens to your circuit. All right, because if you were building an oven or a heater or something like that, and you had a power of 1,440 watts, what would you size this resistor for? How much power to keep it from frying? At least how much? At least 1,440 watts, right?
Yeah, probably 2,000.
Okay. Yeah, so let's go with like a 2,000 watt element. Okay. But now something weird happened. Okay. How much current do you have going through all this circuitry? How many amps? 12 amps. 12 amps. Okay. 12 amps. Well, if you are a reasonable person, what would you size your wire to be able to handle? How many amps? At least 12
15.
amps. At least 12 amps, right? Okay. So now what we're going to do is we're going to say that something went wrong because things go wrong all the time. So we're going to take this resistor and we're going to redraw these equations because something just went wrong. You had a partial short circuit in your heating element. Happens all the time. And instead of being 10 ohms, now it's 5 ohms.
Oops.
Oops. E is equal to I times R. I is equal to E divided by R is equal to 120 divided by 5 is 24 amps. Now you have 24 amps flowing through the circuit. Okay, so now 24 amps, P is equal to I times E is equal to 24 times 120 is 2,880 watts. Okay, your resistor was initially designed for 2,000 watts in the first place. So what's going to happen to the resistor?
Burn out.
You've already got a problem, right? The resistor is going to overheat. Okay, but now is the resistor going to overheat, or you're now pulling 24 amps through this piece of wire? Now, how did you design this piece of wire? How many amps should it be able to carry?
Well,
12 to 15 amps. Okay, so now all of a sudden, if you think about it, what is a wire? A wire is basically a tube that has current, electrons that flow through it. Unfortunately, wire is not perfect. Wire is made of physical things. Depending on whether it's aluminum or copper or gold, the resistivity of the wire determines, based on its size, how much resistance it has. Well, that's why it has a limited amount of current that can flow through it. The bigger the wire is, the easier it is to push stuff through it. The shorter the wire is, the easier it is to push stuff through it. So now you're pushing 24 amps through this wire that's really only rated for 12 to 15 amps. So what's going to happen to the power in this wire? Because you have a resistance in the wire. P is equal to I times E is equal to I squared R. It turns out it's 24 squared times R instead of 12 squared times R, which is what you had initially. So you basically have 4 times the amount of power being converted into something inside that wire. So what is that extra power in the wire being converted into?
Heat.
And what will happen to your wire?
Burns up.
What if the wire is inside your wall?
Starts a fire.
This
Burns-
actually happened to us
Did it?
Yep.
Yeah.
Ooh.
in January of this year.
What
Yep.
what was it that did it?
A PGE line coming into our house had an open neutral.
Oops.
So you had extra current flowing through something it shouldn't have been flowing through.
240.
Yeah.
So
So
And we had a
the
fire.
voltage.
yeah, so that was extra voltage, which caused extra current.
Yes.
Yeah.
Yeah, all of our lights and everything was acting really weird. You turn on the microwave or try to turn on the toaster oven and the light would dim. It was
Oh, yeah.
very weird, and it was a smoldering fire, and the firefighters couldn't find it. We finally found it and put it out.
So, wow. Well, I'm glad everybody was okay. To cause a,
We were lucky.
cause a lot of damage,
Oh, yeah.
Yeah,
a lot of smoke damage.
Oh, yeah.
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 Over, let's see, I think just the cleanup effort cost over $50,000.
Oh, yeah. Okay, so you basically just, okay, so there you go. Real world application of Ohm's law, unfortunately. I'm sorry about that. So what ends up happening in this case is now, which is going to burn out first? Is it this resistor or is it the wire? And do you want to take that risk? Do you want to take the chance? And the answer is no, you definitely don't want to take that chance. So what we do to prevent these things from happening is we add another element in this circuit, which is basically something that looks like this. That is called a fuse. A fuse is a piece of wire that has been calibrated such that if it carries more than a certain amount of current over a certain amount of time, it will get hot and intentionally burn up. This could also be a circuit breaker. But basically, those devices are overload protective elements that are designed to be sacrificial in case something goes wrong. Okay. Okay, so Ohm's law, I think we killed Ohm's law. If anyone's curious, we're on page 11 of the book now.
Hey, Scott, have you ever heard of, I don't know if you can see this.
Where do you get the book of pages?
Oh,
If you apparently if you download the version that they came out with off the website, it has pages on it. It looks like this right here. We're on series and parallel circuits. So we're now doing series and parallel. And Howard, what was that question?
I'm just going to tell you real quick. My insurance company gave this to me
Okay.
for free. It's a subscription device, but they pay for it. It's called, the manufacturer's called Ting, and it's used to be an early detection for fire safety and wiring. I don't know how well it works, but
I've not heard of that. Now I'm going to have to look it up. Not right now.
Ting, and this is the box that comes in.
The future of fire safety. Okay, cool.
Yeah.
Really?
Again, I haven't plugged it in yet, but
Who's your insurance company?
State Farm.
Damn.
Yeah, they gave it to me. They paid for the first 2 years, and then if you want to go beyond that, you pay. And I'm not giving them a commercial. I'm just saying by coincidence.
Yeah.
I just got this thing, so we'll see.
And it's quite possible it looks for open neutrals and things like that. Because
Exactly.
if you have an open neutral, then the voltage is going to go somewhere. Yeah, well,
I could have sold it to you guys, right?
Well,
Thanks, Howard. We're definitely gonna look into that.
Yeah, you should. You should. Seriously, you definitely should.
And I work in a lot of sawmills, and a big part of what they do is they have, like a high resistance or floating ground.
Yeah.
Or floating delta above a ground. Sometimes they'll be hardwired, sometimes there'll be a Y, sometimes there'll be a high resistance delta, sometimes there'll be a corner grounded delta, and they're all different.
That stuff boggles the mind.
Well, I mean, it all comes down to triangle. Everything's in the shape of a triangle. If you want to see what three-phase power looks like, this is three-phase power. A, B, C. And if you distill it down to this, it's not so bad. And what's really important is determining in your A, B, C phase, here's the center point, and you draw a circle, and you say, this is my 0 angle, this is my 120 angle, this is my 240 angle. All the things are out of phase with each other by 120 degrees. And if you were to draw that, that's not a triangle anymore, is it? Well, yes, it actually still is, but it has a different name.
Circle.
That's a Y. Because it's in the shape of a Y.
Oh.
And then you can take this, and this becomes your neutral. And if you were to do this, that becomes your ground. Now, the interesting thing about this, if I undraw this, and now I have a delta, because a delta is a triangle, this has a new name. That's a delta. Where's ground?
Whichever one you pick.
Or none. I can have 0 volts being over here, where if I then draw circles, I have a circle that goes around this one, and a circle that goes around this one, but a circle that goes around this one. With respect to each other, they're all the same, right? They're all let's say 480 volts with respect to each other. But if I have a ground that's somewhere else, these circles are different sizes. which is why if you have a system like that, or like you have a ground that's tied to one phase like that, then these are actually at the same voltage. And then the circle for this one is 0 size, and this one looks like that, and this one looks like that. They're all at different voltages with respect to ground. So power is, power is incredibly important. And it's important to know if you have power coming into your house, for instance, essentially what flavor it is. Because there are lots of different flavors in the world. I'm building a system right now that has an isolated ground system. So it has phase A, B, and C, and it looks like this. So here's all your devices, and here's ground. So there's no connection to ground other than and ground, by the way, is your 0 volts. That's your reference to Earth.
You're just grounding it to keep it safe so that like if something happens, that's it.
That's right. And this is in South America that I'm doing this. And what's interesting about this system is that I have a system here. So here's my delta A, B, and C phase. And these are 400 volts. And I have heaters that are 220 volts. And I have multiple heaters that go like this that are tied to A, B, and C phases. And all of them are tied to a common, but they're 220 volts, which means that those need to be tied to ground. Well, where do I get ground if ground didn't exist? So I actually have to use a transformer that converts this to this, where I now have a ground, and I connect this over here, and this is my new A, and this is my new B, and this is my new C.
Oh, that's cool. So the transformer is hooked up in the middle.
Yep. And actually this is called a delta to Y transformer, and it's 400 volts on both sides. But it changes the shape.
It's expensive too, isn't it?
It's about $3,000. Yeah. But it means I can run my machine. So
solar systems are kind of like that, except that like if you get the smaller Chinese inverters, they don't accept being grounded to the same ground as you ground all your other things to. You have to separate one.
That's not good.
I know, that's because they're Chinese.
They're cheap. Yeah. All right, here we go. We're going to do series and parallel. So here's our battery. And now we have R1 and R2. So we have 2 resistors. We have our voltage, which is our electromotive force. And what happens in this case is that the resistances, if you think about it, let's say that you're floating on an electron that has to go all the way around the circuit. That's why circuit is called circuit. It comes from circle. You go through the one, and then you have to go through the other one. So the total resistance that you experience is R1 plus R2. That's a series circuit. Now, one thing that's kind of not so great about series circuits is that this will function as a voltage divider. The size of the resistances that you have determines, if I were to measure a voltage here and measure a voltage here, that determines how much voltage is dropped across each of these devices. If I had, let's say, a 120 volts power supply over here, I'm going to replace it with AC just because it's plugged into the wall. I might see over here 70 volts and over here 50 volts. Those voltages would be divided based on the proportions of R1 and R2. If they were equal, I would see an equal split. But if they're not equal, I will see an unequal split. Now, we can actually use this to our advantage if we were to actually want 70 volts. This is known as a voltage divider. Now, we can do the other part of it, which is to take this circuit and do this with it. Say this is 120 volts. So this I'm going to draw as our ground. This is our 0 volts. So if I were to measure the voltage across resistor 1, I would find how many volts?
120. Oh,
If I were to take the voltage across resistor 2, how many volts would I find?
120.
This is how we wire our house, fortunately. Because that means that if I were to suddenly pull out the second light in our circuit, the house would not go completely dark.
It's not a Christmas tree.
It's not a Christmas tree light. So if I pulled out a light bulb, the whole house wouldn't go dark. What it also means is that if I pull out a light bulb, all the other ones don't suddenly get brighter or dimmer.
Right.
So this is known as parallel. All these things, if you want to draw them if you want to think of it this way, all these lines are parallel lines. Every device in a parallel circuit experiences essentially the same voltage. So what is divided in this case? Current. If I have an open circuit right here because I pulled out the light bulb, how much current will I get flowing through there?
Zero.
Zero. There's no current at all. So the currents through the devices are going to be proportional to the resistances. So as it turns out, it's a little more complex calculation to figure out what the total resistance is. If I have two resistors, R total is equal to R1, R2 divided by R1 plus R2. So R1 times R2 divided by R1 plus R2. If I have multiple, then the formula just gets a little bit bigger. So if I had these equal to each other, let's say I had two resistors, and these were both 5 ohms. Let's make it 50 ohms. And this was 50 ohms. What would my total be? 2,500 divided by 100 is 25. It would be exactly half. If I were to do 4 of these, it would actually be a quarter. And one of the benefits of being able to do this is if I want to make a circuit that has higher power handling capability, for instance, that if each of these resistors only can dissipate a smaller amount of power, but I can pick them to be a bigger value, my total resistance is 12.5 ohms, and I get the total power that all of them can dissipate. So if each resistor is good for 1 watt, then the total I get is 12.5 ohms at 4 watts. And people actually build 50 ohm dummy loads for radio frequency testing by doing this. You can use much smaller, cheaper components. Okay, let's see. I think we are on to, let's see, DC power. We did DC power. Okay, so we're into units. Units are really important because everybody loves the number 10, right? But what does the number 10 do for us? It just basically creates a 0. So what is the difference between, if I'm writing this, 0, 0, 0, 0, 0, 0, 0, 0, 0, 3, and 3? Well, this is, we're going to count decimal points. 1, 2, 3, 4, 5, 6, 7, 8, 9.
100 million.
We moved 10 places to the right. So it's 3 times 10 to the minus 10th power. By doing this, we have basically absorbed all those extra zeros that took up so much room. And they didn't really add anything to our accuracy. I mean, they just showed it's a placeholder. So 10 to the minus 10th power is 1/10 times 1/10, 10 times. So decimal points and, big numbers, we can do away with most of those, at least to the point where they're just placeholding. If I took, for instance, the speed of light, 300 million meters per second. Do I really need all those zeros? Well, 1, 2, 3, 5, 6, 7, 8. 3 times 10 to the 8th meters per second. And I just absorbed a whole bunch of extra stuff. Now, the next thing I can do by doing this is that I can take over some of those extra zeros. So if I have 3 times 10 to the 8th power, I can actually represent this as 3 times 10 to the 6th times 10 to the 2nd. When you have the same base, the exponents can add together. And by definition, I can replace 10 to the 6th by the big letter M, which means mega. And this is found on page 15 of the book. So the prefixes from big to small, you can go tera, giga, mega, kilo, and then units, and then little m for milli and micro and nano and pico. This is 10 to the 12th, 10 to the 9th, 10 to the 6th, 10 to the 3rd, 10 to the minus 3rd, 10 to the minus 6th, 10 to the minus 9th, 10 to the minus 12th. The book is the one from the zip file, yeah. You can also, it has page, the one that's online, which I need to start using. Apparently I had an older version. It's the same book, but it has page numbers. So I also have it on page 18. It's the 18th page of the PDF for whatever that's worth. So I can replace this 10 to the 6th portion with the big letter M, and I can say that if this is 3 times 10 to the 8th meters per second, I can say that this is 300 because I'm left with 3 and 10 squared mega meters per second. I can also do, let's say, 6.49 megahertz. Well, I can go the other way. I can say, okay, that we want to see exactly how big this is. We know that that big letter M is 10 to the 6th, which is a million. 6.49 times a million hertz. I can multiply it out. 6490000 hertz. I can multiply it out. If I want to convert this into kilohertz, for instance, kilo is 10 to the 3rd. So that's 6490 times 1,000 hertz. And 1,000 is 10 to the 3rd power. That's 6490 kilohertz. So I can do all kinds of cool stuff with units. And the nice thing about units is with prefixes is that they allow me to not worry so much about all those zeros. Now, why do we get to that point? Because we're going to get to the next components. And the next components, it is very, very unlikely to find something in the order of components of a certain size. So, okay, we know resistors, right? That could be 50 ohms. That could also be 50 K ohms. And what does the K stand for?
1,000.
1,000. Yep. It could also be 2.2 mega ohms. Right? That would be 2.2 million ohms. These are all very common resistor sizes that are used in different parts of circuitry.
Mhm.
Now, we might also have a resistor that looks like this. This is called a potentiometer. This might be a 0 to 100K ohm potentiometer. where it's an adjustable resistor with a knob on it. And it could be, depending on where the knob is, anywhere between 0 and 100,000 ohms. So, okay, so now we're going to talk about some other components which make electronics a lot more interesting. So we're going to write this word again. Okay, what is that word made of? Electro and magnetic. Agreed?
Yep.
Okay. We have two components. This is called a capacitor. This is called an inductor. This has the big letter C, the big letter L. Capacitor has a property called capacitance. An inductor has a property called inductance. This capacitor is measured in farads. Inductor is measured in henries. A farad is an enormous amount of capacitance. A henry is an enormous amount of inductance. We don't use those. We will very often use picofarads or microfarads. For henries, we will do millihenries or even microhenries. It is really important to note that we never really have like a 1 farad. A 1 farad capacitor is an enormous capacitor. You know, a 1 Henry choke is an enormous inductor. So that's why most of these things are measured in pico, micro, sometimes nano. So if we were to draw now a capacitor, we would see that a capacitor looks like this internally. It's two parallel plates that are separated by a distance that is filled with a non-conductive material. Air is a really good one. Could also be mica. It could be polyethylene. It could be any number of different things. Okay, so what do you know about two charges, a plus and a minus, if we were to hook this up to a battery? Opposites do what? Opposites attract, right? So what are those pluses and minuses trying to do?
Get together.
They're trying to get together. Well, if they can't physically jump off the plate, what are they trying to do? They're trying to take the plates and do what? Push them together. They're actually generating a force. They're actually generating a force. And at every point within that space, there's something called an electric field, which is a representation of how much they are how much effectively they are trying to push or pull themselves together. That, if we were to take this and disconnect this battery, does that go away?
Yeah.
No. If we take away the battery, those charges are still there. It stays charged. That's why a
yeah. After you've charged it, you're saying.
right. If we take that
okay.
battery away, that charge is still there. In other words, the capacitor still has a lot of energy stored in it, or a little energy, depending on what it is. So unless we give those charges a way to escape, which might be in the form of a resistor, they'll flow through that resistor. That might also be, in my case, when I was a kid, a pair of screwdrivers where I went like this and tapped the screwdrivers together. And what do you think happened?
Dischargeable spark.
I got a very, very bright blue flash, which actually was enough energy with a big capacitor to do what I later learned, which is something called arc welding.
Yeah.
And I destroyed two very nice screwdrivers doing that, but it no longer had a charge. Okay, so capacitors are actually used as energy storage devices. They store energy in an electric field. Man, here we go. They store energy in an electric field. Okay, an inductor stores energy in, what does everybody think? What kind of field? Magnetic field. Okay. So what we're going to draw first is a straight piece of wire. Straight piece of wire, and we're going to put a current going through it. Okay, everybody grab your right hand, stick your thumb out. Now roll your fingers around so your hand is pivoting around your thumb. A current flowing through a piece of wire generates a magnetic field around the wire. So it generates an energy field around the wire. Now, if the current continues, what will happen to the energy? It will continue flowing. If there happens to be another piece of wire that is in that magnetic field that's being made, if a current makes a magnetic field will make a current. This is why we try to shield wires that are carrying AC current, like microphone cables, from each other, because they will develop something called crosstalk because of the magnetic field that's made. Okay, so a capacitor makes an electric field energy storage, an inductor makes a magnetic field energy storage. So now let's say that we hook this up to a battery and it's DC and it looks like this. And we have a current flow and everybody is happy. But now let's say we suddenly do this and we take away the path and we cancel the current. What happens to the magnetic field? Does it suddenly go away? No, but the current did. But that energy is still floating around in space. Either it finds some way to dissipate or it finds some way to dissipate. So what ends up happening is that you end up developing a very, very large voltage across this inductor, where it will attempt to find a path for that energy to be dissipated as a current. This will generate a nice spark. If it is connected to some kind of electrical components, it might blow up your components too, like a transistor. This is why, again, if we're going to do something like this, we would include a new device, which we're going to add, which looks like this.
Where are you drawing that?
Yeah, we can't see it. It's off the screen.
Everything, I think everything you're drawing is like below the edge of what we can see.
Okay, here, I'll draw it up here. So here's our current. Whoop.
There we go.
There's our magnetic field. And so when we disconnect, the coil or the inductor makes a large voltage, which it tries to use to dissipate the energy that it's stored. Unless we give it a path to dissipate that energy, this is known as a diode, which is a one-way street. That gives it a path for current to flow through this. And I believe diodes are actually the next component that we're talking about. So, okay, so interestingly, a capacitor stores energy in an electric field, and an inductor stores energy in a magnetic field. And we're going to take lunch at about 8 minutes, if that's good with everybody.
Yep.
Okay. So now what we're going to do is we're going to draw this capacitor in space, and we're going to hook up a battery. Okay. So if I draw it like this, what's going to happen is that the pluses are going to flow to this plate, and the minuses are going to flow to this plate. And once it's fully charged, what's going to happen?
Stop flowing.
It's going to stop flowing. So if we were to measure the current, we would see that the current would initially be very high, but then it would go to zero. Well, because the capacitor is full, there's no more capacity, literally. But now we're going to take this capacitor and we're going to do this with it. We're going to switch the plus and the minus.
Oh, crap.
So the minuses are going to flow this way, the pluses are going to flow this way, and then eventually the minuses are the new pluses are going to flow and replace everything in the capacitor, and then the capacitor is going to charge up to a completely new thing where it's plus and plus and plus and plus and minus, 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 minus. Well, what's it called if we switch the voltage back and forth and back and forth? That has a name.
Alternating current.
Alternating current. That's right. That's called AC. So if we were to do that and we do it faster than the capacitor can completely charge up, we know that when the capacitor is totally charged up, our current is 0. But how about if we manage to stop it from happening and flip it around before the capacitor is totally charged up? We always see current flow, right? If I were to take this capacitor and make it disappear and put a wall here and say we have a mystery device right here. And all I know is that when I put AC into this mystery device behind the wall, I always get current flow. If I always get current flow, what is that mystery device?
Transistor. Well, it's a diode.
Nope. It doesn't even matter what the resist. It doesn't even matter what direction it's flowing. What is the mystery device? That is a short circuit. That's a short circuit. That's a piece of wire.
Oh, okay.
That's a magical piece of wire. If I were to take this and connect it to DC and the capacitor charged up, what would happen to that? What would that mystery device look like? It would charge up, and then how much current would flow? None. What is it called when you have no current flowing through something? What must be there?
Oh, it's an open circuit.
It's an open circuit.
Oh.
So for a capacitor, AC looks like a short circuit and DC looks like an open circuit. Well, an inductor kind of goes the opposite. If I have an inductor that's hooked up to DC, it's just a piece of wire, right? It's going to make a magnetic field. Everything's fine. So DC for an inductor basically looks like what?
And open.
Nope, that's a short.
Oh.
Right? It's just a piece of wire. This is an electromagnet. This is a DC electromagnet. If I were to take the same inductor and hook it up to AC and go like this, we just said that when you remove the voltage from an inductor and you try to cancel the current, it does not like that happening. It fights back. Well, if it fights back, it says, no, you know what? I'm not going to allow any current to flow. If something doesn't allow any current to flow, what does it look like? What is something that allows no current to flow?
Sure.
Yep. And we can actually say that this is an open circuit. In the extreme, what we get is that for AC and DC, capacitors and inductors act like open and short circuits. In between, they sort of have their properties change. But what's really important now is to note that what we're going to do is use this to our benefit. So let's say that we have AC going through here. We have our AC circuit, and we have something that looks like this. So we have our capacitor and an inductor and a resistor. We have AC. Well, the AC current makes it to this point. AC voltage makes it to this point. What happens right here? The AC has a choice. Well, what does an inductor look like for AC?
Open.
An open circuit. What does a capacitor look like for AC? A short circuit. The AC is going to flow this way. You're not going to get anything flowing over here. How about if we also have this voltage? I'm going to draw that in green. That's DC. And now we're going to redraw our circuit. When the DC makes it to that point, it's going to have a choice of which way to go. So when the DC voltage hits the capacitor, what's going to happen?
Charge capacitor.
Nope. Well, it's going to charge it. And then what?
Stop.
And that's it. Nothing.
Stop.
So
Yeah.
there's no DC flowing this down. And the DC then is going to see this wide open just piece of wire, which is a coil, just a piece of wire and a resistor. And your DC is going to flow that way. So now what if you have a voltage that is made up of question mark? And in it, it looks like this. So it has an AC, obviously AC looking thing to it, but it also has DC because it would normally be centered around 0. So it's shifted up. What will this magic circuit do?
It would become a filter, basically.
All your DC would go this way and your AC would go this way.
Right.
You have
If half the
separated.
current will go one way and half the current.
No,
will-
it's not half the current. It's not half the current. It would actually separate the two kinds of voltage.
Oh, yeah. Yeah.
It would actually separate the two kinds of voltage that are inside it. This has a name. This is the basis of something we call a power supply. And this right here acts as a filter for the power supply to keep any residual ripple or AC away from it, away from your sensitive electronic components. This is known as filtering. An essential part of this filtering is that we have to make this into this. That's a power supply. We take
So that's like
AC.
the Blue Eddy, like it's a Blue Eddy, you mean?
That
Camp?
is a DC power supply. You look at your cell phone, you look at your computer, you look at every single thing in your house that runs off of DC. If it plugs into the wall, it basically is doing this. Here we go. This is a transformer that takes 120 volts and makes it into, let's say, 12 volts AC. A transformer will have a turns ratio. It's basically a piece of iron that a coil is wrapped around. It has a number of turns. The number of turns, current makes a what kind of field? Everyone? Magnetic field. The magnetic field, because this is iron. Iron, everyone knows that that iron, steel, they make really good magnets. They constrain the magnetic field. We pass the magnetic field through a different number of turns of wire, and the ratio of the number of turns gives us a voltage ratio. This is known as a transformer. But we still have a sine wave. We have a sine wave. Okay, now we can take this and run this through a diode. A diode is a device that has a plus and a negative terminal. It's made of silicon usually. And it has a P portion and an N portion, which are split in half so that a diode becomes a one-way street. It will only allow current to flow in the direction of the arrow. What that means is for the waveform where the voltage is plus, the diode will go this way. For the other half, where it's minus, it will not. So coming out of the diode, what you now have is a waveform that looks like this. Does that ever go below 0? If it doesn't go below 0, that has a
No.
name. If it doesn't go below 0, that means it always goes in the same direction, which means that our AC on this side now got converted into DC. Magic. Absolute magic. Now we take this and we allow this capacitor to charge up when the voltage gets high. But what happens when the voltage coming in goes to zero? It builds up electrons, it builds up charge, and then it allows them to backflow, and it takes that waveform and does this with it. Smooths it out. If you have a bigger capacitor, maybe it does an even better job. Maybe it looks like that. And then you have a special kind of diode, which is a voltage reference diode called a Zener. And this basically says anything that is above a certain voltage, I'm just going to allow it to open up and flow backwards. And that's known as a Zener diode. And what that does is it says anything above this certain level, I'm just going to allow it to disappear and flow and be dissipated as power. So what do you get out? You get a nice, clean DC voltage with a little bit of ripple. This is the basis for, let me cancel that. Everybody have one of these? That's what's inside it. That is what makes up a USB charger. That's how they work. That's how we recharge everything in our house. That's how we build big power supplies. That's how we build little power supplies. Everybody ready for lunch?
Yeah.
Any questions before I go? Okay, is 20 minutes enough or you want half an hour?
Half an hour.
Half an hour, okay. So we'll go, you know, let's just go 1 o'clock our time. Right? Think about lots of questions and you know, come up with really cool stuff that's just a burning question. I like burning questions.
Thank
And
you.
even if you don't, it's okay. I hope everybody's mind isn't completely fried, but
So where do they make most of these semiconductors at?
Taiwan.
Taiwan and China?
Well, you know, actually Taiwan has the biggest foundries in the world.
Oh, do
But
they?
yeah, but actually like, you know, wafer fabs and stuff like that, Silicon Forest, the Portland area.
So
There's
when
a-
I used to live in Taiwan back in the 70s, they had no industry above making
know.
stuff out of beer cans and cardboard.
Yeah. Yeah. Taiwan, actually the largest, well, actually with regard to China and Taiwan, that's why everybody's so worried about Taiwan getting invaded by China, because they have the largest semiconductor fabs in the world. And they do a really good job of it. I mean,
They
there'll
make
be,
great fireworks too.
well, yeah, that's independent.
Right.
All right. Any other questions? Okay, see you at 1 o'clock.
So I guess we just keep these videos open.
Yeah, you can leave it open. Is anybody back yet?
Yep.
I bet you got questions.
Oh, I'm too mind boggled for questions. I wouldn't be able to word them.
Nah,
I was just thinking, you know what?
bring it on.
Thank God the test isn't immediately after your class.
Yeah.
Because I'm going to do, I mean, I was great at math in the 1970s.
Mhm.
So I've got a lot of, reading this and rereading it and working it in my mind to do before I can think about taking a test.
Okay. Well, I mean, you don't have to memorize everything. You don't have to know how to do everything. I mean, I know people who've said, look, you know what? I'm just going to assume I'm going to get all the math wrong.
Well, see, math was always my thing. I love math.
Right. But I mean, I actually have had people who said, I'm just going to assume I'm going to get all the math wrong.
Yeah. What I studied in college was accounting.
Okay.
I mean, and then what I did for a living was I worked mortgage lending, where I was an underwriter for loans, evaluated appraisals and such. I mean, math was my whole thing every single day. So I feel like I've got to conquer some of this math because, otherwise it's just, I'll feel like I have a broken brain.
Well, ask away, because part of it is math and part of it is conceptual.
Yeah. Well, and in my mind, because I also study a lot of sciences. So in my mind, I'm trying to convert this to things that I'm familiar with, like, the law of inertia and the energy expounded when molecules collide, but it doesn't seem to convert although you would think it would.
I mean, yes and no. It depends. I mean, electrical stuff is different.
Yeah.
It's
a world unto its own.
Well, it basically comes down to like a physical I won't even say physical chemistry. It all comes down to physics.
Mm-hmm.
But it's physics on a molecular level. So
yeah, I got the molecular thing down, but not the physics.
But feel free to ask anything.
Yeah, I'm still trying to put it into cause and effect, and there is some cause and effect in here. So that's what I'm going to try to home in on as I go back over this stuff, cause and effect. This happens because that happens, and this interfered with that, so that's why that happened. Like the resistors and the conductors, that's all cause and effect. So that much, if I can start there, then I think I can just add to that.
Well, I mean, at some point it comes down to just, it is because it is.
Yeah.
I mean, we could go, you could go down more and more and more levels into, the nuclear physics, but we're not going to do that. At some point, unless you're a physicist, there's no point to doing that.
Right.
It's just to say that, we're not going into the nuclear force. We're not going into the strong force and the weak force. We're going to stop at electromagnetics, which is, electric forces that attract protons and neutrons, or protons and electrons.
Okay. So I think I'll get it. I just have to pound it into my head a little bit.
And we're not going into why there's only 2 electrons in the first shell, and they're sp hybrid orbitals and spd hybrid orbitals, which, my daughter's going to be a senior in college, and she had to take Gen Chem, but Gen Chem now is very different than when I took it. So I basically, if she wanted me to help her, I said, okay, well, I'm going to have to go back and I'm going to have to learn the new Gen Chem.
Right.
So I did. I mean, I basically went through, hybridized orbitals, and she took organic chem. Like, okay, well, I never took organic chem, but I've always thought that it was interesting. So I'm going to learn organic chem to the point where I can help you a little.
You need an honorary degree along with her.
Well, I was the one who said at some point, I'm not going to be able to help you anymore.
But yet you accepted the challenge.
I tried. Yeah, I do like a good challenge. And part of it was that I always was interested in organic chemistry, but being in electrical engineering, I never needed to take it and I didn't have time to do it.
Yeah, see, that's how I feel about math. I've always been interested and intrigued by math. It's so logical to me typically, and I'm a logical thinker, but sometimes it doesn't really seem to be logical.
Well, okay, how about the stuff that's on the screen then? Which I just put there.
Well, I think that
because that's the next thing we're doing.
Something equals something, then you're solving for X basically. So that's logical.
Right. But the question is, why do I have up there what I have up there and how does it apply? You know, it's not the mechanics of doing the math. It's why are they there? Why is it there?
Yeah, I'm afraid my brain is stuck in the mechanics.
Yeah, well, look at what's there. All right. I mean, do you understand what a log is? A logarithm is logarithms and exponents.
Not really, no.
Okay. So basically you have a base to an exponent equals result. All right. So that could be 6 to the 6 to the second power. What's 6 to the second power?
No idea.
6 times 6.
Yeah.
36.
Wait. So you're saying you don't have a good grip on exponents?
Nope.
Okay, so we need to do that. So that's shorthand. It's shorthand notation. So if I say 10 to the third power is 10 times 10 times 10, it's
Okay.
just shorthand. If I say 6 to the fourth power, that's 6 times 6 times 6 times 6.
Yeah. See, this is all stuff I knew, but it was back in the 60s
Okay,
and 70s.
well, no, let's do it because this is important. 3 to the minus 1 is 1 over 3 by convention. Anything to the negative power is 1 divided by that. Right. Well, this is the fundamental key to understanding. Otherwise, you're lost when I do the logarithms.
Mm-hmm.
So if I say, what's 10 to the third power?
10 times 10 times 10.
Which is
1,000.
Which is 1,000.
Yeah, okay.
Yep. And that is also known as a kilo. Right. Okay.
I haven't bought any marijuana lately, but I'm going to take your word for it.
Well, what's 10 to the sixth power?
10 times 10 times 10 times 10 times 10, which my brain doesn't even want to go there.
1 plus 6 zeros. That's 1,000,000.
Oh, that makes it easy. 1 plus 6 zeros.
Yeah. Which is 1,000,000. That has a name of mega.
Yeah, I
So-
looked at that charts of the mega, all the tera, all that. I looked at all that, and that's pretty simple to remember. Well, if you memorize it.
Right. But to know that it's from scientific notation. Now, the question is, so that's an exponent, a base to an exponent is the result. Now, the question is, a logarithm is basically a reverse exponential. So the log, and we're going to say that the base is 10 of 1,000,000. So the question is now, what power does 10 have to be raised to get 1,000,000? And we already just did it.
10 zeros?
Well, no, this number in here, what power does 10 have to be raised to get that answer?
6.
That's 6.
Yes, yeah.
Because 10 to the 6th power is 1,000,000. So the logarithm of 1,000,000 is 6 base 10. I mean, that's the definition of a logarithmic function.
Okay.
So if I were to do this, and let me erase that and say, okay, what's 2 to the third power?
I'm making notes. I'm sorry. What was it again? I was writing down.
What's 2 to the third power?
27.
2 times 2 is 4 times 2 is 8.
Yep. So 2 to the third is 8. So what's the logarithm base 2 of 8? That means to what power does 2 have to be raised to get 8?
3.
That's it. It's just the reverse. So now, all right, we're starting again, by the way, now that we've done that. So now you notice what I've drawn here. Notice what I've drawn here. If 10 to the x is something, so we're doing logarithms and decimals. We're actually doing exponentials and logarithms and decimals. So if 10 to the x power is something, then that also means that the log base 10 of that something gives you the power that it was raised to. So again, if I have 10 to the third is 1,000, that means that the log base 10 of 1,000 is 3. This is gonna be really important. This is the basis for the stuff that we're doing right now. Because we have these things called gain and potentially loss. Loss is a negative. Gain is something positive. So it was determined that there had to be a convenient way of expressing a difference between two things that were relative to each other rather than absolute. Because I could say, what if I started at 1 and I went up to 10? What is the mathematical difference between 1 and 10?
9.
9. If I went from 10 to 100, what would that be?
99.
Well, it's 90.
Or 90, sorry.
Right? But the proportions are the same. So it was determined, okay, we need to be able to represent something compared to something else in a way that is not based on the numbers themselves. In other words, 1 to 10, that's a difference of 9. 10 to 90 is 10 to 100 is 90, which is a 10 times bigger jump, but relative to each other, they went up by a factor of 10. So it's not a difference like that. It's a proportion. So the question now is, how many times bigger is, if we go from 1 to 10, how many times bigger is that?
10 times.
10 times. How about from 10 to 100?
10 times.
10 times. That's good. We get the same answer. So in other words, it doesn't matter where we start. It matters where we end and where we start. It's a relative thing. So that's to be able to compare two things together. So by definition, gain or loss is a comparison of the end point. We'll call that the after point. That's the end point with respect to the before point. In other words, how much change was there? Proportionally. That is gain or loss. Well, so if I went from 1 to 10, I could very simply divide 10 by 1 and get a factor of what? 10 times. How about if I went from 1 up to a billion?
Then you're going to use one of those little words, so you don't have to do the 0.
Yeah, but no, I mean, I get 10 billion, I get a billion times, right?
Okay.
That's a lot of zeros. It's a lot of stuff to carry, especially if the things that you're comparing are really, really different in size. Like, let's say that you started off with this much power going down your antenna cable. And by the time you amplified it, you were at 0.001 watt. So what would your gain be? It would be 100, it would be a billion times. But okay, what's the difference between a billion and 900 million? Right? Who wants to, right, but who, well, it's not, it's
100 million.
It's 10 ninths. Who wants to carry that kind of detail? Right? Not really necessary. So it was determined that a logarithmic scale was an easy way to do this because it would kind of absorb all the tens. It would absorb all the factors of 10. So what we're going to do with this is that instead of just taking a division of the after versus the before time, what we're going to do is we're going to take the logarithm of that change. So we're going to erase this. I think everybody's got it.
Yeah, I can't see the very bottom.
Yeah, I'll get it. But well, I mean, it should be there, and I can't move it. It might be that it got cut off somewhere. Okay, so I wish I could just shift it.
Well, there's like a little thing in the bottom of my screen that has a bunch of different things where you turn the mic on and off.
Yeah,
and it
yeah.
just doesn't go away, but it's not that much of the screen.
Okay, so here we go. So gain is really is power at the end divided by power at the start. That's a change between two different things. So the power at the end versus compared to the power at the start, that's gain. Now, an easily expressed way of that an easy to express way of that is using logarithms. So we're going to take another way of gain in bells is equal to 10 log base 10 of p end divided by p start. Okay, and this is kind of just what we were doing. So let's say our end point was 1,000 and our start point was 1. So Carol,
Yes.
what's our plain old gain? End divided by start.
What's our gain?
Yeah,
So we're not
it's
for the
just-
different. We're not looking for
No,
the
we're looking for the gain, which is the division of one
1,000
by the other.
times.
1,000 times. Right. Okay. Now, what we're going to do is we're going to take the power at the end divided by the power at the start. But now we're going to take the logarithm of it. So it's log base 10 of 1,000. So that means how many times, to what power does 10 have to be raised to get 1,000?
10 to
No, 10 to the what power is 1,000?
12? 12? I can't remember.
10. How do you
Three.
get to 1,000? 10 times 10 times 10. 3 of them.
The third power, yeah.
So the gain in bells, the name for Alexander Graham Bell, is 3 bells. But it turned out that a bell was actually a pretty big number. You know, a bell was a lot of stuff. So we did this thing called a decibel, and we multiplied it by, we added a factor of 10. So it's 10 times log base 10 of p end over p start. So it's 10 times log base 10 of 1,000. And what did we just say log base 10 of 1,000 is, Carol?
Third power.
That's 3. 10 times 3 is 30 decibels. So that's 30 dB. Whoops. Oh, that's really.
So you created the bells to decibels.
Yep. We just
I mean, yeah,
converted them by multiplying by 10.
Okay.
So the decibel is used everywhere. Things where, okay, places where, there we go. Places where decibels are found. Let's hear some. You might even know.
Measuring sound.
Measuring sound. That's right. Any musicians? Measuring noise. Anywhere else? Anyone ever work on a mixing board for recording?
I know the old tape machines and the sound recorders have
VU meters.
decibel meters.
They have
Yeah.
VU meters.
Yeah,
Yep.
and they measure
So those numbers are all measured in decibels. But here's another question. Let's say that I have an amplifier where it has an input of 0.1 watts and it puts out 10 watts. This is a very common thing. What is my gain of my amplifier?
100.
That's right. No, it's not 100.
Yeah, it is.
Nope. 10 log base 10 of 10 divided by 0.1. So it's 10 log base 10 of 100. So what's the log of 100?
It's 2
times 10?
It's times 10. So it's 20?
20 dB. It's 100 times, which is 20 dB.
In other words, 2 zeros.
Yeah, exactly right. So let's do another one. I have, I start with a transmitter of 0.0001 watts.
Well,
go ahead.
I was just going to say, if you take the 0.1 watts and multiply that by 100, you get 10. I understand what you're doing in logarithmic expression, but it is still a gain of 100
Yes, it's a gain of
in
100.
decibels. Okay,
Right,
so we're in agreement. Okay.
Yeah, we express it in decibels. So let's say
Correct.
let's say we have a start point of 0.0001 watts, and we want to say how many dBm is that? dBm by definition is dB compared to a milliwatt. What's a milliwatt? Point 0.001. Okay, so 10 log. Told you my handwriting was atrocious. 10 log base 10 of 0.0001 divided by 0.001. So what is that number right there? What's 0.0001 divided by 0.001?
100.
It's it's what it should be a tenth,
Well, yeah.
right? So it's 10 log base 10 of 0.1. By convention, the log of a decimal is the log of 0.1 is -1. So it's 10 times -1 is -10 dBm. So basically it's -10 dB compared to a milliwatt. That's a measure that people use. dBm. It's for signal strength. Let's take a look at an antenna. Okay, so let's say we have an antenna that looks like this. It puts out an equal signal in all directions. This is known as an isotropic radiator. And we have another antenna that we want to test against this antenna, which is a virtual antenna. But this antenna looks like this. It's a Yagi directional antenna. It's a beam antenna. And it has a main lobe that looks like this. And this antenna has, whereas this one puts out 1 watt in all directions, this one puts out, let's say, 20 watts in the forward direction. It was measured as having 20 times the forward power in that one direction, basically eliminating all the other directions. It basically took the energy from all the other directions and pushed it forward. Okay, so how do we do that? What's the gain? 10 log base 10 of 20. Uh-oh. Well, this is actually not so hard. 10 log base 10 of 10 plus log base 10 of 2. They actually multiply together. And you add the logs together. So you can split 20 into 10 times 2.
Oh,
So
that way you keep it in the same base 10 notation.
Yep. Okay, and what's the log base 10 of 10? What power does 10 get raised to get 10?
1.
1. And this is about 0.3. So it's 10 times 1.3 is how many dB? 13 dB. That would be the gain of that antenna compared to the other antenna. These are used in every reference that you will see. If you ever go to buy anything antenna-wise, it will list an antenna gain, and it will give you either dB or dBi. dBi would be compared to an isotropic radiator. dBd would be compared to a dipole antenna. Those are the standards by which antennas are measured.
Do you need to match them or do you want higher dB?
Depends what you want to do. So let's say that I have a transmitter right here. Right, this is my radiator, and I put out energy like this, and it measures a reference energy of 1 watt in this direction. And I replace this with a dish antenna, which has a gain, which I've measured as a signal strength of 1,000 watts. but I've still put the same amount of energy in. It's just a lot more efficient in that one direction. If I wanted to have an omnidirectional antenna, I would not do this. If I wanted to point to somebody who was way over here, that would be a great idea, right? So there's two ways to achieve this. Well, 10 log base 10 of 1,000 divided by 1 is 30 dB. Okay, so I have two ways to do this. I can keep this original antenna and put it up to 1,000 watts, that little antenna, or I can take this other antenna and use 1 watt and put it through the antenna. Which would be easier?
Easier to do the 1,000 watts because it's hard to point to other ones.
Yeah, but I got to make 1,000 watts of power.
Yeah, that's true. That's true.
That's really expensive, depending on how you're doing it. Sometimes it might even be impossible, depending on the frequency you're on. So this is why we do gain. This is why we do loss. So let's take a look at this cable. Let's say we have a transmitter here and we transmit at 100 watts and we have a loss of 3 dB in the cable. How much power comes out the other end? So here are two rules of thumb. 10 times is equal to 10 dB. These are the only things you must remember. This is all that I remember after all these years. 2 times is equal to 3 dB. You can approximate everything with those two things. If I double, that's 3 dB. If I go up by a factor of 10, that's exactly 10. If I go and cut by a factor of 1/10, that's negative 10 dB. So it works both directions. If I cut in half, that is negative 3 dB. These are the only things you will ever need to remember to get really close. So if I have a loss of 3 dB, what does that 3 dB do? What does it do to my power? The answer is right here.
Cuts it in half.
Cuts it in half. So if I'm transmitting at 100 watts, how much comes out the other end?
50 watts.
50 watts. Where does the other 50 watts go?
The cable heats up.
Yep. That may be a problem. That may not be a problem. Depends on the size of the cable. Depends on where it is. It may be enough to damage the cable. That's why it's important to know all this stuff. Okay. Well, now that we've done gain and things like that, any questions on gain? 10 times is how many times? 10 times is how many dB, everyone?
10.
Okay. Twice is how many dB?
3.
There you go.
So why is it an odd number of dB with twice and an even number of dB
Because
with 10?
because 10 log base 10 of 2 is 0.3 times 10. And it's approximate. It's not exact.
Oh, okay.
But the log of 2 is about 0.3.
So, and it's a good rule of thumb, like you said, it's a good way to guesstimate something.
It will get you very, very close. Like, let's say that I have, I want to know what the approximate power is. If I put out 1 watt out of my transmitter and I have minus 5 dB here. This is the other good thing about decibels. I have a piece of cable and I have minus 3 dB here. And then I make it up to my antenna and my antenna has 7 dB, or let's say 6 dB of gain. Or heck, let's give it another number. Let's say it's got 11 dB. And I have another box up here, which has minus 1 dB. Okay, so what's cool? Add it all up. How many decibels of gain or loss do we have?
2 dB of gain.
Right, because I have minus 5, minus 3, minus 1, and plus 11. Add them up, I get plus, what did we say, plus 2?
Yeah.
Okay, well, plus 2 is not quite plus 3. Plus 3 dB would do what?
Half.
No, positive.
Oh, right.
That would be 2x.
Times.
So
Yeah.
2 dB, yeah, okay, maybe 1.5 times. Approximate. So I'd get about 1.5 watts equivalent out in this direction.
So you're relying on the gain of your antenna to make up for the shortfall of all the other crap in between.
Yep. Now, this works the other way too. So let's say that I've got a signal coming in that has a strength of minus 110 dBm. That would actually be 0.00000000000. Sorry, one too many O's. 0.1 watts. That's how many watts are coming down the antenna. That's why we don't bother to do that. That's why we say minus 110 dBm.
Gotcha.
So let's say that we have 11 dB of gain here. Right? So what's our level right there? Minus 99. We just had gain. Okay, how about after another -1? Minus 100. Minus another 3. Minus 103. And right here, another -5, so minus 108. So now we take a look at our receiver. What if our receiver has a sensitivity of minus 105 dBm? What are we going to hear?
Nothing.
Nothing. Exactly. You will hear nothing. So what can you do to remedy this situation?
Increase the gain.
Get a bigger antenna.
Get a bigger antenna. Yeah. What else could you do?
Turn down the game.
Amplifier.
Well, let me ask a question. Where would you, if you were to put a preamplifier, where would you put it?
At the antenna.
You'd put it right at the antenna because you can't amplify what isn't there. So if I added a preamp right here and I had a 5 decibel gain right there at the antenna and it was sensitive enough to hear minus 110, then instead of minus 108, I'd now be at minus 103, which is above the threshold. And all of a sudden my system goes from not working to working. That's why bigger antennas are a good thing. What's another way to do something best? So what's another way to improve this system?
Oh, better cable.
Better cable. Yeah. And notice I also had a 3 dB loss at this junction right here because I had, let's say, a lossy connector. What could I do? New connector. When you're building a system, decibels are the currency in which you work. Okay, batteries. So we're on what looks like page 23, just really quickly. Batteries, rechargeable batteries. Battery is a chemical storage means for electricity. So if you have a battery, basically when you discharge the battery, you're using the energy stored in chemical reactions to generate electricity. If it's a rechargeable battery, you can run it backwards by putting electricity, electrons back into it. You're reversing the chemical reaction. So rechargeable batteries, lithium ion, lithium iron phosphate. You have NiCads, nickel metal hydride, car batteries. That's a lead acid battery. Those are all rechargeable, which means that the chemical reaction works both ways. Non-rechargeable batteries, you've got carbon zinc. If you've ever seen like a little coin cell inside a watch, those are lithium, but they're lithium metal and they're not rechargeable, but they also last for 10 years. There's a lot of very high density energy storage. Okay, diodes. We covered diodes a little bit. What we're going to do just to make sure we cover diodes completely is that we have a diode. A diode is basically like a one-way street sign. You notice on your one-way street sign, you've got an arrow on that. The cathode is the negative terminal. You've got a plus and a minus. If you find a diode, it will be marked with a band on the cathode. So sometimes that might also be called a stripe, as they say in the book. Now, because diodes are not perfect, you remember that they only flow in one direction, not in this direction. A diode actually has a certain amount of voltage drop. So if I were to put 12 volts here, and this goes through a resistor to ground, I would only see, depending on what it is, if it's a silicon diode, I would only see 11.3 volts. If it were a germanium diode, I could see 11.7 volts. So that means that inside that diode, just by functioning, it drops 0.7 volts for silicon and 0.3 volts for germanium. Now, if you look at the periodic table, you will see that silicon and germanium, both of these are semiconductors. And germanium is actually in the next row below silicon in the periodic table. So it's a bigger atom. As we were talking about, you've got inside the diode, you've got P material and N material, and the current flows like that. You have a stripe on this end. The important thing to note is that intrinsic silicon is a semiconductor. It doesn't really conduct very well in either direction. But in the P material, you might put these things called holes. This is usually phosphorus or something like that. And there are other materials that you would put to put an excess of electrons in the N material to make it more electrically negative, positive and negative, P and N. And again, that process is called doping. You dope the intrinsic silicon to make it slightly more one way or the other way. And by doing that, you make it into a one-way street. And yes, diodes have existed since in the transistor form since 1947. They were invented at Bell Labs. Changed the world.
Yep.
There's a special kind of diode called an LED, a light emitting diode, which looks like this. So that when it turns on in the forward direction, it's positively biased. It emits light. That's a light emitting diode. Okay, so now we're on to what happens if you take two of these diodes and you put them back to back. So if I take two of these diodes, again, this is a diode, P, N, and I put two of them back to back, and it looks like this, and I make it into a stack, P, N, N, P. Well, the ends are really one layer. And you'll remember that the P goes like this. So I can go like this with my P. I can make it look like that. So this would be a stack of materials. I could also do it the other way. I could make it N, P, P, N. There's an N, there's a P. And it would look like this. There's my arrow going out. On my other one, I'd redraw it, and it would look like this. Any idea what these things are called?
Transistors.
These are called transistors. And what are transistors used for? This is, anybody tell me, what are transistors used for?
They can be switches or amplifiers.
They can be switches or amplifiers. They're used for everything. We use them everywhere for everything. Imagine if we had a switch. Now, this is a 3-terminal device, as it's called, because there are 3 terminals. Now, you can make this transistor about the size of that dot that I just put there at the bottom of the page. You can make it 100 times smaller than that. You could make it 1,000,000 times smaller than that. They still work. You can put 2 billion of them on a single chip. Now, it functions as a switch. What if I were to tell you that instead, this is like real size, I could make a device that looked like this? This is actual size. and use it for the same thing that a transistor is used for. Any idea what this is called?
Light switch?
A vacuum tube.
Vacuum tube, yes. Before there were transistors, when people were developing anything, they used vacuum tubes. This is how big a typical vacuum tube is. Now imagine if something the size of the head of a pin had to be replaced by something the size of a vacuum tube to do the same job. That's what we were dealing with. That's why transistors are so revolutionary, because they can be made really, really small. Okay, so what we're going to do now is draw our transistor. This is known as a bipolar junction transistor, or BJT. It has 3 terminals: base, collector, and emitter. And if we look at this particular one, which direction would you say that arrow is pointing? Toward the middle or away from the middle?
Away from the middle.
Yes, I would say it's not pointing in. It's pointing out. It's not pointing in. This is an NPN transistor, NPN. That's how you remember which way it is. If I were to flip this around and draw it like this, that would be a PNP transistor. They work essentially the same way, except that they work backwards to each other. Most transistors in the world today are NPN. The way that a transistor works is that if a small current is applied from the base to the emitter, such that if you look at it, you will see that this right here is actually just this. That is just a diode. If that diode becomes activated, notice that it's also connected to here. There is a separate path that goes like this, from the top to the bottom, from the collector to the emitter. You will get a proportional amount of current going from the collector to the emitter. It may be 200 times as big as the current going from the base to the emitter. So if I could put, let's say, 1 milliamp into here, I could get as much as 200 milliamps going through the big root, through the big chain. The benefit of this, of course, is that if I can alter this current linearly, so that if I get 0.5 milliamps, I will only get 100 milliamps. If I do 0.2 milliamps, I will get 40 milliamps. So what does that allow me to do? What do you notice about this waveform, for instance, which I'm changing? This is my current. This is what is coming out the other side.
You're amplifying.
It's an exact copy, hopefully, or very close, of the input waveform, which is very low current, and this is very high current.
Mm-hmm.
It's a big copy. That is known as amplification.
Mm-hmm.
That is one of the basic uses of a transistor. Now, at some point, you will put so much power, so much current into the base that what happens is the collector to emitter junction says, well, that's it. I'm maxed out. I can't do anymore. So that would basically look like this. I have this thing completely off, and then I suddenly turn it on, and then I turn it off, and I turn it on again. What will happen over here is no matter what happens over here, my waveform will look like this. And it doesn't matter how big or small it is coming in, it's maxed out. So what is that?
That's where you get the switch.
That's a switch. Transistor in saturation, which basically means it can't do anything else other than what you're asking it to. It's maxed out. It's functioning as a switch. just a plain old on-off switch, except that on this side, on the left-hand side, the current might be 20 milliamps. And depending on how you built it, on the right-hand side, this could be 10 amps. What's the benefit of that?
You can control a large device with small amount of current.
Yeah, you can control a big device with a small amount of current. This could be 10 amps. If it's at high voltage, that could be a big lighting circuit. On top of that, you can also, if you can do it fast, you can also turn this on and off very quickly, and this will turn on and off very quickly. So we might be able to change this input voltage so that it looks like this. And what we'll end up with is something on the output that looks like this. So if this is, let's say, a lighting circuit, what will happen on the output? It'll flicker, but it'll go super bright. But what'll happen the rest of the time?
Go dark.
It'll go dark. So what does it look like compared to, let's say, just this? If it's flickering faster than we can see.
Looks dimmer.
It looks dimmer. Yeah. Incredible stuff. Just through transistors. Okay. There's another type of transistor that we use, which actually is used more often even than bipolar junction transistors. Okay, this is known as a FET, or a field effect transistor. It has 3 terminals. They're the gate, the drain, and the source. And this is known as a field effect transistor. The reason that it's a field effect transistor is if we look at this transistor, what is this device right in here? That is a diode. A diode requires voltage and thus current to get it to work, to make the whole thing run. So now let's instead take a look at this field effect transistor. We're going to look at that same junction right there at the input. What does this thing look like right here, everyone?
Capacitor.
That looks like a capacitor, doesn't it? So if I put a big positive charge over here, what's going to get attracted to the other side?
Negative.
Negatives. If I change this and I take these away and maybe go the other direction and put negatives here, what's going to happen on the other side?
Go positive.
Go positive. Depending on how this is built, this channel either turns on or turns off and allows me to basically put a voltage over here to make a current flow through here. The benefit, of course, is that this is more efficient because I don't have to have any current flow on the input side. I just put a voltage there. And the input resistance of this device is very, very high. It's just a capacitor. Once it's charged up, it doesn't take any. So this is a much more efficient transistor. This is actually what's used, or some variant of this is what's used in most integrated circuits, most chips in basically everything now. All right, so we're going to get through this. We're going to draw a circuit. And here we go. This is a ground down here. Ground is our reference 0 volts. Okay, so we have a power supply like that. And what is the point of doing this? Well, if we put a voltage here, we'll call it volts in, this will turn on the transistor, which will open up this channel, which will allow this battery to run through there. This is a light. And what will happen to the light when we turn this voltage on?
It will light up.
It will light up. And if we turn the light off, if we take away the voltage,
It goes
the
off.
transistor turns off and the light turns off. This is an electronic circuit for switching. Okay, so we already drew a power supply, but I'm going to bring it up on the screen anyway. So right here is our power supply. Notice it plugs into the wall. Number 2 is a fuse, because anything you build should have a fuse in it. Number 3 is an on-off switch. Number 4, does everybody remember what that thing is called? Nope. What's big number 4?
The transformer.
Transformer, yes. And a transformer's job is to convert one voltage of AC into
DC.
nope, another voltage of AC. Because that power is coming in at 120 volts. And what is your typical computer power supply or your phone power supply? How many volts?
5 volts.
5 volts. So in order to make that, maybe you want 120 volts in to this transformer and 10 volts out. Because anything above that, you're going to be burning off anyway. So you might as well get close. So that transformer is a device that converts one AC voltage to a different AC voltage. Now, you'll also find these out on the light pole out in your street. That voltage, what voltage do you use at home? If you're a normal person.
110.
110. What is the voltage out on the power lines?
Michigan 13.2.
13,200 volts. So that transformer has roughly 110 to 1 turns ratio, so that you have 13,000 volts on the high side and only 110 volts on the low side. Really useful to be able to convert it. So what's the point of doing that? Why would you want to transmit energy at such a high voltage?
Smaller cable.
Because V equals I times R and P equals I times E. So if you can raise the voltage, you don't need as much current to transmit the power, which means, like you just said, you can use smaller cable. And because power companies aren't into wasting money, they want to use the smallest cables they can find, which means that if they can transmit energy, if they can transmit power at 600,000 volts instead of 100,000 volts, that is greatly advantageous. Okay, so next we have a diode. The function of a diode is to take the AC and rectify it, as it's called. Rectification is the act of taking AC and turning it into DC. The way that this works, this is a half-wave rectifier. The reason that it's called a half-wave rectifier is because it's taking this full waveform of AC, and what is it doing? When the diode sees positive voltage, it turns on. So we're going to make that green. When the diode sees negative voltage, what's it going to do?
Block.
It's going to block it. So we're going to make that red. So the output waveform basically is this blue line. It's rectifying it and making half of the wave. So that is a half wave rectifier. Now, the next step up from this is something called full wave rectification, which is actually not that hard to do. You would take AC and it goes like this. So here's your in, here's your out, and here's your load. Put a capacitor on it so that when this is plus, it follows a path that goes like this. We're going to follow the loop like this. It goes through here, back down through here, and it has to make it to the other side. So it goes like this. And then we're going to reverse it. We're going to put the plus down below, and it's going to go through this way, and then through here, and then it's going to find its return path that way. This is called a diode bridge, and this is known as a full wave bridge. And by doing that, our output waveform, because 2 of the diodes work half the time and the other 2 work the other half of the time, this waveform is converted into this waveform.
Do diodes always work the same way with negative and positive?
Yep.
Always the same?
Yep.
Blocking or letting through?
Unless, of course, they're Zener diodes. And a Zener diode is a special power supply diode. That could be like a 9-volt reference or a 5-volt reference. And that's known as a zener. And that's basically right on the output of a power supply. And its job is to basically limit the amount of voltage that gets out of the power supply. It has it's actually built to operate backwards, but we're not going to do that. You just need to, you don't need to know it exists, but it's good to know that it exists.
So for our purposes, it's always blocking the negative and letting the positive go through.
Yes.
Okay.
Okay, so now just looking at this drawing, number 6 is a big filter capacitor. The point of a filter capacitor is to charge up when the voltage goes high, and then some of that built up charge will then dissipate through the rest of the circuit when the charge goes low. 7 and 8, that's a light, just turns on when the power supply is on. And hey, look at that. We have a little current regulator, which is number 9. And what's number 10?
Zener diode.
That's a Zener diode. Look at that. It's in the output of the power supply. Okay. Now, here we go into the final insult. Everybody ready for the final insult? Okay, remember I said, and I'm going to draw this. This is, okay. So if we have a capacitor at DC is like an open circuit. For AC, it's like a short circuit. An inductor for DC is a short circuit, and for AC is an open circuit. Right? And if anybody wants to go over that again, we can. But basically, the capacitor isn't able to, it isn't even able to charge up if there's a frequency and the voltage is switching back and forth. It's never able to charge up. So let me ask a question. Doesn't it seem like the faster you go, the capacitor will be more and more and more shorted? Like it will really not come into play because you're switching it so fast that the capacitor can never charge up. But is it possible to find a point where when you slow down, flipping it back and forth, sometimes it might start to act a little weird? And the same with an inductor. You could speed up the AC so that it starts to become an open circuit instead of a short circuit, but it's not quite that, right? By changing the frequency, you're actually changing how it behaves. This actually has a name. This is called reactance. And reactance is, it plays into something called impedance. Okay, so remember there was something called resistance. What is resistance? What does it mean to resist?
To stop part of it from going through.
Right, to fight back. What does it
Right.
mean to impede?
Same
Kind of
thing.
means the same thing.
Yeah.
Okay, so resistance is the ability of an object to fight back against the flow of DC current. Impedance is the ability of something to fight back against the flow of AC current. For a resistor, what do you think they would be the same or different?
It would be the same.
They should be the same. That's right. In a resistor, it does not matter if it's AC or DC. A resistor is a linear object that just says, I'm going to resist the flow. If it turns backwards, who cares? Real time. But an inductor builds up a magnetic field. A capacitor builds up an electric field over time. So obviously they do change somehow with time and with frequency because they're not given as much time to react. So what happens with inductors and capacitors is that inductors and capacitors, in the extreme, this is how they behave. AC we'll call it infinity frequency. This is what happens. DC is 0 frequency. It's 0 hertz. That's what happens. However, in between, what we find is that between those extremes, for an inductor, the impedance or reactance of an inductor, it turns out that I'll draw this in a second. The ability of an inductor to behave based on frequency is actually this. And for a capacitor, okay, so, well, what's 2 pi? That's just a number, right? And it's somehow related to 360 degrees. Yeah, right? Okay, but it's just a number. It's 6.28. We're just going to leave it alone. What is C? C is capacitance. It's a function of how big the capacitor is and how it's built. What is L?
Inductance.
Inductance. That's a function of how big the wire is, how many times you coiled it around, what conductor size it is, and stuff like that. You know, how many loops it is. That determines the inductance. But what is the thing in there that is now added to it? In both of those formulas.
Build up, you said?
No, what's those? What are the things that are what is added to both those formulas that you don't expect to see?
Frequency?
Yeah.
Oh, I haven't followed that.
Frequency. The reactance. In other words, how these devices react to AC is dependent upon what?
How fast?
How fast the voltage is changing. They are
Yeah.
frequency dependent, which is kind of trippy, but really, really helpful. Very, very useful. Very, very useful feature to have. The reason that I say this is now I'm going to do a little bit of branching. And I'm going to digress slightly. And I'm going to draw that circle that we had again. So I'm going to, over in the right-hand side, I'm going to draw this circle. Okay. It's on the coordinate plane. And I'm going to draw a letter R and a letter X. Now, what do you notice about the two axes, R and X?
Perpendicular.
They are perpendicular to each other. Very good. Now, there is a property called impedance, which is the resistance of something to AC. It's how it reacts to AC. It's the letter Z. The formula for Z is R plus JX. The J just signifies that it is at 90 degrees to R. But this is actually really profound. What it means is that the resistance and the reactance, this is resistance, and this is reactance, are at right angles to each other. They are actually perpendicular. So if we have a device that has, we're going to do Z equals R plus JX, and we have a resistance of 3 ohms and a reactance of 4 ohms. I'll draw those 3 and 4. What is the length of the hypotenuse of that triangle? Does anyone recognize that triangle, Ellie?
5.
That's 5. Yeah. So if we were to measure it, we would find that 3 plus J4 is equal to 5. The magnitude would be 5. because they're part of a right triangle. What else do you notice about that? You could actually take a measurement of the angle between those two that it makes. So what this means is that not only does it make for some really weird math, because 3 + 4 is clearly not 5, right? But if they're at right angles to each other, it generates a right triangle, which has a hypotenuse. And in fact, because of that, you could say that the angle is not that, well, that's the magnitude of the angle, or the magnitude of that is 5 ohms. But it would also, you'd also have to say that it's tilted at an angle. And that is, what is it, about 50 degrees, 55 degrees, to place this particular line in the right spot. So where does this come into play? This comes into play in the fact that what is Ohm's law, everybody? Way back to Ohm's law.
E equals I times R.
E is equal to I times R. Well, in fact, that's true for most things, but for AC, what is R? What do we use instead of R?
Z.
We use Z. E equals I times Z. And so if we have a current that is 1 amp, and we have an impedance that is 5 with an angle of 55 degrees, that means that we have a voltage of 5 with an angle of 55 degrees. Okay, so now if we were to plot those on a curve or plot those on a circle, what that means is our current, if it were here, our voltage would be up here as they travel around the circle. And if we were to actually take these, and I'm going to erase this drawing, I'm sorry. If we were to take these waveforms and we have our current that looks like this, because it's a sine wave at that particular frequency, this is our current, and our V is equal to I angle, or 5 times I5 angle 55 degrees, what would happen is our voltage would be over here. In other words, what is this difference in angle called?
Phase shift.
That is a phase shift. That's right. So what happens is that we have actually managed to separate and split apart the voltage and the current. Now, here's the other tricky thing, that for a capacitor, 1 over 2 pi XC, or sorry, 2 pi FC. For an inductor, it's 2 pi FL. But now when we convert this to Z, it's actually negative. It flips. And this one, ZL, stays positive. Which means that if there's no resistance, I have ZL, and I have ZC, because they're in now opposite directions. So if I take two things and I make a capacitor and follow it with an inductor, and they add together, if I pick my component sizes exactly right, what could I do with those two things?
Cancel each other out.
And what's my total resistance?
0.
Nothing. That's right. But because it's frequency dependent, what happens is I get something that when I change frequency, the resistance looks like this, or the impedance looks like this. When I start at 0, it's really high. And when I get to a certain point, it goes down to 0 and comes back up. So that my impedance goes completely to 0 at one frequency. Just by picking the value of C and L for a given frequency. And the reason that I'm spending some time on this, even though the math might be a little bit much, is because this is a fundamental of all radio circuits. This is a fundamental of every kind of tuned circuit you can think of. This is a tuned circuit. And what is the point of doing this? The point of doing this is that if you have the real world has a bunch of frequencies floating around from DC, which is 0, up to infinity. What does this thing, which has 0 impedance right here, what does it allow us to do?
Only the frequency you want.
It's a filter. This allows us to filter out all the crap that we don't want. This is the same thing as blue blocker sunglasses. This is, this is the same thing as if I only want to see red light, I have a red filter that only passes red. If I only want to allow one frequency, let's say 146.7 megahertz, which is in the 2 meter band, I can build a filter that only allows that plus a small range of frequencies around it to go through and block everything else just by picking those values. So this is critical importance for anything that for any kind of transmitter, for any kind of receiver. Your cell phone would be completely useless without this. Your computer would be completely useless without them. This is how we build filters. This is how we pick filters so that we can actually build a power supply that works. Okay, let's see. Back to this. Okay, so now I'm going to show you this print right here. Everybody see that schematic okay?
Yep.
Okay, what do you see on that schematic? There's really only number 4 is an antenna.
Got 2 variable capacitors and a variable inductor.
Okay, so if I am looking to allow just a certain frequency through, what do those devices allow me to do?
Tune into the frequency.
You tune them to the frequency. This is a pre-selector or an antenna tuner. It allows you to match the impedance of whatever the antenna is to the impedance of what's on the other side. And when you have a good impedance match, remember, impedance is how something reacts to AC. When they're matched properly, you get power through because the resistance goes away. The impedance goes away, the resistance goes away, and you get maximum power through just at the frequency you've picked. This is a tunable circuit. And you might say, okay, what do we use this for? Well, what we use this for is we build something that looks like this. I will pull one up. Hopefully there's a photo of the inside. Here we go. Ready? Time to share. Can everybody see that picture right there?
Yep.
That is an antenna matching device that is used for tuning radio circuits. So what do you see in that photo? I hope it's big enough to see.
Looks like there's lots of coils.
Yep,
and
there's one
switches
big coil
and
Yeah.
capacitors.
and two variable capacitors. Those are attached to tuning knobs in the front, and they mesh more or less material with each other, front and back plates, and allow you to change the capacitance by changing how much of the material is in parallel with the rest of it. And that inductor, which is that big coil right in the center, it has 12 different wires attached to it, so you can short out pieces of it, so you can change your inductance. You keep the same diameter, but you change the length and the number of turns of coil.
So is that the MFJ tuner that's in the pictures?
That is the basis of every MFJ tuner. And most pi tuners, that's known as a pi tuner. And the reason it's called a pi, or no, sorry, that's a T tuner. The reason that's called a T is because the schematic looks like this, which is a letter T.
Right, so it's just like the schematic in your book.
Yep.
So
And yes,
what's the rotary switch for?
the rotary switch allows you to, well, it depends on which rotary switch you're talking about. So if I were to, let me share that page. There we go. You can see this, see the picture at the bottom?
Yeah.
Okay, so the rotary switch in the center is actually a 12 position rotary switch that has 12 detented positions that allow you to select different taps of the coil, which shorts out other pieces of the coil.
So that's what all those wires are coming off, going
Yep.
to the switch.
Yep, and the left and right rotary dials, those are connected to the shaft, which is connected to the upper part of each of those capacitors, which allows them to mesh more or less with each other. The more material is parallel because it's meshed, the higher the capacitance. And if you change the capacitance,
And you got the other coil too.
That's just a measurement coil, or the one at the bottom, that's a that's either a that's for either measurement or as a balun, as it's called, which is for changing an unbalanced line like coaxial cable through a transformer into balanced line like open wire feeder or ladder line, which is two parallel wires.
Like the 300 ohm TV cable?
Yep.
Oh, okay.
Exactly. Okay. Well, now that we've killed that, so let's see. Other components, a switch. Okay, so we're just going to cover this a little bit just because we have to. This is a switch. Right, that's just a plain old switch. If we were to take two of these and go like this and drive them off of a single operator. So this by itself at top, this is a single pole, single throw switch. Poles are the number of contacts that you have, or the number of circuits. The T is the number of throws. So if I were to have a circuit that looked like this, that would be a single pole double throw. In other words, it could go either up or down, but it's only one circuit, so it's single pole. If I were to take this whole circuit here at the bottom on the left, that would now be called a double pole single throw because it's circuit 1, circuit 2. So it's double pole. A relay is basically if I were to take this switch and the actuator, instead of it being a hand operator, like a plunger, if I were to replace the plunger with a plunger like this that was driven by an electromagnetic coil, that would be a relay. A whole bunch of things on one chip, that's called an integrated circuit. A device that displays a value on an electrical quantity as a value is a meter. What controls amount of voltage from a power supply, that's a regulator, voltage regulator. What are most voltage regulators made of? It looks like this.
Or Zener diode.
That's a Zener diode. Yep. Zener. Easy to remember because this whole thing right here looks kind of like a letter Z. So that's a Zener diode. A good reason to use shielded wire is that you have crosstalk. You don't want crosstalk. And now we are into radio waves. And I'll show you what the page looks like. And here's what the page looks like. It says radio wave characteristic. I have it on page number 35 of the book. And a lot of this stuff we've covered, but some of it we have not. And then we get into propagation. So how about a 5-minute break and then come back for radio waves and propagation and antennas and feed lines and stuff? Does that work?
Sounds good.
Okay. My bladder appreciates it. All right, we still got a couple minutes. Questions, comments?
Feel better now?
I do feel better now. Yes, thank you.
Yay. This class is pretty interesting, and it's like a lot of the stuff you touch on, I know I learned it somewhere before, but it's been like so long since I took a lot of these things. And
well, I like to think of teaching it as RF engineering light. You know, electrical engineering light, electrical engineering for non-engineers with a focus on RF. Hey, Howard.
Yeah, I'm here.
You said you were double E also?
Yes, sir.
Where'd you go?
I went to Brooklyn Polytech.
So did my dad.
Oh, I know him.
Do you? He got he went to CCNY for his bachelor's and Brooklyn Poly for his master's.
Yep. Interesting. But just like the gentleman said before, I haven't touched this stuff. Let's see, I'm 68. I haven't touched this stuff in almost 45 years.
Yeah.
I mean,
I do it all the time, but you know,
I haven't really touched this. I'm amazed I even remember what I remember.
You remember Maxwell's equations?
Of course. My father's name was Max, so he used to always tell me.
But do you remember related. Okay, so div dot del, oh god, del there's divs and dels. Del dot B is 0 because there are no magnetic monopoles. Del cross del cross H is mu E. There's a del dot E is no, del cross H is epsilon E. Or is it like mu over epsilon?
I don't remember
Remember?
to that detail, to be
Well,
honest.
remember there's a value of mu over epsilon, or epsilon over mu, which is it relates to the permittivity of free space and refractive index.
Oh, refractive index, that's another one. Wow.
Yeah, it's like, okay, when was the last time I heard that? In 1972.
Well, I use that in photography class, refractive
Right.
index. Yeah.
But actually refractive index, we're going to get to very shortly.
No.
Yeah. You know why? Because it governs RF wave propagation.
Oh, yeah, that's true.
And
but you've realized, and I know you know this, that some of this it's kind of a deep dive for some people.
Yep.
And I hope we don't wind up scaring people away from taking this test, because it's really, it's like if somebody were to say to you, gee, I want to ride a bike, you can go through the physics of air resistance and tubing and all that, or you can just say you get on the seat and you start pedaling with your feet.
Yep.
Well,
So and I realize there's a happy medium between those two, but
yeah,
some of this is really deep dive for
I
people who
know.
have never touched double E. They're like sitting there, I'm sure, going, what the heck's he talking about?
Yeah, but you know what? Here's my thought, right? I've taught a lot of kids. Kids, if they hear something, they will remember something.
Correct.
Adults, if they hear something, will remember something. Oh, I knew something about that.
Right.
And I don't, I actually had one person tell me this class was the biggest waste of time I've ever seen in my life.
Oh, no way.
Really? And I asked him why, and he said, I wanted you to teach me how to use a radio. I'm like, well, you can you can buy a radio and do that.
Yeah, you get them from China and probably break up the law.
But you know what I'm saying.
I do. I do.
It's a very, and I'm not faulting you. I'm just saying it's a very fine line.
Yep.
That these kind of classes have to walk, because you can get to a point where the deep dive becomes
too much,
counterproductive.
Yep.
Like going into the periodic table.
No, it's important. But the only reason I went there was because we.
I'm not faulting you for it.
No. But that's why normally I wouldn't have.
Yeah.
But somebody asked, and because if somebody asked, they can't be the only one who wants to know.
Well, they could be.
They might be. Yeah.
No, I think you're doing a great job. Don't get me wrong. I really do. But your audience is a very mixed level.
It always is.
Yeah. You
have like there's a lot of other mixed level participation though. Like every once in a while somebody chimes in, but that's it. I don't know if I hear everybody on my end as much as the instructor does.
Oh no, we hear what he does.
Yeah, we hear everybody.
Oh, okay. Yeah. So it doesn't seem like a lot of people have. It's only like 4 or 5 people I've noticed that even say anything.
Because the ones that don't have a background in this area, it's rather difficult to pick this up. I have a double E.
Yeah,
I'm not, again, that's not a criticism. We're just saying, it's an obvious observation.
All right. Well, I see a lot of black windows on the screen. I would like to hear I'd like to hear some comments as to whether or not people are keeping up, or, that's why I asked, is everybody good with this before we go forward,
Yay. Uh-oh.
I'm still here. I don't have a background in this, so I'm kind of struggling a little bit to keep up, but it's given me a good basis, I think, to start and know what I really don't know and what I really do know.
Yeah, I agree with that. This is way over my head, but I really appreciate what you have to share. It's really quite interesting.
And the thing is that I think once you start, have you started going through the book yet and start taking tests?
No, not at all. This is my first intro into
and
it.
That's why, when I send everything out ahead of time, I say it's a good idea if you start taking tests and start reading through the material so that it's not completely alien.
Yeah,
You know?
so I've skimmed over the like the study guide. I skimmed through that and whatnot. It's just, how life is.
Yeah.
So yeah, but kind of just threw myself to the sharks. But yeah, it's definitely really interesting and intriguing.
Okay, so I see Luke, who's got the last name of Maxwell, which means a lot to me. Ellie, Luke, our college students.
Hello, sorry, I had my mic on or mic off. I don't know if this is true or not, but my grandpa was saying that I was distantly related to the Maxwell, of which the Maxwell equations are from. So kind of interesting, but.
Well, I mean, are you keeping up okay?
Yeah, a little bit. Some of the schematic stuff is going over my head. I think I'll definitely have to do some independent study of the video again. Just
and a big part of it is going through the whole question pool.
And so it is a pool. It's available online.
Yeah. Well, and actually, that's one of the things that I included. I think if you have an iPhone, you can download the app to basically study the whole question pool, one section at a time.
I have a very non-technical neighbor who I love dearly as a friend, and trust me, she has no technical aptitude whatsoever. She set up index cards of all 450 questions.
Yep.
And just repeatedly went through them, and it was purely a memorization. And she actually scored very well on a test, to my amazement.
Sounds like
Sorry,
my wife. My wife, who has no real technical background,
Yeah.
she got a 94 on her test.
Yeah, there's nothing wrong with doing that. Say again?
The test only has 35 questions, so you never know what you're going to get.
Yeah, well, that's why you take all 450, because a
right,
lot
you
of
just-
them
You just study them all.
memorization. Yeah.
I want to
Sounds
borrow
like a lot.
that
It's really not
lady's
that many.
cards. Does that lady loan out her
You
cards?
You could.
I don't know, to be honest. She didn't lend them to me.
Yeah.
But I mean, they're easy to make.
I'm starting at it from a very, very basic, no knowledge level too. And a lot of it is over my head. However, I'm feeling like when I put all of it together with the manual that I downloaded and I rewatched the video, I think each time it's more and more is going to actually sink in.
Right.
So does everybody see this on their screen?
Yeah.
amstudy.org. Notice study mode, read questions. Here's all the questions.
Oh
with
my
answers.
gosh.
Nice.
What was that? hamstudy.org, O-R-G?
Yep.
Hamstudy, one word?
Yep.
Was it always an open question pool?
Yeah.
So
ever since the 70s.
That's
They
the
just-
link from your email, right?
That's part of it.
Yeah.
I mean, I like the app, but this works too. Notice you can do study mode. And,
They just changed the questions as of last month. Am I correct? in that?
not for the tech. The tech's been a year. The general changed a month ago.
Oh, I didn't know that. Okay.
Yeah. But yeah, you can sign up to take practice tests. You can go through the entire question pool. Every single one. In fact, just for fun, I'm studying for the Canadian exams. And
hope you get an A in them, eh?
well, you have
can
to
help them put out all their fires.
Yeah, well, you need to get HF privileges, you need to pass the basic with honors. As opposed to just, you have to get 80% on the basic exam. But I want to go for the basic and advanced so I can, do more stuff. Because somebody actually was asking me about, the Canadian exam. I'm like, I've operated in Canada dozens of times, but I've never considered taking the Canadian exam. I said, well, you should. And it's actually different. So.
Oh,
Oh, I see. They actually got a little date range when they actually changed the
Yes.
exam, and the general one is the one that just changed. The other ones are
Yep.
still old.
Yep.
yeah, so technicians till 2026.
Yep.
Not as old as the ones my dad had to take when he had all his, what did you call them? Vacuum tubes?
Yeah.
Yeah, actually, the first exams that I took, they were just basically they would like the examiners would write the questions on the board, and they'd make their own exams. This was before the question pools. They would just make their own questions up. They said, "Draw a Hartley oscillator." Like, oh shit! I was 15. You know, I mean, how else do you do that other than memorizing it?
I had a philosophy class where the final exam, we were all nervous about it. The final exam was one word: why. and myself and most of my classmates wrote pages and pages and pages. The only, and this is true, the only guy that got an A was the one that answered, why not? I'm not making that up. That's true. And we were all really, as you can imagine, not happy about that.
What year was that?
That was in 70. I went to Stuyvesant High School, which is a math and science school. And that was one of my electives. So I'm going to say that was in 72 or 73. I graduated in 73. That's a true story. And I did maybe 4 or 5 pages of just esoteric, well, let me explain,
It's a loaded question.
It is, but it's also quite simple. But anyway.
That's great.
I divert.
Oh my God, that's great. Okay, anyway. So, hey, Stephanie, I like this to be interactive, and so tell me how you're feeling, Stephanie. I hope you're still here.
Yeah, I'm here. I'm feeling okay. Yeah, I'm feeling okay. I like I said, the discussions are great. I think the overall, just trying to get the categories down of what we're even talking about is helpful. I'm not great at just memorizing without having it have meaning, and that's where I'm just trying to attach to the discussions, and even just the examples of somebody's house lighting on fire or the merry-go-round. All those illustrations are really powerful for me.
Good.
So,
Good.
and
Okay.
that you don't get from, or at least not the books that I've been reading.
Yeah.
So this is just the interactive dialogue is super helpful.
Okay, good. Well, we're on to radio wave characteristics. We're really past the heavy math part. Now we move to the more, getting ready to use it and having some fun with it.
You did say there were only going to be 2 math equations we had to know, and I think we spent a lot of time on 2 math.
No, because the math is the basis for everything.
Yes.
But now that you've seen it, you understand. Okay, well, you know what? I've at least seen. There's a circle, there's a unit circle, there's the basis for all of this. So now we've covered what waves look like, why they exist, and now we're gonna and then how to make them. Right.
And Scott, I've got a bunch of notes that I was taking, and if you would be able to check these for accuracy, because I don't want to send any mistakes to anyone, then I'd be willing to email them to everyone if they want to look over them.
Oh, cool. If you take notes, anything like my daughter does, they're probably amazingly good. And are they on paper, or she does it on the iPad?
Paper. I always do paper notes.
Oh yeah, but see, those are
pictures.
Oh, look at that.
Oh my
God.
God.
My gosh, look at mine.
You're gonna write a book. Yeah.
Hey, Ellie, can you send those out? Even if it's not 100%, it's going to be very, very useful. Please.
Yeah, of course. I just hope there's nothing wrong in them. I think they're all pretty accurate, but fantastic.
Will you have our emails?
Yeah, I have everyone.
To do that?
Okay, yeah. If Scott has everyone's, then yeah, totally.
That would be great.
Ellie, are you getting something out of this? I hope.
Oh yeah, 100%. Yeah.
Good.
I'm fresh out of some math classes from high school and freshman year, so that gives me a basis.
Did you go to South?
Yeah, Yeah.
Okay, well, Hannah went to South and Nate goes to South. So, but what year are you in?
I'm going to be a sophomore.
Okay, so she's 21. She's going to be a senior.
Mhm.
So cool.
I can't even comprehend how the people think when they do math, because my daughter, she's majoring in statistical mathematics, and it's like, oh my gosh, and she showed me some of her stuff, and it's like 2-3 pages long formulas, so I don't know how you do it.
At our next break, you want me to go grab some of my the labs that I did in college? They were all handwritten.
Yeah.
And
right?
one semester of labs was a handwritten notebook this thick.
Oh no. That's okay. We don't have time for all
Inch
that.
and a half thick. I still can't believe I ever did it, but then I think, oh, right. That was every weekend. That's right. And it was all handwritten. So, all right, radio wave characteristics.
Hey, Scott, one quick question.
Yes.
Can you summarize what the two key math issues
Hold on, you dropped out there.
problems are? You pointed out the one. Can you summarize what the two key math equations are that we need to know? You summarized the rule of thumb for the dB, which was, I think, 10x equals 10 dB and 2x equals 3 dB.
Yeah, then
Is
what?
that one of the two?
And Ohm's law.
Both of them.
Ohm's law? Okay.
And going from a frequency to a wavelength.
Okay.
So I summarize it by making these 3 circles. And in fact, if I do a class in person, I put those on the board.
Well, they're at the bottom of your cheat sheet that you sent us.
Yep. That's
Perfect.
it right
Thank
there.
you very much.
And then 10x equals 10 dB, and 2x is 3 dB. That's it. We're getting to the antennas. The antennas are going to be, fairly easy math compared to all this stuff, but we're going to be using this one a lot.
Which one? Oh, okay.
The one in the middle. Yeah. Okay, here we go. Radio wave characteristics. Everybody, the 2 components of a radio wave, we're on page 35. What are the 2 components of a radio wave?
Wavelength and frequency.
Nope. Electric.
Oh, never mind.
Electric and
magnetic
field. What do you know about the electric and magnetic field? They're all perpendicular. They're all at right angles. How fast does a radio wave travel?
Speed of light.
Speed of light. And the speed of light is approximately
Bazillion.
3 times 10 to the 8th meters per second. So 300 million meters per second. Okay. Excuse me. How do we refer to frequency bands? Well, if we look at the frequency spectrum chart that I sent out, we will see that somewhere. Band plan. Okay, so notice we have our frequencies. How are these bands called? What do we usually use? 30 meters, 20 meters, 17 meters.
Meter.
Yep, we use the approximate wavelength of the band. 2 meter band is not exactly 2 meters. It's about 2.05. We call it the 2 meter band. And shortwave bands, 49, 31 meters, they're all called out by the wavelength in meters. So just so you get an idea of where it is that we live, notice all these different bands that we have. We have access to all these bands, plus a whole bunch above this one. I want to show you the NTIA frequency chart. Can everybody see that?
Jeez. Yeah.
This covers from very low frequencies where it says not allocated to all the way up to 300 gigahertz, if I'm not mistaken. And notice it's in bands of 10 times, each of which is 10 times bigger than the previous one. So we call this one from 3 megahertz to 30 megahertz. That is called the high frequency band. Notice at the chart, high frequency is not really all that high. It's the 3rd one down. So it's actually fairly low frequency, but compared to what existed before that, what people were using. In the early 1900s, it was virtually impossible for people to use frequencies any higher than that. So that was known as the high frequency band, 3 to 30 megahertz. 30 to 300, that's known as VHF. And notice our color that we have access to, the colors that we have access to are the ones that are in this teal right here that says amateur. Notice these bands are used by a lot of different services. Now, just because it's teal doesn't mean it's ours. You know, you actually have to look very closely and see, oh, okay, that's ours. That's ours. That's ours. You look at this other chart and it looks like we have all these frequencies. And then you look at this chart and realize that our frequencies are really, really small. You know, our allocations are really pretty small compared to the entire spectrum of use. So 3 to 30 is HF. 30 to 300 megahertz is VHF. 300 to 3000 megahertz is known as UHF. So high frequency, very high frequency, ultra high frequency. Now, important to note, because each of these, we'll call them a decade. Each one is 10 times bigger than the other. And from one end to the other, it's 10 times. If you look at the total amount of space on the high frequency band, it goes from 3 to 30. How many megahertz is that? Between 3 and 30.
30.
27 megahertz. Okay, how about between 30 and 300?
207.
And between 300 and 3000?
297, whatever.
2700.
2700, yeah.
So there is a lot more bandwidth. I mean, if you look at these bands, there is, the further down you go on this chart, each of those bands is 10 times bigger than the previous one. That's a logarithmic expansion.
You say it's wider.
There's just that much more room. If you look at between 3 and 30 megahertz, you have 27 megahertz in there. Between 30 and 300, you have 270. Between 300 and 3000, you have 2700 megahertz of space.
Okay.
Even though it looks like they're the same space, each of these, as you go down, is 10 times bigger than the previous one.
Yeah.
So that's why the ones at the bottom look like a container ship on steroids.
That's also why the ones on the bottom are so sought after, because if you have a 1 gigahertz bandwidth signal, you know, you want to have a super fast network, where are you going to put 1 gigahertz on a band that only has 27 megahertz of space?
Nowhere.
You can't do it. So if you want that, the ultra high frequencies, super high frequencies, you know, like the 30 to 300 gigahertz range, that's the only place that you can put your stuff and actually have it work.
Wow, that ain't your dad's CB radio.
No, it is not. Okay, so moving on from that. So we did the band. Okay, so you have to remember HF, VHF, and UHF, what the limits are. RF stands for radio frequency. Okay, so now we know that what are the limits on HF, everybody? One more time.
3 to 30.
3 to 30. Okay, how about VHF?
30.
30 to 300.
300.
UHF?
300 to 3000.
Excellent. Okay. So all of these behave totally differently. So what we're going to do is we're going to draw a picture of the Earth, and we're going to have antennas that look like this, and we're going to aim signals up toward the sky. So these are going to be HF, VHF, and UHF. And so this will be 3 to 30, 30 to 300, and 300 to 3000. Whoops, too many zeros. Okay, so VHF and UHF signals will just typically go up into space when they hit the atmosphere. So this is the atmosphere that we live in. VHF and UHF signals will typically just penetrate all the way out into space, unless there's something very special for them to bounce off again. That might be in the case of VHF and UHF, that could be the lowest level of the atmosphere called the troposphere. The troposphere contains all the weather, or most of the weather that we deal with. Part of that weather that we deal with is temperature inversions, which causes different indices of, what do we get? I said we were going to say that. Howard?
Resistance.
I didn't hear the question. Say it again. I'm sorry.
Oh, the troposphere at about where all the weather is, that contain temperature inversions. Temperature
Right.
inversions cause differences in density of air. Different densities of air create different indices of
Moisture.
Of distortion.
refraction.
Refraction. Oh, yeah.
Remember, I said we were going to talk about it.
Yeah, you did.
I
You
did. Indices of refraction. And what happens is the same way that if you're driving down the road and you see a reflection of the sky in the road, that's caused by different temperatures of air right above the highway, which causes a different index of refraction. And what you can end up with is something called a duct. And your waves, which normally would just puncture right through the atmosphere, can actually get trapped. So you can get tropospheric scatter and you can get tropospheric ducting. And that's typically caused by temperature inversions and can take VHF and UHF signals a distance of hundreds of miles. Normally, those signals would basically go along the ground using ground wave. And a little bit, let's say that this is the end of line of sight right here on the ground to light. Radio waves might go an additional 10% because the waves are considerably longer and the Earth curvature compared to the wave is not as significant.
Well, what about the people that think the Earth is flat?
Well, then it should always work to
I
everywhere.
couldn't resist. I
know,
apologize.
but then it should always work to everywhere, which it does not. So
No.
Okay, so that explains a little bit of why the radio horizon is a little bit further out than the visible horizon, because radio waves are longer, so the Earth doesn't seem quite as curved. Radio waves also are bent slightly by the atmosphere, which causes them to go a little bit beyond the line of sight. So when are VHF and UHF signals propagated by the atmosphere? So once we get above the troposphere, we can get into the stratosphere and the mesosphere, et cetera. But then we get up into the layers called the ionosphere, which typically starts at about 30 to 50 miles up and extends up into basically the end of the atmosphere, which is practically speaking about 600 miles up. So we have layers called the D layer, the E layer, the F1, and the F2 layer. Those are the layers of the ionosphere that form as a result of solar radiation, which is the sun emitting visible light and infrared and X-rays and cosmic rays and gamma rays and ultraviolet and visible light and radio waves. The sun makes a lot of radio waves too, a lot of noise coming out of it. Fortunately, most of the hard ultraviolet and X-rays that hit the atmosphere are absorbed by the fact that our atmosphere is full of oxygen and nitrogen. Those typically trap and dissipate most of the energy contained in the ultraviolet and X-rays. But in doing so, that energy tends to take those stable diatomic molecules and cause an electron to pop off, causing ionization to occur. So you basically end up with a molecule that's missing an electron and a free electron that's floating around in space. Once in a while, one of those electrons will find an ion and then pop back together and recombine and just becomes nothing as far as we're concerned. But what ends up happening is that at different levels of the atmosphere, you have different populations of electrons that are floating around, different levels of ions that are floating around. During the day, they tend to get bigger. During the nighttime, they tend to get less. because the sun's not out directly overhead.
And they look pretty, really pretty up north.
Yeah, they do. So the other thing is with regard to this, that what are the two parts of electromagnetic waves, everybody? What are the two fields that are inside an electromagnetic wave? Electric and
Electrical and magnetic field.
electric and magnetic. Okay, the Earth has magnetic field lines. It also has these clouds of electrons that are floating around, generated by the interaction between the sun and the Earth. Well, you take some energy that is basically electromagnetic, and it goes up here and it hits these clouds of electrons, and all of a sudden what happens is that at certain frequencies, at certain angles, what will happen is that the light, if we want to call it that, it's radio waves, but it's basically like light, will be refracted back to Earth. And what ends up happening here is that this person can talk to this person well beyond the horizon, potentially over a distance of thousands of miles. This is known as ionospheric skip.
Reminds me of that commercial where the girl goes, "It's the mirrors."
It is. It is.
It's the mirrors.
It's close to it, yeah. But now let's take this angle and we'll increase the angle slightly. And now it gets refracted, but it goes up here. What happens to that wave that goes up that way?
Goes away.
Goes away, which means that what would normally be heard down here is not heard. So we basically have this zone right here where we can talk to people. And in this entire area, this is known as the skip zone. We skip over it. We can't make contact at certain frequencies inside of a certain distance because of the geometry of what we're doing. This is typically true of the high frequency bands, and it involves a lot of atmospheric physics and a lot of geometry and a lot of knowledge of the sunspot cycle, because the sun goes through 11-year cycles. We're coming up on the peak right now when the sun produces more ionizing radiation than during the dips. We also have a lot more solar flares at that same time. It also depends on season. It depends on time of day. And during the next break, I'll bring up a couple of cool maps that represent that. There's also something
And
called...
is it fairly predictable with all the extra knowledge, or is it fairly random where it's going to ultimately land?
Okay, well, so it totally depends. So I'm going to draw this cloud right here in the E layer, and then I'm going to draw another cloud in the D layer. The D layer forms every day during daytime, from sunrise to sunset. And what ends up happening is that this D layer ionizes very heavily, and all of your energy that goes up below about 10 megahertz gets almost completely absorbed, which is why AM radio signals, which are down in the 1 megahertz range, you can't hear them during the day from more than about 40 miles away. Whereas at night, if you've ever listened to the AM radio, you know that you can hear signals from far away.
Right.
The reason being that this layer right there completely disappears at night, and it allows those signals to reach the upper atmosphere. So that's the D layer. Then there's this E layer, which forms sometimes for still unclear reasons. And what this E layer does is it can take VHF and UHF signals and bounce them back down. But this is known as typically sporadic E, because it forms in the E layer and it forms very sporadically. It's almost impossible to predict where and when it's going to happen. And because of that, it becomes very difficult to plan contacts using it.
So it's completely random.
It's almost completely random. It's probably not in the end, and once somebody takes the time to figure out what's causing it. But it's been like that forever, and we haven't figured it out yet. So the F layer is the most reliable method of long distance communication. because it is going to form during the day just because of, you know, atmospheric physics and the fact that the sun is still shining. So long as we still have an atmosphere and so long as we still have the sun, we still get ionization in the F layer. The density of the ionization up there determines the maximum usable frequency that you can use. During the day, under direct sun is when you get your peaks. During the peak of the sunspot cycle is when you get your peaks. During the summer is when you get your peaks. So if you get, you know, a sunspot peak middle of the day in the summer, that's going to be your best chance of working really high frequencies. As soon as the sun goes down, you basically have this process of recombination of the electrons and the ions up there, and your population goes down, your density goes down, and your maximum usable frequency goes down. And this happens every day. And what this means is that the process of planning a contact on over long distances on high frequency can actually be quite complicated. It's also true that the Voice of America in the 1980s, when they were trying to figure out how to best spend money by, you know, not wasting it and sending signals into areas of the world where the signal could never end up, what they ended up doing as a result was creating a propagation prediction program that allowed them to kind of figure out what areas and what times of day and how much power using what antennas to run to optimize the signal that was getting to certain points in the world. Well, of course, us being hams, you know, we're, you know, kind of like the consummate experimenters. We have access to all these frequency bands. It was adapted for use in the amateur bands, and it's still used today as a prediction tool. And I'll pull that up during the next break. Okay, why do signals vary so greatly when an antenna is moved only a couple of feet? If you spend time on VHF, you will see this. Okay, so what we're going to do is we're going to draw a person, which is probably me with a radio, and we're going to have a wave that is traveling through space with a wavelength of 2 meters. Okay, so in between point A and point B, we have another person. Don't know who that is. So how many total waves were there in between point A and point B? Let's estimate. 1, 2, 3. We'll say 5 waves. Right? This is a really short distance communication, but it's still valid. So now, so we had 5 wavelengths between me and the other person, between point A and point B. Now, what we're going to do is we're going to draw another path. Let's say that I have a coffee table right here, and I'm going to draw the same wave. So let's see, 1, 2, 3, 4, 5, plus a little bit. So that was, let's say, 5.5 waves. Okay, so now I'm going to actually draw what's being received at the other end. Okay, so how much extra time did it take for the green wave to get there? They were transmitted at the exact same time, but the green one bounced off of a different direction and had to travel a little extra distance. What is the difference in the number of waves that it took? One was 5, the other was 5.5.
So half.
A half of a wave. Well, what's a half of a wave? Literally, it's a half of a wave, right? It looks like this. What happens when those get there at the same time?
Cancel out.
They cancel out. This is known as destructive interference. Because of the phase difference, because of the path length difference, those waves canceled each other out. So how could I remedy this situation? If I know something about the geometry, how long is this wave? 2 meters. So if I'm station B, what could I do?
Move.
Move. Take the radio, move it a couple of feet. And guess what? Now I'm at a point where the green signal is getting there and it's in phase because it's getting there at the same time. And it traveled the same number of waves. It might be a different amplitude, but so what? What are they doing now?
They're in sync.
They are in sync. This is now called constructive interference. They're actually helping each other out.
So they're making the amplitude bigger.
Yep. This is known as multipath. Multipath is a very common thing because radio waves rarely travel between 2 points in a straight line, in an exactly straight line. There's always something to bounce off of. If you're driving a car, you might actually sound something a little bit like this as you drive around, because you're going from constructive to destructive interference, but because of your speed, it's changing from constructive to destructive and back and forth rapidly. And that's known as picket fencing, because it sounds like you're actually talking to someone from behind a picket fence. The pickets are moving in front of you and blocking you. Okay. If you do have multipath interference is usually not a good thing. Multipath interference, if you're using voice, it'll make you sound weak. If you're using digital communications, having computers talk to each other, it'll increase your error rates because you're starting to lose pieces of the signal.
Yeah, that's why the old TV is better.
Yeah. Here we go with another one. Although old TVs, if you had multipath, you could get ghosting.
Mm-hmm.
So, whereas now you'll just have blocking. The signal will go away.
Yeah, exactly. It's
pick your poison.
See a picture before, but now you don't get nothing.
Now it just turns black. That's right.
Or little squares that melt.
Right. What effect is multipath interference? We talked about that. Okay, so let's say that we have something or other right here. If you live in Oregon, this is called a mountain. And you're hiking down here, like my friend Nathan, and there's another hill here. And up on this hill, on the other side, is a repeater, which we do have. But notice that Nathan could not get to this repeater because there was another hill in the way. That path is blocked. He was up in the Mount Hood wilderness. He actually got his signals back to our repeater by pointing them at Mount Hood and bouncing them off of Mount Hood so that they would bounce off of that large object and back to our repeater because it was higher than he was. So if something is in the way, you can actually bounce your signals off of solid objects. Now, another thing he could have tried, there's something called knife edge diffraction, which is if you have a steep enough peak, and this is another result of physics and diffraction, you could actually aim it right at the peak and you'll have some signal that basically diffracts in all directions, including down. So that's known as knife edge diffraction. On microwaves. Okay, remember I said we were going to talk about microwaves?
Mm-hmm.
Okay. What is a microwave, everybody? What is a microwave?
A faster wave than a radio wave.
No. Microwave is another frequency of a radio wave.
Yeah.
That's all.
That's what I meant. It's a faster frequency.
Well, that's a higher frequency, 2.4 gigahertz. And guess what? This is a ham band. You can actually repurpose a microwave oven if you can get it to oscillate in a nice, stable fashion. You can actually operate a microwave oven on a ham band.
Yeah, that's something Charlie would do.
Scott, can I just ask a quick question, please?
Sure.
Because the way you were saying this, when it comes to refraction, you were implying, if I got you correctly, that 100% of that signal gets reflected or refracted.
Oh no!
There is a portion of it that gets absorbed.
Most
so
of
the
it
signal is
disappears.
actually weaker.
Most of it disappears.
So when your buddy is pointing, when he's going to the higher mountain to get to the repeater, he's losing a great part of that signal, but he's still getting something, whereas before he was getting nothing.
That's right.
Is that
That
Okay,
is
just
true.
want to.
Actually, the same is true when you're aiming a signal at the sky. If you're aiming I mean, if you're looking at a single hop, okay, so here's the craziness of the numbers. So S9 is a really strong signal, right? If you look at an S meter, which is a signal strength meter, that is calibrated as 50 microvolts across 50 ohms at the antenna terminal. Well, let's do a little math. V squared over R, right? That's our power. So that's 50 times 10 to the minus 6th squared divided by 50 is 2,500 times 10 to the minus 12th divided by 50 is 50 times 10 to the minus 12th watts, which is how many watts? What's 10 to the minus 12th, everybody?
Picowatts.
This is 50 picowatts.
Something.
50 picowatts. That is 50 trillionths of a watt. That is a strong signal coming into a radio. So let's say that you transmit a signal at 100 watts up into the sky. To be a good, solid, readable signal, like a loud one, this much power has to get down into the other person's radio through their antenna system. What percentage of that is that? So that's 50 times 10 to the minus 12th divided by 100. So that's 0.5 times 10 to the minus 12th is 5 times 10 to the minus 13th, and then divide by 100. So that's 0.000000005% of your transmitted signal that actually gets to the other end. Think about the absurdity of the fact that this works at all.
It's magic.
This is actually magic. This really actually is magic. And this is why, to me, radio is still one of the most fascinating things out there, because it is only by virtue of the fact that amplifiers can produce enough gain. They can receive and amplify a signal that is this much. Remember, that's a strong signal. You can have a much weaker signal and still be able to listen to it. This is what we have basically been able to create with electronics.
So you figure if you amplify a sound from a guitar amp at 100 watts, you can't barely stand in the room with it.
Yep, 100 watts is a lot.
And then when you go to make it come out of your radio so you can listen to it at all, and you just amplified it 10 to the 12th.
10, right, 100 trillion times.
Which you can't even count that much in your lifetime.
No, exactly. Yeah, those are the kind of numbers that we're dealing with. That is, to me, why radio is such an amazing thing. That the fact that it works, the fact that I can actually talk to somebody more than halfway around the world. The propagation from solar radiation gives me the ability to do it, and the equipment gives us the amount of gain necessary to do this. Even if you only do it using a handheld radio, still the numbers are mind-bogglingly small.
Well, you could do it further, but there's a time delay.
Yeah, the time delay doesn't even come into play. I mean,
really? I mean, if you're talking like to a space shuttle or something.
Actually, that's not far.
That's true.
The moon is only a second and a half.
Yeah.
I mean, I've actually heard my own signal before, bouncing all around the world, like the entire trip around.
Like an image.
Oh, it was actually my own signal echoing completely around. It was about it was less than 0.2 of a second delay. It goes pretty fast. Okay, so now we're talking about microwave oven. So a microwave oven operates at 2.4 gigahertz. Why is that frequency picked? Why is it so important?
So it can interfere with your Wi-Fi?
It can, but that's not why. Why is that frequency picked? Why was that frequency picked?
Because that's what was allocated in the band. I don't
Nope.
know.
Because I'll give you a hint. Any idea what that is?
A Mickey Mouse?
Yeah,
It
except
needs water.
Hydrogen
water.
oxygen.
Water
Yes, water.
molecule. Okay.
H2O.
This is approximately the resonant frequency of the water molecule.
Oh, okay.
Water is strongly resonant at that frequency.
Holy cow.
So if you take a water molecule and you expose it to 2.4 gigahertz RF energy, what will happen? It will absorb energy and shake violently. What is violent shaking also known as?
Heat.
Heat. So you basically heat up your water. That's why a microwave oven works. The fact that a microwave oven puts out 1 kilowatt at 2400 megahertz into a chamber. Now, the other question is, why doesn't a microwave catch fire?
Faraday cage?
Well, that's part of it. Well, but the resonant frequency of a microwave oven, right? The frequency of operation of a microwave oven is about 2400 hertz, 2400 megahertz. The wavelength is about 12 centimeters. If you were to look inside your microwave oven, you would see, okay, bad things that can happen. Bad things happen when a wall has a voltage that changes drastically from one point to another. Because if you have a voltage here and a voltage here, what's going to happen between those points? If you have two different voltages, you're going to have a current. And what is a current going to look like?
A spark.
A spark. It'll leave a little track, carbon track. It'll burn something. So clearly that's a bad thing. So what you want is you want to choose your entire cavity so that your voltage on all the walls is 0 volts. So there are only certain shapes and dimensions, which are going to be multiples of to 12 centimeter wavelengths. They could be half waves long. That could be 6 centimeters. So that's why there are only a certain number of shapes and sizes. They're always going to be rectangular, but that's why there are only a certain number of sizes of cavity that microwave ovens can be made to make sure that this wall is at 0 volts and this wall is at 0 volts, this wall is at 0 volts, and so on and so forth. So that all the surfaces are at 0 volts.
So those
What
great
does it
big
mean if
walk-in microwaves they have at the food store,
Mm-hmm.
those things are huge. You can actually walk inside of them and they won't even turn on unless there's somebody the interlock switch that allows it to turn on.
But that's why the RF energy, basically it's allowed to exist like this, but then in this direction, it has to look like that, where it goes through 0. And then from top to bottom, it has to be like that, where it's 0 on all the surfaces.
Wow.
That's why
So what does
microwave
it mean
ovens.
if your microwave starts sparking?
Well,
You put metal in it.
you
Yeah,
put,
so-
if you
Yeah,
put
you got
metal in
something
it,
in there.
or what happened is where was the sparks coming from? The front or the back?
A couple of years ago, we had a microwave that was getting really old. I can't remember where it was coming from, but every now and then while it was microwaving, like on the inside, there would be sparks.
Yeah.
And we got rid of it, but we weren't microwaving metal.
There was probably some kind of debris in there.
Remnants. Yeah.
There was probably some kind of debris. I've been told that it's really fun to take a compact disc and stick it in the microwave.
Yeah.
Compact. I've never done it. I've seen it done. It makes a really nice streaky pattern where it basically fried the aluminum in between. Oh, you've done this. Yeah. Okay.
No, I haven't done it, but I know of it.
No, Ellie
I think I
has.
saw it on
I have.
YouTube. There's a YouTube
not
on it.
on my own microwave. That
kids
was
will be
at
kids.
the UO Science Fair.
They
had a
did it
booth
at,
where
that's right. They did it in the physics department.
Yeah, they were
Yes.
letting all the kids come up and microwave basically this pile of objects. I really like doing the steel wool. It would make these little explosions. Lots of fun.
Yeah. Well, I mean, you have voltage differentials. Voltage differentials create current. Voltage times current equals power. Burn something up. But that's also why you rotate your food. because at certain points, you're going to have no voltage in there, which means you're going to have no current, which means you're going to have no power dissipation in your food. That's why you rotate your food. Okay, but now where we are back to that is, what is the effect of vegetation on VHF, on UHF and microwave signals? Vegetation has what in it?
Water.
Water. So if you're using the microwave bands, what'll happen if you try to send a signal through trees?
Round it out.
Yep, it'll drown it out. The same thing is true if it's raining. Rain will affect your microwave signals very, very strongly. So if anyone's ever noticed on rainy days, if they have like satellite TV, satellite radio, depending on the frequency you're operating on, if it's raining really hard, you'll lose your signal. That's why. Antenna polarization. Okay, so antenna polarization. This is a vertical piece of wire. A vertical piece of wire generates an electric field that goes up and down. That is perpendicular to the Earth's surface. This is called vertical polarization. Horizontal polarization, if you have a horizontal wire, the electric field will generate a horizontally polarized wave. It's parallel to the Earth. So the polarization of a wave is the direction of the electric field. So a vertical wire makes a vertical electric field, so it's vertically polarized. Horizontal wire makes a horizontal electric field, so it's horizontally polarized. Now, let's say that I have an antenna that is vertically polarized. It is making an electric field that's oscillating up and down, and it encounters a horizontally polarized antenna, like on the right side of the screen. The job of an antenna is to allow an existing field to move electrons in it, which means it needs to allow an electric field to do its work. The electric fields in this case is perpendicular to the way that antenna is designed. So how much of the signal will get through in this case?
Not as much.
Very little, actually. There could be 20 or 30 dB loss between the two. Just by simply taking the antenna and rotating it to a vertical position makes it a functional antenna.
Within what proximity?
Any
Proximity.
If it's line of sight and there's a vertically polarized wave and it's not rotating, like, if something's been skipped off of the clouds, it's basically randomly
Right.
polarized. But if it's direct line of sight, the polarization is very, very important.
So is that a way of signal jamming?
How so?
Well, I'm just wondering if you're blocking basically the signal from being received, isn't that jamming it in a matter of speaking?
No, you're basically ignoring it. So
You can't receive it because you only have a cross section of your antenna receiving
right.
the signal.
So
Yeah, but that's what I'm saying. I may be going off on a tangent here, but
it's not jamming, it's just ignoring. Have you ever
No.
Have you ever worn a pair of polarizing sunglasses?
yeah,
Okay, so when you put on polarizing sunglasses, how much glare do you get from the hood of your car?
less.
Because the polarization as it bounces off the car,
Right.
as the hood of the car is
Right.
horizontal, and you have vertically polarized sunglasses. So
Right, no,
essentially,
I think it's good.
essentially the energy that's moving back and forth this way, when it hits the sunglasses, isn't going to have any effect. It's not going to make it through. It's the
Interactive
same thing.
3D glasses.
Yeah.
Same kind of thing. Open, close.
Yep.
Anyway, yep, gotcha.
Okay, which of the following types of propagation? I'm just going to put this up on the screen. This is important to know. Okay, which of the following types of propagation is most commonly associated with occasional strong signals on 10, 6, and 2 meters? Notice the answer is sporadic E. So remember sporadic E, that's the E layer. That's the one that we can't control. The one that just sort of forms whenever it damn well feels like it. That gives us propagation whenever it damn well feels like it. And that's why, for instance, the 6-meter band is largely subjected to the whims of sporadic E. I just recently, this will make sense, but after 25 years of work, I just recently completed my VUCC on 6 meters, which is working and confirming 100 grid squares. That will make sense in a little while when I show you the grid square map. It took 25 years. I had to wait. Basically, I had to wait for decent openings on the 6 meter band, essentially waiting and monitoring and trying to figure out when 6 meters was going to be open via the sporadic E mode. It typically only happens during the summer and whenever it feels like it. So, one Tuesday morning, I was at work and somebody told me that 6 meters was open, and it was open to Florida. This is a VHF signals all the way to Florida. And I grabbed my phone and I took control of my radio from work.
Wow.
And I was actually able to work something like 20 new grids all over the southeastern United States on a band that's normally line of sight, just because there was this enormous E-skip opening that just happened to show up one day. Didn't repeat the next day, wasn't there the day before.
Wow.
Pretty wild. Auroral backscatter. Backscatter is typically on the 6 meter band. Now we were talking about aurora. The aurora is caused by high energy particles coming out of the sun being funneled in through the magnetic field of the earth to the poles. Well, in doing so, when they stream down, they cause the aurora. The aurora is basically a multicolored plasma. Well, plasma is what? Plasma is excited energetic particles. They're electrically active. Well, if you aim a radio signal at them on the 6 meter band, for instance, there's a chance that some of it's going to get bounced back. So that's called auroral backscatter. We can also, on the 6 meter band, aim at meteor trails. If we have a good meteor shower where we have a few per minute and you're aiming a signal which is fairly wide, you're aiming it up at the sky and you're calling at a really high rate of speed so that a complete transmission only takes a second or two, the trail made by a meteor might last for 10 seconds. So you aim at where you think it's going to be and you just keep sending out signals. And if there happened to be a meteor that left a trail, if you're lucky, it gets bounced back down to earth and somebody else receives it. And then during another one, they'll say, okay, I heard you. And here's your reply. It might be 5 minutes later, but and it's going to be really, really short bursts of data.
Did you do anything during the Perseids shower?
I've never successfully done anything with meteor scatter. I don't have big enough antennas for it. I mean, I think it'd be really cool, but I know that people are out during the Perseids and the Leonids and all the good meteor storms and but no, I've never successfully done it. However, I am going to Vanuatu in a month and a half. And one of the things that we're going to be doing there is, in addition to operating just on HF, one of the guys is bringing all of his Earth, Moon, Earth, also known as moon bounce equipment. So we're going to be operating moon bounce from Vanuatu. Yes, you can bounce signals off the moon.
Who knew?
Yep. And by the way, as a technician class licensee, one thing that's very important for me to note right now, the stuff that we're talking about here is it's kind of esoteric, but it does happen. Notice this propagation for VHF, UHF over the horizon. That's tropoducting. Tropoducting is temperature inversions, and fog and rain on the high frequency bands is basically no impact. Now, I would like to point something out. I want to draw this picture. And okay, so some of you might say, well, all I want to do is operate a handheld radio at 3 watts. Okay. So if we look at the frequency spectrum and the things that you're permitted to do, So you are allowed to operate with an output power of up to, on most bands, 1,500 watts. With a license, with a technician license, which is the basic license that you will be earning. So get that number again, take a look at that number and realize that that's 1,500 watts of RF energy. And that can be at pretty much any frequency you want that there's a ham band. That can be on, frequencies right adjacent to Wi-Fi. I mean, this is a lot of power. Okay. Now, let's say that you have a Wi-Fi router that transmits 0.4 watts, and it is allowed an antenna with 0 dB of gain. Okay. Well, now let us take your Wi-Fi router, and you can do this with it. It has 0.4 watts, and you run this through a homemade amplifier, which you're allowed to build, which is up on a hilltop, and you are allowed to bump that power up to, let's say, 1,500 watts. And attached to this transmitter, which is now running at 1,500 watts, you've repurposed a dish antenna, which you found in the garbage. Don't laugh. It happens. A dish antenna with a horn that's running with 30 dB of gain. Okay, so now let's go through and see just what this does. Okay, what is 30 dB of gain? 30 dB. Well, we're going to split this out. That's equal to 10 plus 10 plus 10. Every time we go up with a factor of 10 decibels, what do we do to our power level?
Double it.
No.
Half it.
No.
Oh,
10,
triple it.
no.
Do one of
10,
these.
10 dB.
By 10.
10 times. So it's 10 times 10 times 10 is 1,000 times. You have 1,000 times gain, and you're allowed to run at the transmitter 1,500 watts. So you have 1,500 watts times a gain of 1,000 times is how much?
Burning up somebody's
1,500 kilowatts.
1.5 megawatts of effective radiated power.
Mm-hmm.
Your license permits this. This is why you need to get a license, even if you only ever plan to use a handheld radio. Basically, it's like, your license permits you to drive a Ferrari, even if you only ever plan to, to drive like a little Honda Fit. Your license permits this. That's why you have to get licensed. That's why we go through this process. You can build your own stuff. This is a license to do what you feel is necessary within the rules to do what you want to do. If you want to put out 1,500 watts of ERP and the beam width is like this, what are some things you need to know about what you're doing? Let's hear it. What's the most important thing to know about what you're doing?
You don't want to point it at somebody.
Yeah, don't want to point it at somebody. That's right. You will cause somebody some serious harm.
Cool.
Knock birds out of the sky.
Yep. Been done.
Yep, it has.
The military does that stuff all the time.
Yep. So there you go. So if there's any reason why you think, well, why do I really have to know all this stuff? This alone is why you have to know all this stuff. And I'm sorry, but this is why you have to know all this stuff.
Right, but you figure you make a setup like that, you aim it to your next door neighbor down the street. They don't have Wi-Fi anymore, and they have to go out buy new routers and everything.
Yeah, but now, what would you do something like this for? Why would you build a system like this?
Maybe to have wireless communication between two places that
Doesn't take that much power.
No, I mean like a long way away from each other.
Yeah, but you're still limited. I mean, basically the delay would cause you to, it would work, but
so the data delay wouldn't be worth it.
No. And on top of that, you're still limited by line of sight. So what can you think that you would want to do where line of sight wouldn't matter? Beyond line of sight. I'll give you a hint.
Bounce it off.
Yeah.
Yep.
Yeah. Space.
Yeah, you want to run moon bounce? This is what you would do for moon bounce. And I can show you some pictures of what people do for moon bounce and why this is of interest to people.
Okay, so you think the people in India that just took their unmanned thing and landed on the south pole of the moon and be pissed off, you burn their thing up with that?
Oh, no, you won't do that. By the time it got up there, you'd be dissipated so much it would have no effect. I mean, the amount of the beam width that you get is it separates, it spreads out so much it wouldn't even be an impact. There we go.
Oh, cool.
Yep.
Moon bounce.
Moon bounce. There's another one. There's another one.
What are those, K-band? Is that a K-band dish? or something?
Probably. It's just repurposed. There's another one.
Wow.
Oh, here's another one. It doesn't have to be.
Oh, it can be like that. Yeah.
It can be like that. That's an EME array. And each one of those sticks that you see is carrying 4 additional sticks that are all in phase with each other. So that is a 1, 2, 3, 4, 5, 6, 7, 8. That is a 32 element array.
That looks like a moonraker or something.
Yeah. Well, that's on the right. That's a 32 element array. Or sorry, 32 antenna array. It's a 4x8 array where each antenna is probably 15 elements. And he's probably running, they're probably running 1,000 watts and have a lot of big preamps up there. That's a $50,000 setup just for working moon bounce. But you can say you did it.
Yeah.
I don't that's why I've personally never done moon bounce. I don't have that much money to spend on.
What was that one array that was all the way in the upper left? It looked like four TV antennas stuck together.
It probably was. Let me see if I can find it. EME array.
You said it was 100.
Oh yeah, there we go. Yeah. Here we go. That is a 2x2 array on a small rotator, and each one is 1, 2, 3, 4, 5, 6, 7, 8, 9, like 13 elements.
Where are we looking?
Up on the upper right.
Upper right. Okay.
Yeah. Well, the big one on the right hand side.
Okay.
I was talking about the one on the upper left, the one that looks
up
like
there?
somebody. Yeah, that one.
Yeah, those are actually that's 4 or 5 element antennas.
They look like FM antennas.
They're specifically for 2 meters, but yeah, I mean they're basically just a Yagi.
Huh.
Just a 5 element Yagi. Nothing exotic.
But they're actually using that for moon bounce.
Yep, you just got to aim it in the right place.
Huh. That's
And
good.
actually, before Arecibo, before the whole dish system collapsed, they used to use Arecibo for moon bounce. You guys familiar with Arecibo?
Isn't that the thing where the towers the cables gave way and the dish crashed into the trees?
Yeah, here.
Now China has the biggest one in the world.
This was Arecibo. And it was basically built into a mountaintop in Puerto Rico. And when they weren't doing studies, the hams who were stationed down there at Arecibo got to use it for moon bounce.
Oh, cool.
Needless to say, the people on the other end did not need terribly big antennas. They did most of the work.
Yeah, but consider the expense they went through to make that thing, and then they just let it decay and wasted it.
Well, I mean, it had a lifespan, it was going to collapse at some point. It was expensive to maintain.
That thing went through a bunch of hurricanes.
Yeah, it did. It was expensive to maintain. And it was going to collapse eventually. All right, HF propagation.
Scott, are these actual questions from the question pool or are these separate?
What, the ones we're
These-
looking at right now?
Yeah,
Yeah, they're on the question pool.
they're part of the pool. Okay.
Yep.
So what does T3A looks like 1-1 mean?
If you look at the question pool, you will find that that is the question number in the pool.
Oh, but is there significance between having it be a T? I haven't looked at it, so I
The
apologize.
T just means technician. All the G's are general, E is extra.
Okay, got it. Sorry to waste your time on that. I
Yep.
didn't know.
That's cool. I didn't know what that was. That's a neat piece of information.
Yeah.
that Really didn't need to know, but there now you know it.
Yeah. And so like example 3A, A is probably one of the categories.
It's section 3. Yeah, section 3, subsection A, question 11.
Okay, perfect. Thank you.
The region of the atmosphere that can bend HF and VHF radio waves are the ionosphere. Long distance ionospheric propagation is very common on HF compared to anything else. Okay, so which of the following bands can provide long distance communication during the peak of the sunspot cycle? So for this, you have to understand that during the peak of the sunspot cycle, that would be the higher frequency bands. If they're the higher frequency bands, you would pick the highest frequency band choices. Notice that, but at some point, 23 centimeters isn't going to work. It's 1.2 gigahertz. 70 centimeters and 1.25 meters. Those are upper VHF. Those all are also aren't going to work. So really 10 meter F layer propagation, 6 meter F layer propagation. I haven't seen 6 meter F propagation in my entire life. I've never seen it good enough. However, there are people who were licensed in the late 1950s. They used to do it. Yeah, 1957 to 59 was a monster sunspot cycle with ridiculous conditions. And they used to do that. Like from here to Japan on the 6 meter band, which is VHF, here to Europe, here to Africa. And it should be line of sight normally. So generally best for long distance 10 meter band propagation. So that would be from dawn to after sun, so shortly after sunset when the sunspots are in. And fading of signals. Well, remember we covered multipath, how signals combine. Sometimes they're constructive, sometimes destructive. By physically moving, like if I'm holding a handheld radio, if I move a couple of feet, it might help things. What if I'm operating on the 20 meter band? How far would I have to move? I'd have to move at least 10 meters. That's 33 feet, except my antenna is attached to my house. So you basically just disappears and then comes back and then talks for a couple seconds and everything's good. And then
So you
to
basically
come back
you're not
again.
reliably going to be talking to that person.
You might, but you might not. You might have deep fade. And that's, we call that with Q signals, we call that QSB. It's basically just deep fading. So random combining of signals through random paths. Elliptical polarization means that you can basically have any kind of antenna you want if you're aiming it at the sky using the high frequency bands, because the signals get absorbed and re-radiated. And because they're getting re-radiated, they're randomly polarized. So if you're using a horizontal or vertical on the ground, it doesn't really matter. Okay, antenna types. Here we go. Antennas and feed lines. This is actually my favorite part of the whole class. Okay, so antennas and feed lines. You know what? Let's take a 5-minute break. It's bathroom time, and I'm going to pull up a really cool picture at the same time.
Because we only have like 15 minutes left after that. That's fine.
Well, 20. It'll be 20.
Okay. Oh, okay.
Yeah, it'll be 20.
That's fine. Cool.
All right.
Okay, and while I'm pulling this up, feel free to ask anything. It's a good time to do it. If anyone has anything.
Hey, there he is. He's back.
I'm still here. I never left. Well, I did leave for a minute.
So where in the world in this US band plan update do the CB radios fit?
CB is at 27 megahertz. They're squeezed in between 10 and 12 meters.
Oh, that's why you don't see it, because it's squeezed in somewhere.
It's in there. So it is there, but I mean, it's a very small band. It's very narrow.
And on that thing that looks like a big container ship.
Yeah.
It's in the top one, right?
It's all the way at the right between 3 and 30.
Zoom that in because that thing is way small.
It is zoomable.
Yeah, I know. I'm zooming. Between 3 and 30, there's 14. Is it?
Okay, everybody, is everyone back?
It just doesn't say it anywhere.
No, it'll be there.
Fix. There's a green band that has no name to it.
No, it's there. I know I've seen it.
Maritime Mobile.
Yeah, they're NTIA. Let's see. It's between 26. It's listed as mobile double star. It's kind of a pinkish.
Mobile double star.
Yeah, I'll share it. You see that?
I'm looking in totally the wrong spot. I should be looking further down. I'm
So-
looking, why am I looking at the wrong spot?
It's right here. Here's 26,965. That's the first half, and then they're up to 27,225, and then right here. That's it. That's the entire CB band. Right there.
Wow.
And then then there's
Oh, okay, now I see.
and then there's MERS. That is right up here. See this area that says land mobile or mobile right there?
Yeah,
That's MERS, that's multi-use and multi-use radio service. Here is our complete vaunted 2-meter ham band. That's the first half of it, and that's the second half. And notice we have amateur satellite. That's the entire 2-meter band.
and that's where that guy said he was pointing his
Yep.
4 antennas at.
Yep. And then the same thing up here, 420 to 450 is right here. That's our 70 centimeter band. And notice it's actually shared right here with radio location.
All
So
right.
we're actually a secondary user of that band. There's another band up here. This is the 900 megahertz band. ISM. And then there's another one. This right here is, see this one right here? 2400 to 2450, where it says amateur, mobile, fixed. This is all Wi-Fi. That's 2.4 gigahertz Wi-Fi.
But they call it amateur,
It's a combination. See this radio location?
right?
That's the 2.4 gigahertz Wi-Fi band. So we actually share that. And the same thing with 5.8. If you're did anyone here a drone pilot? Anyone do any FPV drones?
Nope.
My brother's gonna train to be one. He does robotics at South.
So he's working with Lally then. So you see where this says radio location, mobile, fixed, et cetera, et cetera. This right here is from 5.6 up to 5.9. That is a ham band. That is why it is recommended that most people who do FPV drones get their ham license, because the actual area of the band that you can use if you don't have a license is really, really small. If you get your ham license, you can use the entire band that all those drones are set for. So that's why Lally recommends that her students get their ham licenses.
I'll let him know.
Yeah. Oh, she knows.
Oh, no, Benji, my brother.
Ah, okay. Okay.
Yeah,
so
he
now,
wants to be able to use his toys with more effect.
well, they're big toys.
Oh, yeah.
It's a professional drone pilot's license.
I know the Webster Field where I used to work at, we had all these drones. The Navy had all them things up there. It was amazing.
All right, so here we go. This is, okay, the first thing I'm going to show you, this is VOACAP, the Voice of America Capacity Program or Capability Program. This is for predicting what bands will work between any 2 points on the planet, given your choice of operating characteristics. So Morse code, I'll change that to sideband, I'll go to 100 watts using modest antennas from here to Europe. Notice this is our propagation wheel. Around the outside is the time of day and universal time. Up and down at the left hand, up and down gives you the frequency band, 10, 12, 15, 17, 20, etc. If I were to change this and say, show me between here and Norway, notice the picture changes. Between here and South Africa, it changes again. Between here and Japan, changes again. I can also look at long path, which is going the other way. There's short path, there's long path. So these prediction tools are pretty amazing. Like here to South America. Oh, that must be long path. Yeah, short path, much better. East Coast to West Coast. Surprisingly not as good as you would think. Now, the question is, where does the rubber meet the road? So if we look at the frequency spectrum chart, you see that the band plan says that, oh, stop it. The band plan says, let me unshare the new share. Here's the band plan. Notice you've got all these different frequency bands. The lower frequencies are typically night bands. So this band, 160, 80, 60, 40, those are typically night bands. 30 is usually night, 20 is day and night, and then anything above that is daytime. So this is everyone in the Seattle area and what they're hearing on the 40-meter band, which should be a nighttime band. Notice, pretty much nighttimey, right? We're going to pick a different band. Here's the 15-meter band. What do we notice about that? The daytime band. It's from daylight into where it's just recently gotten dark. But notice something else about it. It's not like there are no people closer than Texas, right? How come we can't be heard closer than Texas?
You know, I'm not picking up what you're putting down about the daytime and the nighttime.
Well, when's the sun stronger, during the day or night? At night?
Okay, so
and since the sun generates all of this, certain frequencies, certain bands require more ionization than others.
okay, I got you.
Right? So the higher the frequency, the more the ionization is required. Yeah, so what's happening here is that in order to get any closer than, let's say, San Diego or Dallas, our angle would have to be so steep that the signals are not getting bent back to Earth. They're passing through the atmosphere. Now, how is it that we managed to get this first cluster, let's say in Texas, and then another one in like Venezuela and Colombia, and then another one in Eastern Brazil? Take a look at the map and tell me what you think.
What map?
You guys see the map on the, oh, shoot, it's not on the screen.
That's
Darn
why I
it.
wasn't picking up what you were putting down.
Oh, I thought it was.
My bad.
There we go. Okay, sorry about that. I thought it was on the screen. That's one of the problems with not being able to see myself. All right, can everybody see that map now?
Yeah.
Okay, so 40-meter band. Notice nighttime band, not a lot there during the day. This is, okay, so here's the 15-meter band. Notice that we've got a cluster in Texas and another one in Southern California, but then nothing any closer. The reason we can't get any closer is because we bounce up, we bounce down. If we want to get closer, the angle is too steep.
Okay.
Okay, but how come? Okay, but now notice we have a cluster in Texas and then another one in like Colombia and another one in Brazil. You notice anything interesting about that?
It bounces and then goes down and bounces again.
Multiple hop. So this cluster in Texas, that's first hop, bounces off the ground, off the water, up off the sky, bounces back down, gets picked up here. Signals that are bouncing into there they bounce up and bounce back down, and they end up being received in eastern Brazil.
And they don't do that off the water.
Oh no, they do. The water's even better.
Oh, is it?
Well, what's water made of? What's ocean water made of?
Right. H2O.
But yes, salt water. And what do you know about salt? Salt, when it dissolves, makes water really conductive. Okay, so now we're picking a different band. Notice this is a 20-meter band, and the map looks completely different. Right? Notice we had this previously, and now we've got this.
So the earlier one was the 40 meters.
This is 17. This is 15 meters.
Okay. 15.
Usually better for transequatorial propagation, which we're getting. But notice this band. People are getting into Europe. People are getting into Japan. But how about the signals into Latin America?
Not many.
It's not for lack of trying. So now let's pick another band. This is the 30-meter band. This is one that is kind of like a hybrid day and night. So not bad. And notice that they're actually getting nearby signals. So from like Seattle to Eastern Washington, like Spokane, Salt Lake City. So you don't have that skipped area. And you also have occasional signals getting all the way to Europe. So all these bands behave totally differently from day to night and place to place. So like if I were to try to pick, I'll see if it's going to behave.
So
15
what is
meters.
this? What is this thing that you're on that you're doing that from?
This is actually called PSK Reporter. It's a website that aggregates received signals that people's computers, when they're receiving, are reporting. So notice now I'm looking at signals from Australia. They're not receiving. Oh, let's see, QF22. So very little in the way of 15 meters, but now I'm going to switch over to 40 and see if the Australians, nope, not a lot. Let's see, 20. Oh, there we go. Pick out 20 meters from Australia right now. So look at that. They're even working into Western Europe through the darkness, which is kind of amazing. Like I said, it's kind of a day-night band. It's sort of the 20 meters is sort of the radio superhighway because of the frequency that it's on. It's always open to somewhere. All right. So that's high frequency propagation. And that's
Scott, as a technician, we don't have access to, as technicians, we don't have access to those higher bands, the 30, the 40s, unless we're just doing continuous wave.
You have 10-meter phone, digital, and CW also.
10-meter ends at phone, right? Okay, but we end at 10-meter for phone, right?
Yeah, but you know what? Get your general license. It's a lot more. It's a lot more fun.
It's really not all that much harder to get,
No,
is it?
no, it's really not. Much of the material is really similar. Having had a lot of people who've done both.
Okay.
Okay, let's see. Antennas and feed lines. Okay, so antennas and feed lines. Here we go. This antenna right here is horizontally polarized because it is parallel to the ground. Okay, so this antenna, we're going to pick the standard basic antenna. We're going to make it a half wavelength long. What's important to note is that this antenna at 1/2 wavelength is literally a half wavelength long. If I were to draw this antenna, I'm going to ask you a question. What is the current at the ends? What does it have to be? How much traffic goes through a dead end street?
Can't be anything.
It has to be zero. That's right. So if I were to draw the current and I have a half wavelength, it looks like this. So this is the current distribution. It has to be in the shape of a wave. It basically goes like that, it goes like that, and everywhere in between. So it oscillates back and forth between up and down, but the ends always have to be zero. Where are the biggest swings going to happen? Right in the center. Right in the middle. So it turns out since the maximum current is right in the middle, this is going to be your lowest feed point impedance. Because E is equal to I times Z, so Z is equal to E divided by I. If your current is max, then your impedance is going to be min. Just empirically. So a half wave dipole is literally a half wave long. It can be fed here, it can be fed here, it can be fed here, but it can't violate the rules of physics. The laws of physics say that the current at the end has to be nothing. And because of that, its current distribution is going to look like this. What's nice about this is that this dipole antenna is really easy to make. Dipoles are super easy to make. It's just 2 pieces of wire, and they're actually somewhat directional. They make a figure 8 pattern in the shape of a donut, kind of, around the antenna. So they make a perpendicular radiation pattern, perpendicular to the direction of the wire. So how much radiation comes off the ends?
Awesome.
That would be 0. So if I wanted to make this directional, I could take this whole thing and make it rotatable. Okay, so now the next thing I can do is I can take this dipole, make it like that, feed it like that. It's a half wavelength long. And I can beef this up because this generates energy in this direction and this direction, but also up and also down. Up and down don't really help us a whole lot, do they? But what does help is if I add a longer element back here and a shorter element or multiple shorter elements up front. This is known as a Yagi. This is a directional antenna, also known as a beam. It's a type of a beam antenna. This is known as the driven element. This is the reflector. And these are directors. These are elements that are not connected to the driven element. They are just floating in space. But because of where they are, being the spacing and the length of these elements, this acts as kind of like a bounce back. And these take energy that's going out in these directions and they sort of like refocus it going forward. So the overall effect of building a Yagi antenna, which looks like this, is to have a radiation pattern that changes from this into a radiation pattern that looks like this.
Yeah.
And if I measure the difference between there and there, what are my units of measurement, of improvement? Come on, everybody. What do you think? What are my units?
Better.
What are my units? Starts with a D.
You know, decibels.
Decibels. That would be the decibels. That would be my gain of one antenna over the other. And notice if I have power going out in the forward direction, I also have a little bit of power going out in the backward direction. The ratio of forward to backwards is known as the front to back ratio. And there's also sides. There's also the front to side ratio. By doing this, we basically can focus more of our energy in the forward direction. Now we can also say, okay, well, let's say we've done all that. How wide is our beam? Well, we can measure that. Here's our peak right here. And this we'll call 0 dB. And we want to take half power points. How many dB is half? You guys remember?
-3.
-3. So if I draw a circle, this is my -3 dB circle. I can go like this, and I can go like this. This is my beam width. That's my half power beam width. And what do you think? And that's measured in angles, but that comes out of the half power point, which is known as the 3 dB point. So now very quickly, what we're going to do is we're going to, and I know it's right around 4 o'clock. Everybody okay for me to finish this?
Yep.
I'm
Okay.
good.
Good. Okay. So what we're going to do now is we're going to take this antenna and we're going to say, okay, let's make an antenna. We're going to pick an antenna that is cut for 50 megahertz. Okay. What's our formula? 300 F and lambda. Okay, 50 megahertz. Where does that go?
In the F.
The F. Which one don't we know? Don't know the lambda. Lambda is 300 divided by 50 is 6. Okay. Now, the one thing we have to do here is because of the real world and the fact that in antenna wires, for the most part, depending on insulation and things like that, most antenna wires should be shortened by about 5%. the velocity factor, the speed of the wave along the wire is actually a little bit shorter. It's a little bit slower than the speed of light. So we actually have to shorten this by 5%. So we take 95% of 6 meters.
So you take 95% of the whole result.
Yeah, we're getting the wavelength.
Okay.
So, all right, so 95% of 6 meters. So I get what, 5.7 meters? That sound right?
What could you say why you reduced it again by 5%?
Yeah. Okay. So the speed of a radio wave in free space
Right.
is speed of light.
Right.
But if we were to take a conductor, it's a piece of copper, but it's going to have insulation, or it's going to have a little bit of oxidation or something on the outside of it.
Okay.
And the end effect of that is to create a velocity factor which is less than 1. So like
5%.
So it's about 5% lower. Our
Okay,
velocity factor is about 0.95. And
Got it.
also because of, end effects, capacitor, the fact that there's a little bit of capacitance here and there, there's self-inductance.
So it's like impurity, basically.
Well,
Is
it's really the fact that, like, if you were to take a piece of copper
Mhm.
and surround it, instead of with air, you have PVC insulation, the radio wave travels actually a little bit slower because it's impeded by
Right.
the fact that the energy has to propagate through the PVC.
Okay, I got you.
And it travels slower through the PVC because
Would it be
it's
safe to call it mechanical loss because it's going through some
no, not appreciably.
copper,
I mean,
PVC, whatever?
Yeah, there might be a tiny bit of loss, but it's not much. It's just the fact that, like, if we were to look at, we're going to get to coaxial cables, and we'll talk about velocity factor in coaxial cable too. But basically you just have to slow it down. You have to knock it down by 5% to make the numbers work out. So 5.7 meters, that is one full wave. Well, how long is this antenna supposed to be? It is a half wave dipole, so that we can draw our current distribution on it like this. So how long is a half wave? If a full wave is 5.7, what's a half wave?
2.85.
2.85 meters. Okay, excellent. So now we have to convert meters into inches. 39.3 inches per meter. And I'll grab my calculator unless somebody beats me to it. .85. Did anyone beat me to it?
Nope.
I got 112 inches. So if I were to make this a total of 112 inches, how long would I cut each leg of that antenna?
50 something.
Yep, that's it. That's how you make an antenna.
So, and that's for a half wave antenna, correct?
Yep.
So what if you want a full wave antenna?
I wouldn't do it.
Not practical?
Well, I mean, you can, but then you're basically looking at the fact that you have to move your feed point. And I'm going to ask why. Now, let's say that you, in fact, take this antenna. That's a really good question. We're going to take this antenna. It's still a half wave long, but we're going to feed it over here. This is actually a popular antenna. This is known as an N-fed half wave. Now I'm going to ask you a practical thing about this. So empirically, we're just looking at, just looking at your gut feeling. So if we were to take a look at this, what is the current right here compared to right here in the middle?
Nothing.
It's almost nothing.
Yeah.
E equals I times Z. Z is our feed point impedance, E divided by I. So if our current is very, very small, what's going to happen to our Z?
Be large.
It'd be big, because something divided by something small is big. So we have a big feed point impedance. At the center, Z is about 72 ohms. At the end, Z is about 2.2 K ohms. What is most coaxial cable? What is the feed point? What is the characteristic impedance of most coaxial cable? This is
Either
something we haven't done yet.
50 ohms or 75 for
50 to 75 ohms. This is a characteristic impedance.
So that 75 ohm cable would match that one better.
Oh yeah, that would be great for center feeding. But how about at the end, where your feed point impedance would be 2.2 K?
There ain't one.
Well, no, there's not. So you have to do something. So what would you do? Well,
Then you have to make a matcher.
what is that?
Transformer.
Transformer. Okay, so remember what a transformer does?
It's a wind down transformer.
Well, let's see. What does a transformer do? It transforms AC voltage into another AC voltage, right?
Right.
But because of the conservation of energy, it also transforms currents. So if the voltage is 7 to 1, the current is 1 to 7, because power has to be conserved. Therefore, they go in opposite direction. So now, if I were to take a look at what the overall is for what the thing actually does, R is equal to V divided by I is equal to 7 divided by 1/7 is 49. Which means that if I would have a transformer that was 7 to 1 turns ratio, I would actually get an equivalent, if I looked through it, resistance transformation or impedance transformation of 49 to 1. That actually works pretty well. If I have 50 ohms and multiply it by 49, that gets me pretty close to that 2.2 right there, 2.2, 2200. So what I would do is I would actually build, and this is if you get an end-fed half-wave antenna, you would actually get an impedance matching transformer along with it that it would allow you to feed power into it. So you're using a transformer not for transforming voltage specifically, but for transforming impedance. It's the same kind of thing if you have like high impedance microphone or high impedance headphones. You would use a transformer to transform and change the impedance so that you can deliver power into the device.
And that way you can stick the antenna straight up and down.
You can do anything you want with it. I mean, you could feed it sideways. You could put it at an angle. It doesn't really matter. Antenna doesn't care what you do with it.
Right, just all the signals coming off of it depends on which way you orient it.
That's right. It changes the pattern, and it changes the pattern, and it also changes, for instance, if you put it straight up and down, it changes the polarization.
Right, and plus your gain is the same all the way around instead of you getting one side that has more gain than the other.
That's right. It would be omnidirectional at that point. Okay, so now I'm just going to draw one more thing, which is a quarter wave. Quarter wave over a ground plane. A ground plane is basically something that looks like a reflective surface. If you're looking from over in space, what you see as you look from here is you see a reflection of this thing. This reflection looks like this. If you did not know that there was a mirror there that you're looking off of, you could not tell that there was no other half of the antenna. The nice thing about being able to do this is that a ground plane basically gives you the image of having a second half of the antenna. So if it's a quarter wave long and to the rest of the world, it looks like there's another half of it, how long does it look to the rest of the world?
It's like a halfway antenna.
Oh, there you go. There's our magic half wave antenna again. So your current goes like this, maximizes, and then you have this fake antenna down here, which is just sort of a projection of the top part, which isn't really there. But that really means that you actually have to have the base of the antenna grounded to the roof of your car or whatever, so that it can actually have current flowing in the roof of the car to make it look like that, which really does happen.
Yeah, after the top of your car rusts out.
Yeah, it's still metal. And actually what's cool about it is that you can actually use a mag mount. If you've ever seen a mag mount antenna, essentially it's a metal plate, and this is an insulator right here. And the metal plate goes through the insulator, but it's separated by a distance. What is that called if you have a plate and a plate?
Capacitor.
Capacitor. At 146 megahertz, that basically is a short circuit. It looks like it's connected. It's a very cool little trick. That's why mag mount antennas work at all. But the nice thing about it is that mag mount antennas, if they're vertical, are omnidirectional. So you can talk to everybody equally well. And for let's say the 6 meters, which we just did, instead of 112 inches, the whole thing instead would be 56 inches.
So like if the little plastic thing on the bottom of your roof mount antenna deteriorates and it rusts through to your roof, you no longer get that capacitive coupling.
Well, you might have a direct coupling.
Yeah.
That wouldn't necessarily be bad. So, all right, let's see. So this, for the 2 meter band, this is only a 19-inch antenna, which is really easy to build. They work great. They cost almost nothing to make.
God, I'm sorry. I have another meeting in about 15 minutes.
I will be done in 3 at most.
Okay. All right, cool.
Okay.
Thank you.
Okay, here we go. Antenna loading. That is a shortening coil. That is a way to make, let's say, a 19-inch antenna look like this tiny antenna on my handheld radio, which is only 7 inches long. We've basically taken a part of this wire and collapsed it into a small area. What is that? What do you think that does to the efficiency?
It's not as efficient.
Yeah, and in fact, because the peak current is down at the base, what have we done with all that current carrying stuff? The peak current is what generates most of the RF. Well, now we've smushed it all into a little coil. So it doesn't transmit well at all. In fact, I've seen an antenna that was as short as 2 inches. Now, it's basically just a big coil. But now if you happen to be right at the repeater site, it'll still work fine. So everything is a compliment. This is known as a rubber duck antenna. Some people say it's basically a dummy load because it's electrically the right length, but it's physically small and has a gain of about -4 dB. A beam antenna, again, we covered that, concentrate signals. Antenna gain is an increase in signal strength. A Yagi is a type of a beam. A rubber duck or dummy load antenna like this one kills your efficiency. Sometimes it matters, sometimes it doesn't. And finally, why would you never want to use a handheld radio inside your car with an antenna inside?
The car's metal all the way around.
Yep. Car does a great job at shielding your antenna. And a 5/8 wave antenna is considerably bigger than a quarter wave, but it has a lower angle of radiation and thus more gain. And that's it for today.
Cool. Good job.
It's got 2 questions for you before you run off.
Yep, please.
When we are looking at the antennas, you said we want half the length of the wave.
Yep.
So if you're working on the 6 meter band, then you transmit or receive on a 2 meter band, or do we need a completely separate antenna for that?
That is a good question. So if you're saying, if you build a 6 meter, let's say a 6 meter half wave or quarter wave antenna, which one?
say halfway, which we were talking about.
Okay.
So if we build a 6 meter,
6 meter half wave. Okay. So here we go. So this is 6 meters. It's cut for, let's say, 50 megahertz. Right? It's cut for. Doug, I think you're frozen. Either that or I'm frozen.
No, you're good.
Okay.
I'm here.
Okay. So it's cut for 50 megahertz. So this is 112 inches total. Roughly.
Okay.
Right? Okay. So let us say that we were to draw our wave on this, right? Okay. So what multiple is 50 compared to 150 megahertz?
3.
That would be about 3. Okay. Now the 2 meter band is from 144 to 148. So if we were to start drawing.
I'm so sorry. I have to skedaddle. I've got work. I gotta go.
Yeah. No, I'm just sticking around because he asked me a question. So
all right,
I'm so
take care. We'll
sorry,
see you
but
guys
I'll
tomorrow.
see you tomorrow.
see you guys in the morning.
All right, bye-bye.
Thanks, Scott. Appreciate it.
You bet. Okay, so Doug.
Yes,
So
sir.
all right, so we're looking at this antenna, which is a half wave, right? What is the only boundary condition that we have? What is the only constraint that has to be true of an antenna? Look at the wire and tell me.
The only constraint?
The only constraint that physics requires.
I don't know if the only one would be.
Only
Well,
one.
you're talking-
Only one. What has to happen at the end?
It's 0 at both ends.
Zero current at both ends. Exactly. That is the only constraint. I mean, physics says you cannot have, unless you have leakage to somewhere else, you have no current at the end of a piece of wire. You just can't. Okay. So what we're going to do is we're going to start at the end and we're going to just start drawing waves. So let's draw a half wave. And we're going to draw another half wave. And then at the other end, we're going to draw the same thing starting from the other end. And it never quite gets to the top, but it gets pretty close. If this was 150 megahertz, what does that mean? What does that look like? So what I want to ask you is our feed point right here, do we get high or low current?
High current.
High current, which means we have low impedance. Okay, that looks good. And does it look like it's truncated anywhere? Does it look like it's smaller than anything? Are there any points at which, okay, it doesn't meet, physics? If this was a full wave antenna, we'd basically have this, where we were feeding it at the center, that would be really hard. If it was not a harmonically related thing, it might look like this. Whoops, darn it. It might look like this. Right. Well,
So
that
if it
wouldn't
went
be
to
so great. That wouldn't be so
10
great.
meter, that might be more of a problem than a 2 meter would be.
Yeah. Well, I mean, the key is that for odd harmonic related bands, it works really well. So if you were to try, I mean, your pattern would be a little bit weird. Your radiation pattern would be a little weird, but you could easily feed power into it and it would work just fine. You could actually model it and see that you had some lobes, radiation lobes that you maybe didn't expect. Like if you looked at it from above, you would expect it to look like this, where it was going in those directions. And more than likely for a 3 half waves antenna, it might look something like this.
Okay.
Because you basically have this piece in the middle going up and this, which are a half wave apart, right? This is a half wave right there. And those are out of phase with each other. And then these are out of phase with each other by a half wave. So depending on, in this direction, because you're talking about like infinity distance away, they would probably cancel. But, and going off in this direction, just looking at it, half wave apart, that actually might work pretty well. So you might have radiation off the ends that you didn't expect. You might have something that looked like, oops. What I really should do is draw it in the same orientation. I'm going to draw it in the same orientation. So normally you would expect it to look like this. What you might end up with is something that looks like this. Shoot, stop that. You might end up with something that looks like this. And that is closer to omnidirectional, and you're not going to have as much gain. But it's going to be closer to omnidirectional, which you wouldn't have necessarily expected. And maybe that's something you want. And you can feed power into it. Now, and this is the same thing that we get when we harmonically relate, let's say the 7 megahertz band, which is 40 meters, and the 15 megahertz, sorry. Now it's slow to do it. 21 megahertz band, which is the 15 meter band. Notice what's the harmonic relationship there? Between 7 and 21. This is 3 times. So those you can build as 40 meter antenna for 7 megahertz, and it'll work just fine on 15. Again, it's not going to give you necessarily the desired pattern. But now here's the other thing. At 49 megahertz, which is close to the 6 meter band, what harmonic is that?
Seven, yeah.
That's the 7th harmonic. So really what you're going to end up with at that point is an antenna that is really long for that band, but it's harmonically related. So it will still work. The question is it going to give you the pattern that you want? So, I mean, it'll look, you know, the current will start at the ends. Let's see, 1, 2. Let's see.
And bottom line is, we really need to think through the antenna if we're doing a base station of some sort, based on what frequencies we want to use or what
Absolutely.
band.
Yeah, absolutely.
Hey, that looks symmetrical to me.
Yeah, it's pretty close. Right. I said it will work. But the thing is, like, it's not a gain antenna. So if you wanted an antenna that would provide you some gain, if you think of it like this, like, so here's an antenna, and here's another antenna, and here's another one. If you were to take these antennas and you fed them all so that they were radiating in phase with each other, so that this and this and this all generated a wavefront traveling this direction at the same time. If you were to go an infinity distance away, these would all reach at the exact same time.
Okay.
Right? So, but what you also want to do is make sure that since they're operating, in phase with each other, maybe you want to make it spacing wise between them so that you don't have anything in these directions. Now, that'll also mean that you have some energy going in this direction. So maybe you don't need 3, maybe you only need 2. And in order to improve on that, you can actually have another pair which is operating such that these wavefronts are generated, let's say this is a half wavelength apart, that these are a half wavelength ahead of these guys. So that this pair is radiating at the same time, and this pair is radiating at the same time, but a half a wavelength advance, so that by the time these get to here, they're all operating at the same time.
Synchronizing.
They're all synchronizing, and this is known as phasing. And if you happen to see like an AM radio station and you look at it from above and it's 3 big towers that are spaced a certain distance apart, that's exactly what they're doing. They're making multiple radiators act collaboratively with each other. The cool thing about it is that you can then take this whole system and you can make it so that I have this and this and this and this in a square pattern. I could make it so that these are operating together and these are operating late, so that my pattern looks like that. Or by electrically changing things, you know, by actually throwing some switches, I could make it so these guys are operating and these guys are operating ahead of time. So the pattern goes that way. Or by changing again with switches, I could have it so these are operating at normal time and these are operating in advance. So the pattern is now that way. And there's all kinds of games you can play with this if you're willing to, you know, willing to design it and wire it up. Actually, this is actually called a foursquare. Those are all vertical antennas. And that's known as a foursquare array. And they're actually really, really popular if you have the space for it. And if
Aren't
you
there
have,
some that have three,
I suppose you could, but
or they use two and then they just swap one out and it becomes directional?
I suppose, yeah, I suppose you could do 1, 2, and then one on either side. to
No, what I
change it.
mean, they actually just use three antennas and they use two at a time and then they just don't use the third one depending on the circumstances.
I suppose, yeah. I mean, you could actually just, you know, just kill two of them and use just one. That would give you an omnidirectional pattern. I know most radio stations, they do actually have to change their pattern for nighttime. And that's a way that they would do it.
Huh.
Got one more quick question,
Uh-huh.
and I'm not going to be here tomorrow, so I'm going to do it all on, you know, the
Yep.
video. This has been a tremendous amount of very good information.